This video gives an introduction to systems of linear equations. The equation 4x minus 5y plus 7.3z equals 27 is an example of a linear equation. And in general, a linear equation is an equation that can be written as the sum of a bunch of numbers called the coefficients times variables, all added up to equal another number. So in this example above, the numbers 4, -5, and 7.3 are the coefficients. The letters x, y, and z are the variables, and the products of coefficients times variables get added up to equal another number. So which of these three examples qualify as linear equations? The first one does not, because the 4 is multiplied by x squared, the square of a variable, not just a single variable. The second equation is also not a linear equation because the 1/3 is multiplied by a product of variables, not just a single variable. The third equation does qualify as a linear equation because if I rewrite it as 5a minus 6b plus the square root of 2c equals -2, then it is a sum of coefficients times variables, all added up to equal a number. A system of linear equations is just a set or collection of linear equations involving the same variables. Here's an example. This example involves 4 equations and 3 variables, r, s, and t. Notice that not every equation has to contain all the variables. A solution to a system of linear equations is a set of values for the variables so that each equation in the system is satisfied. For example, x equals 2, y equals 2, z equals 0 is a solution to this system of equations because if you plug in 2 for x and 2 for y and 0 for z, this satisfies the first equation, the second equation, and the third equation. On the other hand, x equals 1, y equals 3, and z equals 3/2 is not a solution. You can check that these values satisfy the first equation and the second equation, but not the third one. This concludes the brief introduction to systems of linear equations. If you've ever heard the expression, "there's more than one way to skin a cat," it definitely applies to solving systems of linear equations. In this video, I'll demonstrate 2 standard methods, the method of substitution and the method of elimination. If we want to solve this system of linear equations using the method of substitution, the basic idea is to use one of the equations to solve for a variable in terms of the other variables, and then substitute in to the other equations. In this example, I notice that in equation 3, I already have b solved for in terms of 2a plus c. So that makes it easy to substitute in 2a plus c everywhere I see a b in the other equations to get rid of the b variable there. So my first equation becomes -2a plus 3 times 2a plus c plus 4c equals 1. And my second equation becomes a plus 2a plus c plus 5c equals 2. I'll just carry down my third equation. Now, Let me simplify my first equation a bit. I'll distribute and group like terms. Minus 2a plus 6a is 4a, 3c plus 4c is 7c, and that equals 1. I'll also simplify the second equation by getting rid of the unnecessary parentheses and combining like terms. Once again, I'll just carry over the third equation. Notice that my first two equations now have only the variables a and c in them. Once again, I'll solve for one variable, say a, in one of the equations, say the first one, and then substitute that into the second equation. So in the first equation, I have 4a equals 1 minus 7c, so a equals 1/4 minus 7/4 c, and I'll plug that in to the second equation. So everywhere I see an a, I'm going to put in 1/4 minus 7/4 c. Once again, I'll simplify by distributing. Combining like terms, let's see, 6c is the same as 24/4 c, and 24/4 minus 21/4 is 3/4 c, so that's equal to 2. I can subtract the 3/4 to the other side, so I get 3/4 c equals 2 minus 3/4, so 2 is 8/4, so 8/4 minus 3/4 is 5/4, so that means that c is equal to 5/4 divided by 3/4, which is the same thing as 5/4 times 4/3, or 5/3. So I now have a numerical value for c. c is equal to 5/3. Poor equation 3 gets carried along for the ride yet again. Well, I've made huge progress here. Now that I have a numerical value for c, I can plug that number into this version of the first equation and get a number for a. So my first equation is now going to be a equals 1/4 minus 7/4 times 5/3. So that's 1/4 minus 35/12. That's 3/12 minus 35/12, which is minus 32/12, which is minus 8/3. So I have that a equals minus 8/3. Now I can plug a and c into the third equation to get b. Let me just copy the second equation over for completeness. And now the third equation becomes b equals 2 times negative 8/3 plus 5/3. So that's negative 16/3 plus 5/3, or negative 11/3. b equals negative 11/3. And I found the solution to the system of linear equations. I can check my work by plugging in these values into each of the three equations to make sure that they do in fact satisfy all three equations. Now I'm going to attack the same system of three linear equations using the method of elimination. The idea behind this method is I add or subtract multiples of equations together to get rid of variables. Before I start, though, I'm going to write my equations in the standard form where all the variables are on the left and all the constants are on the right. The first two equations are already in this standard form, so I'll just rewrite the third one. I'll put negative 2a plus b minus c equals 0 as an equivalent equation in standard form. I'm going to try to eliminate my variable a from some of the equations first. Notice that if I added together equation 1 and equation 2, I wouldn't eliminate the variable a because I have negative 2 copies of a here and only 1 copy of a here, so they wouldn't cancel out. However, if I take my equation 1 and add twice equation 2 to it, then I'll have 2 copies of a to cancel exactly with these negative 2 copies of a. So that's what I'm going to do. I'm going to take equation 2, twice equation 2, and once equation 1, add them together and put that in the place where I I currently have equation 2. So I'll do this over on the side. So I'll just write down my equation 1. That's negative 2a plus 3b plus 4c equals 1. And then I'm going to write down twice equation 2. So that's 2a plus 2b plus 10c equals 4, because I had to multiply everything by 2. And now I'm going to add these together, and I'll get 0 copies of A, 5 copies of B, 14 copies of C, and that's going to equal 5. So this is what I'm going to put as my new equation 2. Here, I'll write it down here. 5b plus 14c equals 5. My equation 1 I'm just going to copy down. Now I can do the same trick to replace equation 3 with something where variable a is eliminated. So for example, I could take equation 1 and subtract equation 3 and put that where equation 3 is. There are other things I could do too. For example, I could take twice equation 2 plus equation 3, but I'll just do it this way. So that means I'm taking equation 1. So equation 1, negative 2a plus 3b plus 4c equals 1. And I'm going to take equation 3, negative 2a plus b minus c equals 0. And I'm going to subtract. My a's will cancel. 3b minus b is 2b. 4c minus negative c is 4c plus c, so that's 5c. And 1 minus 0 is 1. So this is my new equation 3. 2b plus 5c equals 1. So as desired, I've gotten rid of variable a in the second and third equation. Now I'm going to try to use equation 2 and 3 to eliminate another variable, say b. In the second equation, b has a coefficient of 5. In the third equation, a coefficient of 2. So if I take twice equation 2, and then subtract 5 times equation 3, those coefficients on b should cancel out. Let's try that. So twice equation 2, that's going to be multiplying everything by 2. So 10b plus 28c equals 10. And now 5 times equation 3, that's going to be 10b plus 25c equals 5. But I'm going to subtract that, and that's going to give me, the b's cancel as I want, 3c, because 28 minus 25 is 3, 10 minus 5 is 5. So I'll copy down my equations. From here, it's easy to find c. It's just 5/3, same as before. And once again, I can plug in that number into the second equation to solve for b. 5b plus 14 times 5/3 equals 5 means that 5b is 5 minus 70/3. So that means that 5b is 15/3 minus 70/3, which is negative 55/3. So b is negative 55/3 divided by 5, which is minus 11/3. And finally, I can plug in both the value of c and the value of b into equation 1 to solve for a. I have minus 2a plus 3 times minus 11/3 plus 4 times 5/3 equals 1. And when the dust clears, that gives me the value of a as minus 8/3. So I've finished solving this system of equations using the method of elimination. In this video, we solved the same system of linear equations in 2 different ways. First using substitution, and then using elimination. And thankfully, we got the same answer both times, because math is wonderful like that. So in another video, I'll solve this same system of linear equations yet again in a third way by writing it as a matrix and using matrix row operations. In this video, we'll code a system of linear equations into a matrix. We'll then solve the system of linear equations in a systematic way, using tricks like adding two equations together or multiplying an equation by a constant. As we solve the system of equations, we'll perform equivalent manipulations on the rows of the matrix, and we'll see that ultimately solving the system of linear equations is equivalent to getting the matrix in a particularly nice form. Here's the system of linear equations that we want to solve. We've got three variables, a, b, and c, and three equations. I'm going to start by rewriting the equations in a more standard form by making sure the terms with the variables a, b, and c are all on the left side in ABC order, and the constants are all on the right side. The first two equations are already in that order, but the third equation I'll rewrite as negative 2a plus b minus c equals 0. Now, I could write that same information a little more concisely with an array or matrix of numbers by just recording the coefficients of a, b, and c, and then the constant term on the right. I'm omitting writing down the variable names themselves, a, b, and c, but no information is lost because the order of the numbers, the order of the coefficients, is in ABC order, with the constant terms on the right side of the equations in the far right column of the matrix. To solve this system of linear equations, I'm going to use tricks like adding multiples of one equation to another equation. But the arithmetic will work out simpler if I make use of equations that have coefficients of 1 in front of my variables. To keep things better organized, I'm going to actually switch the order of these two equations. So I'll just copy down my equations. Over on the matrix side, this is equivalent to just switching the orders of row 1 and row 2. Now I'm going to try to eliminate the variable a in the second and third equations. I can do this by adding twice the first equation to 1 time the second equation, and then replacing equation 2 with this sum. Similarly, I can add twice the first equation to equation 3 and replace equation 3 with that sum. So first I'll just copy down my equation 1 because it's not changing. Now equation 2 gets replaced with, let's see, negative 2a plus 2a gives me 0 times a, so there's no a term, which is what I want. Twice b plus 3 times b is 5 times b. Twice 5 times c plus 4 times c gives me 14c. And for the constant term, 2 times 2 plus 1 is 5. Similarly, I'm going to add twice this first equation to the third equation. Again, that eliminates my a. I get 2b plus b, which is 3b. And twice 5c minus c, that's 10c minus c, which is 9c. And the constant term is twice 2 plus 0, which is 4. Over on the matrix side, the same thing would be to multiply twice row 1 and add that to row 2 and replace row 2 with that, and then twice row 1 plus row 3 and replace row 3 with that. That gives me the first same row 1 as before. The second row is going to have 2 times 1 minus 2 is 0. 2 times 1 plus 3 is 5. 2 times 5 plus 4 is 14. 2 times 2 plus 1 is 5. Same idea for twice the row 1 plus row 3. 0, 3, 9, and 4. Notice that I've really done the same thing with both the equations and the matrices, and so it makes sense that if I just read off the coefficients of the equations here, I get the numbers in my matrix, whereas I have zeros where I'm missing the a altogether in the equations. Now I've eliminated the variable a from the second and third equations. Next, I'd like to use one of these two equations to eliminate variable b from an equation. If one of these equations happened to have a coefficient of 1 already, I would use that equation because it'd be easy to work with. But since they don't, I'll just use the second equation and make it have a coefficient of 1 in front of the b by multiplying it by 1/5. In other words, I'm going to take equation 2, multiply it by 1/5, and replace equation 2 with that. So I'll copy down the other two equations unchanged and replace the second equation with 1/5 of it, so that gives me b plus 14/5 c equals 1. Of course, I can do the same thing on the matrix side by taking 1/5 of row 2 and replacing row 2 with it. Now I'm in a position to use equation 2 to eliminate the variable b from equation 3. I can do that by taking -3 times equation 2, adding it to equation 3, and replacing equation 3 by it. On the matrix side, this corresponds to taking -3 times row 2 plus row 3 and replacing row 3 by it. For variety, I'm going to do the matrix side first this time. The first two rows just get copied as they are. Then the third row gets replaced by -3 times the second row plus the third row. So -3, well, the zeros just stay as 0, because -3 times 0 plus 0 is 0. And then -3 times 1 plus 3 gives me 0, which was the whole point, to eliminate that b variable. Now I have -3 times 14/5 plus 9. So that's a little tricky arithmetic here. Let's see, -3 times 14/5 plus 9, which is 45/5. So I think this works out to -42/5 plus 45/5, which is 3/5. And finally, -3 times 1 plus 4, that one's a little easier. That adds up to 1. The work on the equation side is pretty similar, so I'll just write it down quickly. I'm making a lot of progress because now I have an equation with just c in it. So if I multiply that equation by the reciprocal of the coefficient, so by 5/3, I'll have isolated c and solve for c. The first two equations I'll just leave as is for now. I can also do this on the matrix end. Now I've got my system of equations in a nice triangular form with all three variables in the first equation, only the last two variables in the second equation, and only the last variable in the third equation, where the leading variables all have coefficients of 1. Similarly, on the matrix side, I've got a bunch of zeros in the bottom left triangle with 1s along this diagonal. In the next steps, I'm going to work my way back up the equations by using this happy third equation to eliminate c from the first and second equations, and then using equation 2 to eliminate b from the first equation. So let me grab a little more space. To eliminate c from the second equation, I'll need to add the second equation to -14/5, the third equation. That'll make the coefficients match. Or on the matrix side, I'll take row 2 minus 14/5 row 3 and replace row 2 with that. I'll do the matrix side first. So row 1 and row 3 don't get changed, so I'll just copy those down. And now I'll fix up row 2. So let's see, 0 minus 14/5 0 is still 0. And if I do 1 minus 14/5 0, that's still 1. So those haven't changed. The next piece, 14/5 minus 14/5 times 1, that equals 0, like I wanted it to be. And finally, the real content here is that I'm going to take 1 minus 14/5 times 5/3. So that it simplifies to 1 minus 14/3, which is 3/3 minus 14/3, or minus 11/3. So that's what goes in this space here. If we did it with equations, we'd be going through the same process. Now we've actually solved for both b and c, and I still need to eliminate c from the first equation and b from the first equation to solve for a. I'll eliminate C first by replacing equation 1 with equation 1 minus 5 times equation 3, or the equivalent thing with matrix rows. So when I do equation 1 minus 5 times equation 3, that's, as far as the A terms, that's A minus 5 times no A's, so that's just A. For the B's, it's B minus 5 times no B's, so that's going to be just the B. And here I have 5C minus 5 times C, so that's no C's. I'll just leave a blank for the C's. And for the constant term, I have 2 minus 5 times 5/3. That's the same as 6/3 minus 25/3, which is minus 19/3. So I have minus 19/3 here, and I can copy the other two equations down. The equivalent thing happens on the matrix side. And finally, I'll eliminate B from the first equation by adding the first equation and minus the second equation. So let's see, I get A plus B minus B. That gets rid of the B and leaves just the A on the left side. And on the right side, I'm going to do minus 19/3 minus negative 11/3. So that's minus 19/3 plus 11/3, which is minus 8/3 on the right side. Same thing happens to the first row on the row side. 1, 0, 0, minus 8/3, and the other rows or equations just get copied down. Notice that now I can very easily read off my solution from my equations, but I can also read it off from my matrix. 1 times A equals negative 8/3, 1 times B is negative 11/3, and 1 times C is 5/3. To solve our system of linear equations, we use 3 operations. We swapped the order of equations. We added a multiple of one equation to another equation and replaced an equation with that. And we multiplied an equation by a constant. We can similarly use these operations on the matrix form of the system of equations by swapping rows, adding a multiple of a row to another row, and multiplying a row by a constant. By applying these operations systematically, we can end up with a matrix that just looks like 1s and 0s with the solution to the system over in the far right column. This corresponds to solving our system of equations and getting answers for A, B, and C. This video introduces a form of a matrix called reduced row echelon form that can be handy when using matrices to solve systems of linear equations. Consider this matrix that appeared in a previous video. If this matrix represents a system of linear equations in the variables x, y, and z, then what are the solutions to the system? Well, if it represents a system of equations, then this column represents the coefficients of x, this column is the coefficients of y, and this column is the coefficients of z. The final rightmost column represents the constants that are on the right sides of the equations. So if we write out the first equation in the first row, we get that 1 times x plus 0 times y plus 0 times z is equal to negative 8/3. In other words, x equals negative 8/3. Similarly, if we write out the second equation, we get that y is equal to negative 11/3. And the third equation tells us that z is equal to 5/3. So this matrix makes it really easy to read off the solution to a system of linear equations, much easier than this other matrix that we transformed into the simpler matrix and that actually has the same solution. Next, let's consider this matrix. If it also represents a system of linear equations in the variables x, y, and z, then what are the solutions to the system of equations? Well, if we write out the equations, 1 times x plus 2 times y plus 0 times z equals 3, 1 times z equals 7, and the last equation doesn't really give us any new information. It just says if we use 0 coefficients for all the variables, that adds up to 0. We can rewrite those equations a little more simply by saying that z equals 7 and x plus 2y equals 3. There's no unique solution here. As long as z equals 7 and x is equal to 3 minus 2y, we can make y be anything we want. For example, if y equals 0, then x would be 3. If y equals 1, then x would be 1 also. So we have infinitely many solutions. They're just all of the form 3 minus 2y, y, 7, where y can be anything. But it's still pretty easy to read off that information just from the matrix. Much easier than if we were given some other matrix, like this one, that turns out to actually contain equivalent information and have the same solution set. So what properties of these two matrices makes it particularly easy to read off the solution to the associated system of linear equations? One property is the presence of all these leading ones. The first number in each row that's not entirely zeros is a 1. Another property is the presence of lots of zeros. Notice that for each leading 1, all the numbers above it in its column are zeros. We'll use these two properties, the presence of leading ones and the presence of lots of zeros, especially above the leading ones, along with a couple other properties to define something called reduced row echelon form. This is the form of a matrix that makes it particularly easy to read off the solutions for its associated system of equations. A matrix, like the ones on the previous page, are said to be in reduced row echelon form, abbreviated RREF, if, first of all, the first non-zero entry on each row that is not entirely zeros is the number 1. These are called leading ones. That's certainly true for this matrix. For the two rows that aren't entirely zeros, the first entry that's not 0 is a 1. Second of all, the leading ones are in descending order. That means that each leading 1 is to the right of the leading ones in higher rows. That's also true in this example. This leading 1 has no higher rows, but this leading 1 is to the right of the leading 1 in the higher row. If I switched the first and second row of this matrix, though, then this property would no longer hold because this leading 1 would be to the left of the leading 1 above it, not to its right. The third property is that each leading 1 has a column of zeros above it. In other words, it has a 0 above it in every row above it. So in this example, this leading 1 doesn't have any rows above it, and this leading 1 only has 1 row above it, but it does have a 0 above it in that row. And the final condition is that if there are any rows that are entirely zeros, they must be at the bottom of the matrix. Definitely true in this example. So this example is an example of a matrix in reduced row echelon form. Please pause the video for a moment and see if you can figure out which of these 6 matrices are in reduced row echelon form. Matrix A is in reduced row echelon form. It has a leading 1 in every row that's not entirely zeros. The ones are in descending order. Above each leading 1, there's a 0, or column of zeros, and the rows that are entirely zeros are at the bottom. Matrix B is also in reduced row echelon form. All three of its rows have leading ones. The ones are in descending order, and above each leading one, there's a column of zeros. There are no rows that are entirely zero here to worry about. Matrix C is not in reduced row echelon form. Why not? Well, it doesn't have a leading 1 in the second row. The first non-zero entry of this second row is a 2 instead of a 1. Matrix D is also not in reduced row echelon form. This time the problem is that the leading ones are not in descending order. This leading 1 is to the right of the leading 1 in the row above it, as we want it to be, but this leading 1 is actually to the left of the leading 1 in the row above it. Matrix E is not in reduced row echelon form. It does have the leading ones, and they are in descending order, but we don't always have zeros above the leading ones. In particular, this leading 1 has a 1 above it, not a column of zeros. Finally, this last matrix is not in reduced row echelon form either. This time it's the simple matter of the row that's entirely zeros is supposed to go at the bottom. In this video, we introduced an especially nice form for a matrix called reduced row echelon form. To be in reduced row echelon form, a matrix has to have a leading 1 in each row that is not entirely zeros. The leading ones have to be in descending order. The leading ones have to be topped by columns of zeros. And any rows that are all zeros have to go at the bottom. In a future video, we'll practice getting matrices into reduced row echelon form using an algorithm called Gaussian elimination. In this video, we'll practice converting matrices to reduced row echelon form using elementary row operations. Recall that elementary row operations consist of the following three things: swapping rows, multiplying a row by a constant, and adding a multiple of a row to another row. If we think of each row of the matrix as representing a linear equation, then these are exactly the steps we might take to solve the system of linear equations. Recall also that a matrix is in reduced row echelon form if there is a leading 1 in each row that is not all zeros. The leading ones go in descending order, kind of like a staircase, although there can be some uneven steps. The leading ones have columns of zeros above them, and any rows that are all zeros are at the bottom. So this is our destination, or our goal, reduced row echelon form, and this is our methods of getting there. We'll see, in fact, that any matrix can be transformed to reduced row echelon form using just these elementary row operations. And the algorithm that we'll use to get there is called Gaussian elimination. So let's put the matrix for this system of linear equations into reduced row echelon form. The instructions talk about an augmented matrix. All that means is that we're going to write the coefficients of the first variable, x1, in the far left column, followed by the coefficients of x2, the coefficients of x3, and finally, these constants on the right side of the equations will go in the far right column. The constants can be thought of the additional or augmented part of the matrix. So the first equation becomes the row -7, -6, -12, -33. The next equation becomes 5, 5, 7, 24, and the last equation becomes 1. There's a 0 as the coefficient of x2, since x2 doesn't appear in this equation, and then 4 as the coefficient of x3, and 5 as the constant term. To get this matrix in reduced row echelon form, I'm going to need a leading 1 in every row that's not all zeros. Well, I could get a leading 1 in the first row just by dividing the whole row by -7, but I think it's going to be easier instead to just swap the first and the third rows. So that'll give me this new matrix. Now I'm going to try to get zeros in the column under this one so that the next leading ones will be to the right of this leading one, as they're supposed to be. To get a 0 in this position, I'm going to take -5 times the first row plus the second row and replace the second row with that sum. So -5 times the first row plus the second row goes to where the second row is. The first row I'll just copy over. Now in the second row, -5 plus 5 is 0. -5 times 0 plus 5 is 5. -5 times 4 plus 7 is -20 plus 7, so that's going to be -13. And -5 times 5 plus 24, that's -25 plus 24, so that's -1. I can also get a 0 in this position if I take 7 times the first row and add it to the third row. So that's 7 times R1 plus R3 goes in the R3 position. So that gives me 0, -6. Now 7 times 4 is 28 minus 12 is going to be 16, and 7 times 5 is 35 minus 33 is 2. Now that I've got a leading 1 on the left side of the first row and zeros below it, it's time to worry about getting a leading 1 in the next column somewhere. There are a couple possible approaches. I could multiply the second row by 1/5 in order to turn that 5 into a 1. But since that'll create some nasty fractions, I think instead I'd like to maybe add together these two rows and replace say the second row with their sum. So that's R2 plus R3 goes in the R2 position. I'll just copy over the first row. I'm not going to change it. And the second row becomes the sum, so that's 0, -1, 3, and 1. I'll copy the third row down for now too. Now I just have to multiply the second row by -1, and I'll have my leading 1 in the second row. Now I'm going to work to get zeros below this leading 1. So I want to get a 0 here, so I can do that by taking 6 times row 2 and adding it to row 3. 6R2 plus R3, and I'll replace R3 with that. I'll copy the first two rows over. And now in the third row, I'll get 6 times 0 plus 0 is 0. 6 times 1 minus 6 is 0, like I want it to be. 6 times -3 plus 16, that's -2. 6 times -1 plus 2 is -4. So now I've got a leading 1 in the first row with zeros below it, a leading 1 in the second row with zeros below it. My next job is to get a leading 1 in the third row. And to do that, I'm just going to multiply the third row by 1 over -2. That gives me this matrix, which has a leading 1 in every row, and the leading 1s are in descending order. There are no rows of all zeros that I have to worry about, but there is one more thing I have to fix. I need to have zeros above each of the leading 1s. I'm fine here because there's nothing above it, fine here because there's a 0 above it, but here I need to make zeros in these rows above this 1. Now I can do that by adding a multiple of row 3 to each of row 2 and row 1. To get rid of the -3 in row 2, I'm going to take 3 times R3 and add it to R2 and replace R2 with that. To get rid of the 4 in row 1, I'm going to take -4 times R3 plus R1 and replace R1 with it. Notice that that won't mess up any of the progress we've made with these leading ones here and all these zeros because row 3 just has zeros everywhere before that leading one, so adding a multiple of it to the previous rows won't mess up the columns over here that have the zeros in them. Okay, so I'll copy the third row down as it is now, not making any changes to this. For the second row, I need 3 times row 3 plus row 2. So that's going to give me 0, 1, 0, and then 3 times 2 plus negative 1 is going to be 6 minus 1, which is 5. Now the first row gets replaced by negative 4 times R3 plus R1. So that's just 1, 0, 0 here. And negative 4 times 2 is negative 8 plus 5 gives me negative 3. I now have a matrix in reduced row echelon form, and I can use it to read off the solution to my system of equations. My solution is just x1 is negative 3, x2 is 5, and x3 is 2. So before we leave this problem, let's just review some of the steps we took to get ourselves into reduced row echelon form. We first focused on getting a 1 in the top row and as far left as possible to get a leading 1 there. Then we got zeros below it by adding multiples of that first row to the other rows. Then we kind of moved down and in a bit and focused on getting a 1 in this next position, or at least in the second row as far left as we could. Once we had the 1 there, we could use multiples of this second row to get zeros below it. Finally, we got a leading 1 in the third row as far left as we could. And once we had worked forwards like that to get our leading 1s in descending order, we could go back up and get zeros above them as needed by using multiples of the row to eliminate the numbers in the rows above it. This systematic process that we used is called Gaussian elimination. In this video, we used elementary row operations to put a matrix into reduced row echelon form in a systematic process called Gaussian elimination. This process is complex, and it takes a while to get adept at it, but once you do, you'll have a powerful tool for solving systems of linear equations efficiently. In this video, we'll address the question of how many solutions does a system of linear equations have, and how can we tell? Addressing this question can also be thought of as addressing the existence and uniqueness of solutions, since existence of solutions has to do with having at least one solution, and uniqueness has to do with having no more than one solution. Let's start with some simple examples of systems of equations with 2 equations and 2 variables. How many solutions does each of these 3 systems have? In the first case, if we solve these 2 equations together by adding them up, we get 2x equals 4, so x equals 2, and plugging x equals 2 back into, say, the first equation gives us 2 plus y equals 1, which means that y is negative 1. So here we have a solution, x equals 2 and y equals negative 1, and is unique. In the second system, it's not too hard to see that there's a problem. We have that x plus y should equal 1, but x plus y should also equal 4. Well, both of those can't be true. And in fact, if we try to solve these equations together, for example, by taking the first equation and subtracting the second equation, we get 0x, 0y equals 1 minus 4, negative 3, so 0 equals negative 3, which is definitely impossible. So no solutions exist for this system of equations. For the third system, you might notice that the second equation really just contains the same information as the first equation. It's just the first equation multiplied by 2. And in fact, if we try to solve the equations together, for example, by taking negative 2 times the first equation and adding it to the second equation, we'll get 0 x's plus 0 y's equals negative 2 times 1 plus 2 is 0. So you just get 0 equals 0, which is always true. It doesn't contain any new information. So in fact, any pairs of x and y that satisfy x plus y equals 1 will work. So we can think of y as being a free variable. We can set y to anything, and then we just need x to equal 1 minus y. So one way of writing the solution set is all pairs x, y, where x equals 1 minus y, or you could write it as all pairs of the form 1 minus y, y. Particular examples of solutions might be, for example, if y equals 1, then x will be 0, so 0, 1. Or when y equals 2, x will be minus 1, so minus 1, 2 would be another solution. There are infinitely many of these solutions. So we've observed 3 possible outcomes to solving a system of linear equations. One solution, no solutions, and infinitely many solutions. Thinking about these equations as equations of lines in the plane can shed some light on what's going on in these 3 situations. Here's a graph of the equation x plus y equals 1, which can also be written as y equals negative x plus 1, and a graph of x minus y equals 3, which can also be written as y equals x minus 3. And you'll notice that those 2 lines intersect in this unique point with coordinates 2, negative 1. However, when we graph the second set of equations, we get 2 parallel lines, both of which have slope negative 1, but different y-intercepts. Therefore, the 2 lines have no intersection, and the system of equations has no solution. Finally, when we graph these 2 equations, our 2 lines are on top of each other. So any point on this line satisfies both equations, and there's an infinite number of solutions to the system. Let's analyze these 3 systems from yet one more perspective. Let's write down their augmented matrices and row reduce them. Here's the augmented matrix for the first system. Let's take negative 1 times the first row and add it to the second row. Replace the second row with that. We can then multiply the second row by negative 1/2. And finally, get rid of this 1 up here above that leading 1 by taking negative 1 times the second row and adding it to the first row. We get a nice matrix in reduced row echelon form where we can read off the solution. 1 times x equals 2, and 1 times y equals negative 1. No surprises there. But let's see what happens when we put the next system in matrix form and try to row reduce it. So once again, we'll take negative 1 times the first row plus the second row and replace the second row with that. We can continue to row reduce by multiplying the second row by 1/3 and then subtracting that second row from the first row. We've got something weird going on here. We've got a row that has all zeros in it except a 1 on the very far right. That's saying that 0 times our variables, x and y, add up to 1, which is impossible. So this weird row with all zeros and a 1 on the far right is a signal that we have a contradiction, that we have an impossible system of linear equations with no solution. Finally, if we write down and row reduce the third augmented matrix, notice that in addition to the far left column that has a leading 1 and the far right column that just represents those constant terms, we have a column, this middle column, that doesn't have any leading 1s in it. That's different from this first situation in which all the columns besides the far right column of constants, all of those other columns had leading 1s. Because this second column doesn't have a leading 1 in it, the variable that it represents, which here is y, is what's called a free variable. It can be anything. So we have no restrictions on y, and the only restriction we have is that 1 times x plus 1 times y equals 1. So y is free and independent, whereas x, we can say, depends on y. Of course, we could have made x independent and y depend on x if we wanted to. But making y the free variable makes it easy to recognize it as coming from the column that doesn't have a leading 1. The absence of a leading 1 in a column is what we'll be looking for as a signal that our system has infinitely many solutions. In fact, the 3 situations that we see here are the only situations that we can have for any system of linear equations, even much more complicated ones. A system of linear equations can either have one unique solution, or it can have no solutions, or it can have infinitely many solutions. The systems that have no solutions are called inconsistent systems, while the systems with solutions are called consistent. Let's look at some other examples. Here, we're supposed to find the solutions to a system of linear equations. So we're supposed to interpret this matrix as the augmented matrix of a system of equations in 3 variables, say x1, x2, and x3, with this last column being the constant terms. I'll sketch out the row reduction process, but leave the details for you to work out separately if you're interested. Here I've used the first equation, which already has a 1 in its leftmost column, to get rid of the coefficients underneath it by adding appropriate multiples of this first equation to the other equations. Here I've turned this -4 into a leading 1 just by multiplying the second row by -1/4. Now I use the second row to zero out the entries below this leading 1. And I turn this leading -10 into a leading 1 by multiplying that row by -1/10. Finally, I can zero out the entries above this leading 1 by adding multiples of the third row to these 2 rows, and use the second row to zero out the entries above its leading 1. Now that I've got my matrix in reduced row echelon form, what kind of solution set does my system of linear equations have? Well, because of this last row, in which all the coefficients of my variables are 0, but the constant term is 1, I have a contradictory equation, and so I have no solutions. In fact, I could have predicted this even from this stage of reducing my matrix without completing the entire row reduction process. Let's try another example. To row reduce, I'll start by swapping my first and second rows. Since I already have a leading 1 in the first row now, I'll use it to zero out the entries below it, namely this entry in the third row. I'll make this leading 2 a leading 1 by dividing the second row by 2, and use the second row to zero out the entries below its leading 1. Finally, I'll get rid of any non-zero entries above my leading 1s. So my matrix is now in reduced row echelon form. Notice that I don't have any of those contradiction rows where I have all zeros and then just a 1 in my constant column. I don't have any contradiction rows, but I do have some columns that don't have leading 1s in them. In fact, columns that correspond to variables. I don't care about this far right constant term column, but over here I have a column corresponding to the variable x2 that doesn't have a leading 1 in it. So that means that x2 can be used as a free variable. I can set it to be any number I like. And x1 has the relationship that x1 minus 7x2 equals 17. In other words, x1 is 7x2 plus 17. Now x3 has got to be equal to -7, and x4 has to equal -2. So I have infinitely many solutions that can all be written in terms of one free variable. That is, I can write them as x1 as 7x2 plus 17, x2 is just x2, and then -7 for x3 and -2 for x4. These ordered quadruplets give my infinite family of solutions. For completeness, I'll give one more example that illustrates the third possibility of a unique solution, but I'll leave out even more of the details in the row reduction process. With my matrix in reduced row echelon form, I can analyze this solution set. I don't have any of those contradictory rows where I have all zeros as my coefficients and then a non-zero element for my constant term. Having all zeros as coefficients and then a 0 as my constant term is fine. That's just saying 0 times x1 plus 0 times x2 plus 0 times x3 is 0, which has to be true. It doesn't add any more information. So I can just ignore this row of entirely zeros. And once I ignore it, I don't have any contradictory rows, and I don't have any columns that don't have leading ones in them, besides the constant column. And therefore, I'm going to have a unique solution. My solution will be that x1 is equal to 2, x2 equals 3, and x3 equals -1. So here is an example of a system that has a unique solution. This video revealed the fact that there are 3 and only 3 possibilities for the number of solutions for a system of linear equations. There could be one unique solution, there could be no solutions, or there could be infinitely many solutions. We can observe which situation we're in by examining the augmented matrix for the system once it's converted to reduced row echelon form. If the matrix has a contradictory row with all zeros and then a 1 in the constant column, then that tells us we have no solutions. If there's no such contradictory row, but there are columns corresponding to variables that don't have leading ones in them, then the variables for those columns without leading ones can be used as free variables, and there are infinitely many solutions. Finally, if there are no contradictory rows, and all columns corresponding to variables have leading ones in them, then we're in the situation where we have one unique solution. The columns corresponding to variables, by that I just mean all the columns except for the far right column, which corresponds to those constant terms. That concludes this video on existence and uniqueness of solutions. This video gives an example of setting up and solving a system of linear equations. So my friend Pete is going on a backpacking trip, and for simplicity, he decides to only bring 3 kinds of food: peanuts, corn nuts, and freeze-dried mango. He wants to use exactly 12 liters of space and 5 kilograms of weight. Since freeze-dried mango is so delicious, he'd like to take as much freeze-dried mango in liters as peanuts and corn nuts combined. Is this possible? In order to describe this situation in equations, we're first going to need to decide on some variables to describe our unknowns. We don't know, and Pete would probably like us to tell him, how much peanuts, corn nuts, and freeze-dried mango he should bring to satisfy these criteria. So I'm going to let P equal the amount of peanuts, C be the amount of corn nuts, and M be the amount of mango. But hang on a second, what should my units be here? I could describe the amounts in liters or in kilograms, or I suppose I could describe them in numbers, like number of peanuts, corn nuts, and mango slices. But since this last condition has to do with liters, I think it'll be easiest for me to stick with liters. So I'll let these amounts be in terms of liters. Now, the fact that he wants to use exactly 12 liters of space for all this food already gives me one equation. I know that the amount of peanuts in liters plus the amount of corn nuts in liters plus the amount of mango in liters has to add up to 12 liters. Now, I also know that the weights of these food items need to add up to exactly 5 kilograms of weight. To write this condition as an equation, I'm going to need to know how much P liters of peanuts weighs in kilograms, and similarly for the corn nuts and the mango. A quick internet search brings me to an aquacalc.com website that has all these food volume to weight conversions. And I find that for peanuts, shelled peanuts, 1 liter corresponds to 0.64 kilograms of weight. For corn nuts, 1 liter is 0.36 kilograms. And for freeze-dried mango, 1 liter is 0.1 kilogram. So therefore, the P liters of peanuts will weigh 0.64 times P kilograms. The C corn nuts will weigh 0.36 times C kilograms, and the M liters of mango will weigh 0.1 times M kilograms. So that has to add up to 5 kilograms. The third and final condition is that Pete wants to take as much freeze-dried mango in liters as peanuts and corn nuts combined. So to write that as an equation, I'm going to write that mango liters is equal to peanut liters plus corn nut liters. So now I have 3 equations in 3 variables, a nice system of equations, and let's solve this system of equations to find out how much peanuts, corn nuts, and mango Pete should bring. So I've copied these 3 equations over to a new page where we can solve them. There are many ways of solving systems of linear equations, and in another video I show some systematic methods. But here I'm just going to use an ad hoc method. I'm noticing that since m is equal to p plus c, I should be able to just substitute in for the expression p plus c. That's the same thing as m. So that means that m plus m is equal to 12. In other words, 2m is equal to 12, so m has to equal 6. Now if I plug that number 6 in to the first and second equation, I get p plus c plus 6 equals 12. So in other words, p plus c equals 6. And in the second equation, I get 0.64p plus 0.36c plus 0.1 times 6 equals 5. So that simplifies a little bit here. Now from the new first equation, I can actually rewrite this to solve for p in terms of c, and I can plug that in to the second equation, 0.64 6 minus c plus 0.36c equals 4.4. That simplifies to the following. Now my second equation involves only the variable c. So I'll simplify a little further by combining c terms and moving my constant terms all the way to the right side. So now I can divide to get c equals 0.56 over negative 0.28, which is negative 2. And finally, plugging that value c equals negative 2 into this version of equation 1, I get that p equals 6 minus negative 2, so p equals 8. So I found out that anything that satisfies these 3 equations must have p equals 8, c equals negative 2, and m equals 6. And I can verify the solution does in fact work by plugging back into my original equations and seeing that it satisfies all 3 of them. So this is our unique solution to our system of equations, but is this a solution to Pete's backpacking issue? Not really, because in order to satisfy all his criteria, we're going to need to have negative 2 liters of corn nuts. So in fact, in the real world application where all these variables need to have non-negative values, there is no solution. Sorry, Pete. And that concludes this example of setting up and solving a system of linear equations. In this video, we'll talk about adding 2 matrices together. We'll also talk about multiplying a matrix by a scalar, like the number 5. The word scalar is just a fancy word for a number to distinguish it from from multiplying by a matrix. In a future video, we'll talk about multiplying two matrices together, but not yet. Recall that a matrix is just an array of numbers, like this one. The dimensions of a matrix are the number of rows and the number of columns. For example, in this matrix above, we have 2 rows and 3 columns, so we say that this is a 2 by 3 matrix. The number of rows is always listed first. The elements of a matrix are just these individual entries. So this matrix has 6 elements. Sometimes these elements are indexed by their row number and column number. So for example, if I want the element A21, that would be the element in the second row and the first column, so that would be the number 5. If instead I wanted the element A12, that would be the first row and the second column, so that would be the number 0. Sometimes you'll see a whole matrix listed out with this abstract notation. So A11, A12, A13, A21, A22, A23 is the correct ordering for the entries in this 2 by 3 matrix. The first index in these double indices tells you the row number, so each of these numbers is in row 1, and the second index tells you the column number. To add together two matrices of the same dimensions, so here dimensions 2 by 3, we do just what you would think we would do. We add the corresponding elements together. So 1 plus 3 is 4. 0 plus -5 is -5. -4 plus 7 is 3. And similarly, if we add corresponding elements in the bottom row, we get 6, 11, 2. To subtract two matrices of the same dimensions, we subtract elements. So here we get -2, 5, -11, 4, 7, and 0. Note that it's not possible to add or subtract matrices with different dimensions, because we wouldn't be able to line up corresponding elements. To multiply a matrix by a scalar, it's just a number, we again do just what you'd think we do. We multiply each element by that number. So here we're multiplying 3 by this matrix. That just means we get 3 times 1, which is 3, 3 times 0 is 0, 3 times -4 is -12, and similarly, we get these numbers on the bottom row. It's most typical to write scalar multiplication with the scalar on the left side, but it's also possible to write the scalar multiplication with the scalar on the right side, and it means the same thing. One last point is that instead of writing subtraction of matrices, it's also possible to write it as addition together with scalar multiplication by -1. I'd like to go through some properties of matrix addition and scalar multiplication, but before I do that, I want to review some properties of just addition and multiplication of numbers. So we say that addition is associative. What this means is if you have numbers like, say, 3 plus 4, and you add those together and add another number like 7, that's the same thing as 3 plus 4 plus 7. You can group these in other orders, and more generally, if you have A plus B grouped plus C, that's the same thing as adding A to the grouping B plus C. That's the associative property. Addition is commutative. That means it doesn't matter what order you add things in. A plus B is always the same as B plus A. There's something called an additive identity. We usually just call it the number 0. The key property of number 0 with addition is that if you add 0 to any number, you just get the same number you started with. We have this property called the distributive property. Multiplication distributes over addition. So if you have 4 times 3 plus 5, that's the same thing as 4 times 3 plus 4 times 5. And that's true no matter what numbers A, B, and C you stick in the places of 4, 3, and 5. When you multiply any number by 0, you just get 0. Multiplication is also associative. A times B times C is the same thing as doing A times B first and then multiplying that answer by C. And multiplication is commutative. A times B is the same as B times A. Well, guess what? These same properties hold for matrix addition and scalar multiplication. If you add matrices together, it doesn't matter if you first add the two matrices A plus B and then add that result to C, get the same thing if you group it the other way. And this follows really from the associative property for addition of numbers. Because when we're adding matrices, we're just adding numbers in each position of the matrix. Same thing for commutativity. You can add matrices in either direction and you'll get the same answer, just because you can add numbers in either direction and you'll get the same answer. Now what about this additive identity? Is there such a thing as a zero matrix that you can add on to any other matrix and just get the same matrix? I'll write the 0 with little brackets around it to emphasize that it's supposed to be a matrix, not the scalar number 0. See if you could guess what that matrix would look like. If you're guessing that it would have all entries 0, you're exactly right. Because when you add 0 to every single element of a matrix, you're just going to get the same matrix again. Notice that, to be precise, there's actually a lot of different 0 matrices. One for every possible pair of dimensions, m by n. Just like for regular multiplication and addition of numbers, scalar multiplication over matrices is distributive. So if I have a scalar k and I multiply it by the sum of two matrices A and B, I could instead first multiply the first matrix by k and then multiply the second matrix by k and then add them up. Multiplication by the scalar 0 is just going to multiply every single entry of my matrix by 0, so that's going to give me a 0 matrix. Scalar multiplication is associative in the sense that if you have like k times L and you multiply that by a matrix A, that's the same thing as k times LA. And scalar multiplication is commutative in the sense that k times A is the same thing as A times k, pretty much by definition. So all of the properties that we've mentioned about regular addition and multiplication work for matrix addition and scalar multiplication with matrices. But we'll see in a future video when we talk about matrix multiplication that there are actually some surprises with matrix multiplication, and not all these properties will hold. Let's end with an example, finding 5a minus b, where A is this 3 by 3 matrix and B is that 3 by 3 matrix. In other words, I want to take 5 times this matrix and then subtract that matrix. So to do 5 times this matrix, I'm just going to multiply all the entries by 5. Then I'll subtract this other matrix. So I'll just subtract entries, and I get 2 minus 20 minus 4 minus 4, 25 minus 13, 9, 0, and minus 2 as my final answer. In this video, we added matrices together, element by element, did scalar multiplication by multiplying each element by that scalar, and we talked about some of the properties. Previously, we defined the sum of two matrices in the simplest, most natural way that we could, simply by adding corresponding elements. It would be possible to invent a matrix multiplication that worked similarly, just by multiplying element by element. 1 times 5 is 5, 2 times 6 is 12, and so on. But we're not going to do matrix multiplication this way. The standard definition of matrix multiplication the topic of this video, is more complicated. It's also much more useful. So one reason that we want to define matrix multiplication in this more complicated way is that when we use matrices to represent transformations or changes in a system, then applying two transformations, one after the other, will exactly correspond to multiplying two matrices in the way that I'm going to show you. And this will allow us to use matrix arithmetic to model complex systems over time. So before we define multiplication for general matrices, I'm going to start with very special matrices called vectors. A matrix that has only one column is called a column vector. So this is an example of a column vector. It has 4 entries, all in one column. So as a matrix, it's a 4 by 1 matrix. And in general, a column vector is an n by 1 matrix for some number n. A matrix that has only one row is called a row vector. Here's an example of a row vector. It's a length 4 row vector, or in other words, a 1 by 4 matrix. And in general, a row vector is the same thing as a 1 by n matrix for some number n. I'm going to show you how to multiply a 1 by n row vector with an n by 1 column vector, first with this example. To multiply this 1 by 4 row vector with this 4 by 1 column vector, we multiply the first entry of the row vector with the first entry of the column vector, the second entry with the second entry, and so on, and then we add those products up. So we're going to do 3 times 1 plus 6 times negative 2 plus 1 times 3 plus negative 1 times 5, which adds up to negative 11. Sometimes I like to visualize this as tipping the row vector on its end and then multiplying numbers at the same height with the column vector and adding them up. Let's write this multiplication process as an abstract formula. Let's write our row vector, say W, and write out its entries, W1, W2, W3, all the way through Wn. And then let's write our column vector V with entries V1, V2, V3, all the way through Vn. To perform the multiplication of these two vectors, W times V, we multiply W1 times V1, add that to W2 times V2 plus W3 times V3, and so on, all the way up to the last product, Wn times Vn. We add up all those terms. If you're familiar with summation notation written with this big letter sigma, this can be written as the sum of Wi times Vi, where I starts at 1 and goes through n. Notice that we've only defined multiplication for a 1 by n row vector times an n by 1 column vector. It wouldn't make sense to multiply a row vector and column vector with different number of entries because the entries wouldn't line up the way we're using them. It would be possible to define multiplying a column vector times a row vector in that order. There are a couple ways to define this, one of which may surprise you. But for now, we're going to stick with multiplying row vectors times column vectors in that order because that's what we need to define more general matrix multiplication. So now let's define matrix multiplication in general. Let's suppose that A is an m by r matrix and B is an r by n matrix. Then the product, A times B, is an m by n matrix, and the entry in row I and column J is given by the product of row I of A and column J of B. Notice that a row of A is a 1 by r row vector, and a column of B is an r by 1 column vector. So this is just the kind of vector product that we defined on the previous page. I want to emphasize that when we're multiplying two matrices, A times B in that order, then the number of columns of A needs to equal the number of rows of B. That's the only way that the elements will line up when we're doing our vector product, and the only way that the matrix multiplication will make sense. Let's look at an example where A is this 4 by 2 matrix, and B is this 2 by 3 matrix. Notice that the number of columns of A is equal to the number of rows of B, so it makes sense to compute A times B in that order, even though it wouldn't make sense to compute B times A. Suppose we want to compute the product A times B. I'll call that matrix C. And suppose we want to just find like the entry in the second row and the third column. So I could call that C23. To do that, we need to take the second row of A, so that's 1, -5, and multiply it by the third column of B, so that's 6, 3, and we do our vector product, 1 times 6 plus -5 times 3, so that's 6 minus 15, which is -9. So C is going to be a 4 by 3 matrix, and its entry in the second row and third column is going to be a -9. But in practice, we're not just going to want to compute one random entry of our product matrix. We want to compute all its entries. So let's do this in a systematic way, starting with the first row and the first column of B to get the entry in the 1, 1 position. Let me rewrite my matrices down here, and I'll leave space for my 4 by 3 product matrix. So now for my entry in the top left position, the first row and the first column, I'm going to take the first row of A and multiply it by the first column of B. 2 times 4 plus 3 times 1, that's 8 plus 3, which is 11. Now let's get the next entry in the first row and the second column. So that's going to be the first row of A and the second column of B. So we'll take 2 times 3 plus 3 times -2. That's 6 minus 6, or 0. Moving right along, to get the entry here, I'm going to need the first row of A and the third column of B. So that's 2 times 6 plus 3 times 3, which is 12 plus 9, or 21. Now I'm ready to move on to the next row of the product. So that's the second row, first column position. So that'll be the second row of A times the first column of B. We have 1 times 4 plus -5 times 1, so that's 4 minus 5, or -1. Continuing like this, for the next entry, we'll take the second row times the second column. So that's 1 times 3 plus -5 times -2. 3 plus 10 is 13. And the second row times the third column gives us 1 times 6 plus -5 times 3. So that's 6 minus 15, which is -9. That's the one we calculated before. The last two rows are similar. For the third row, for the third row of the product, I need to take the third row of A and multiply it by each column in turn. 0 times 4 plus 7 times 1 is 7. 0 times 3 plus 7 times -2 is -14. 0 times 6 plus 7 times 3 is 21. Finally, we get the fourth and last row of the product by multiplying the fourth row of A by each column of B in turn, and that works out to -3, -5, -3. And we have our matrix product. Please pause the video and calculate for yourself the product y times z and then the product z times y. Notice that in this case, we can do the product in either order, since each of these is a 2 by 2 matrix. So their inner dimensions agree no matter which order you do the product in. So when calculating y times z, we're going to get the matrices multiplied in this order. And the result should be 44, 28, 11, and 31. The 44 comes from multiplying the first row of y with the first column of z. 1 times -1 plus 5 times 9, that's -1 plus 45, or 44. Multiplying the first row by the second column gives us the 28, the second row by the first column gives us 11, and the second row by the second column, 7 times 3 plus 2 times 5 is 31. Let's see what happens when we multiply in the opposite order, z times y. This time we get 21, 44, and 55, a completely different matrix. Even the one number in common is just a coincidence. This example shows us that multiplication of matrices is not commutative. Y times z is not necessarily equal to z times y. In a future video, we'll look at properties of matrix multiplication more thoroughly and figure out what properties do hold. In this video, we defined matrix multiplication by multiplying rows times columns. And we noted that matrix multiplication is not, in general, commutative. In this video, we'll talk about properties of matrix multiplication and compare them to properties of multiplication for ordinary numbers. I've listed some properties of multiplication that hold for ordinary numbers. Let's see which properties also hold for multiplication of matrices. Multiplication of numbers is associative. That means if I multiply a times b and then multiply that by c, that's the same thing as multiplying a by the product of b and c. It doesn't matter how you group them. It turns out that matrix multiplication is also associative. I'll write capital letters to denote the matrices instead of numbers, but the property is the same. There's also a version of associativity that holds for multiplying matrices and scalars together. If I let lowercase k represent a scalar, that's just a number, then I can do, if I do k times the matrix A, recall that just means multiply every entry of A by the number k, and then do matrix multiplication of that times B, that's the same thing as multiplying A times B first, and then multiplying the result by k. In fact, it's also the same to multiply A by the product of k times B. Although I won't prove these properties here, they can be proven by writing out a formula for matrix multiplication in terms of the entries of the matrices and using some algebra. When we're talking about numbers, multiplication is commutative. A times b is the same as b times a. It doesn't matter the order. However, as we saw in a previous video, matrix multiplication is generally not commutative. A times b is not necessarily equal to b times a. Actually, a lot of times it's not even possible to multiply matrices in both orders. For example, if we have a 4 by 3 matrix and multiply it by a 3 by 2 matrix, that's legit because the inner dimensions 3 and 3 are the same. But if we reverse the order, so instead of a times b, we do b times a, that would end up being a 3 by 2 times a 4 by 3, which doesn't make sense. But even when we can multiply matrices in both order, for example, square matrices, matrices whose number of rows and columns are both the same, can be multiplied in either order. So like if we have a 2 by 2 matrix A and a 2 by 2 matrix B, we can multiply them both ways. But most of the time we won't get the same answer. I'll write down a couple of 2 by 2 matrices just to show you. Multiplying in this direction, so row times column, gives us -1, 1, -2, 3, but multiplying in the other order gives us 1, 1, 2, 1. So multiplication of matrices is not generally commutative. For numbers, multiplication distributes over addition. That is, if we take a times b plus c, That's the same thing as A times B plus A times C. Also, if I multiply B plus C times A, that's the same thing as B times A plus C times A. Well, the same distributive properties hold for matrix multiplication. I won't prove that property here, but it can be proved by focusing on each row and column separately. Finally, for numbers, there's a multiplicative identity. That's the number 1. It's called a multiplicative identity because 1 times any number gives you the same number, and any number times 1 gives you the same number. Is there also a multiplicative identity for matrices? In other words, a matrix I for identity, such that I times any matrix gives you the same matrix, and that matrix times I gives you the same matrix? In fact, there is, as long as we restrict ourselves to square matrices. That is, matrices of dimensions n by n for some number n, the same number of rows and the same number of columns. In fact, there's a whole family of identity matrices, one for each size square matrix, one for each number n. So let's see if we can figure out what this identity matrix needs to look like. So I'm just going to write down some random matrix A, let's say a 3 by 3 matrix. And we're going to try to figure out what this identity matrix I needs to be in order that we get the same matrix A as the result when we do this product. First of all, we know that I needs to also be a 3 by 3 matrix for the dimensions to work out. So thinking about the first row of I, when I multiply the first row of I by the first column of A, I need to get this entry 3. So that first row needs to just pick up the number 3 in this column. If you're thinking that the first row of I should be 1, 0, 0, that's the right idea. Because then when I multiply this row by this column, I'll get 1 times 3 plus 0 times 8 plus 0 times negative 2, which just gives me the first entry 3. Similarly, if I multiply 1, 0, 0 by the second column of A, I'll get 1 times negative 4, 0 times 9, 0 times 5, which picks off the number negative 4. First row times the third column picks off the number 7. Now looking at the second row of numbers, when I take the second row of I and multiply it by the first column, I need to get the number 8. When I multiply it by the second column, I need to pick off the number 9. When I multiply it by the third column, I need to pick off the number 1. Well, I can do that if I make the second row of I be 0, 1, 0. Finally, when I multiply the third row of I by each column of A, I need to pick off these last 3 numbers. I can do that by letting the third row of I be the row 0, 0, 1. So this is what my identity matrix needs to look like, and I can check that if I multiply in the other order, A times I still get back to my original matrix A. And there was nothing special about this particular matrix A. If I'd stuck in any other numbers here, this matrix I would still have done the trick. More generally, the identity matrix for any n by n square matrix will consist of n ones down the diagonal with zeros everywhere else. In this video, we noticed that matrix multiplication is associative. It is not commutative. It is distributive. And there's a multiplication identity, I. In a previous video, we worked out the mechanics of matrix multiplication. This video focuses on interpretations of matrix multiplication, particularly in terms of the columns of matrices. Recall the mechanics of matrix multiplication. If we multiply A times B to get C, then to get this top left entry of the answer matrix, C, we take the top row of A and multiply it by the left row of B one element at a time. 2 times 1 plus 3 times 2 plus 1 times 3 gives us 11. To get the entry in the first row's second column, we do the first row of A times the second column of B. And in general, we saw the ij entry of A times B. By that I mean the entry of A times B in row I and column J. We get this by taking the product of row I in matrix A and column J in matrix B. Recall that to take the product of a row vector and a column vector, we multiply the corresponding entries and add them up. Sometimes this is called a dot product. But instead of thinking of this matrix product element by element, I want to think of it column by column. What does the first column of this answer matrix C represent? In fact, this column, 11, 15, comes from multiplying the matrix A by the first column of B. That makes sense if you think about where each of these entries of the first column of C comes from. The top entry comes from the top row of A times the first column of B. The next entry comes from the next row of A times the first column of B. All the entries of the first column of C come from multiplying rows of A by the first column of B in order. So that's just the same thing as multiplying the matrix A by the first column of B. And similarly, to get the second column of C, we can multiply the whole matrix A by the second column of B. So in general, when we multiply two matrices A times B, then the jth column of A times B tells us the product of A with the jth column of B. One way to write this is if you have A times a bunch of column vectors, I'll call them x1, x2, say x3, x4, in case we have 4 column vectors in B, then this is the same thing as just multiplying A times each column vector and sticking them together into a matrix. Let's apply this column interpretation in an example. Suppose we know that we have a matrix here, I'll call it A, and we know that A times this column vector gives us this column vector. Notice the dimensions work out fine, and the arithmetic works out fine. And I've also pre-calculated that A times this other column vector is this column vector, and A times this third column vector gives us this column vector. So now, if we want to multiply the same matrix A times the matrix we get by sticking those little 2 by 1 column vectors all together into a 2 by 3 matrix, that's just the same thing as doing A times 2, 1 as the first column, A times 1, 1 as the second column, A times 0, 3 as the third column. And so it's just the same thing as concatenating all those column answers, like this. Before I look at the third interpretation of matrix multiplication, I want to define a linear combination of vectors. A linear combination of vectors is just a sum of scalar multiples of the vectors. So for example, if this is our vector v1, v2, and v3, here we've written down a linear combination, 3 times v1 plus 4 times v2 plus negative 2 times v3. These scalars 3, 4, negative 2 are called the coefficients in the linear combination. So there's a third interpretation of matrix multiplication, A times B equals C, that focuses on the columns of A as well as the columns of C. So this interpretation says that the jth column of A times B tells us the linear combination of the columns of A with coefficients given by the entries in the jth column of B. Let me show you what I mean. So to get, say, the first column of C, we're going to use the entries in the first column of B to tell us that we want 1 times the first column of A plus 2 times the second column of A plus 3 times the third column of A. That's 1 times 2 negative 4 plus 2 times 3 2 plus 3 times 1 5. And you can check that that adds up to the first column of C, 11 15, right? Because 1 times 2 plus 2 times 3 plus 3 times 1, that's 2 plus 6 plus 3, which is 11. 1 times negative 4 plus 2 times 2 plus 3 times 5, that's negative 4 plus 4 plus 15, which is 15. Similarly, to get the second column vector of C, we can use these numbers in B to tell us that we need the linear combination negative 2 times the first column of A plus 5 times the second column of A plus 1 times the third column of A. You can verify that really does give us this column of C. It makes sense that this works because we saw before that each column of C just comes from multiplying A times the corresponding column of B. And when we multiply a matrix A by the column, then we're doing a bunch of dot products, right? Dot product of this with this, and then the dot product of this with this. But each dot product is just the same thing as taking a linear combination of entries of A, where the coefficients of linear combination are given by the column of B. So we're taking a linear combination of these three numbers, sticking it in the first entry, a linear combination of these three numbers, sticking it in the second entry. That's just doing a linear combination of each column and sticking it in the column. If we want to write this out in notation, then if we write the columns of A as, say, V1, V2, V3, I'll just use the same matrix B, then the columns of C will be 1 times V1 plus 2 times V2 plus 3 times V3 for the first column, and negative 2 V1 plus 5 V2 plus 1 times V3 for the second column. Let's do an example in which it's useful to think of the matrix product A times B equals C in terms of linear combinations of columns of A. So let me copy down my matrix A, and I'm going to call its column vectors V1 and V2. I need to multiply it by a matrix B, and my answer matrix is going to have in its first column 2 times V1 plus 3 V2. That's because my first instructions say that the first column of A times B will be twice, or 2 times, the first column of A plus 3 times the second column of A. In its second column, negative 3 times the first column plus 4 times the second column, that's going to be negative 3 V1 plus 4 V2. The third column will be V1 plus V2, and the fourth column, 5 times the second column, that's just going to be 5 V2. Well, we know that we can think of matrix multiplication as each column of B giving us instructions for linear combinations of the columns of A. And so the first column of B has to be instructions, take twice V1 plus 3 times V2. That means we need an entry of 2 here, an entry of 3 here. Since the next column of C is supposed to be negative 3 times the first column of A plus 4 times the second column of A, our instructions in B are negative 3, 4. Similarly, the third column of B needs to be 1, 1. And the fourth column of B needs to be 0, 5. In this video, we talked about 3 interpretations of matrix multiplication. The first interpretation is that the entry, the ij entry of the product A times B is the ith row of A times the jth column of B. The second interpretation of matrix multiplication says that we can think about the columns of the answer as being A times the columns of B. So the jth column of A times B is A times the jth column of B. Finally, the third interpretation says that the jth column of A times B is a linear combination of the columns of A with coefficients given by the jth column of B. There are other interpretations of matrix multiplication as well, but these three will give us the tools we need for now. This video gives an introduction to vectors and basic operations on them. A vector can be defined as a list of numbers. If the numbers are written vertically, then the vector is called a column vector. If they're written horizontally, then it's called a row vector. We'll be working with column vectors for the rest of this video. I'll use square brackets to surround the numbers in my vector, but you may see other notation elsewhere, such as angle brackets. When I assign a variable name to a vector, I'll put a little arrow above it to signify a vector, but you may see other notation elsewhere, such as boldface or a little hat. The components of a vector are the numbers or entries in the list, and the dimension of the vector is the number of entries. So here, my vector has dimension 4 because it has 4 components. The first component is 3, the second is -1, the third component is 7, and the fourth component is 2.6. For the rest of this video, I'll be working with vectors of dimension 2 for simplicity. But everything I talk about does generalize to vectors of higher dimensions. We add two vectors by adding their corresponding components. So to add these two vectors, we add 3 plus 1 to get 4 as the first component, and 7 plus -5 to get 2 for the second component. We subtract them by subtracting their components. So here I do 3 minus 1, which is 2 for the first component, and 7 minus -5, so that's 7 plus 5, which is 12 for the second component. A scalar is another word for a number, and we can multiply a scalar by a vector by just multiplying each component of the vector by that number. So here, in this example, if we want to multiply 5 by the vector with components 3 and 7, we just multiply 5 times 3 and 5 times 7 to get 1535. The negative of a vector is formed by multiplying the vector by -1. So here, the negative of this vector with components 1 and -5 will just be -1, 5. So say we have the vector v with components 3 and 7. What's negative v plus v? Well, negative v is going to be -3, -7. When we add that to 3, 7, we just get a vector whose components are all zeros. This is called the zero vector, and it's sometimes written as 0 with an arrow over it to signify that it's a vector with components that are 0 and distinguish it from just a scalar 0. In fact, for any vector v, -v plus v will give us the 0 vector. We can visualize a vector with two components, v1 and v2, by drawing an arrow that extends v1 units horizontally and v2 units vertically. So for example, if I want to draw this vector v with components 2 and -3, I need an arrow that goes over 2 units horizontally and down 3 units vertically. The tail end of the arrow is called its initial point, and the arrow end of the arrow is called its terminal point. It's often convenient to put the initial point of the arrow at the origin. So then going over 2 horizontally and down 3 vertically would give me this arrow to represent v. but it's perfectly fine to start the arrow anywhere else. So for example, I could put the initial point here, go over 2, down 3, and get this arrow to represent V. Since it doesn't matter where we put the initial point, only how far over and down we go, we say that a vector has a length and a direction, but not a position. Any two arrows that can be dragged over to lie on top of each other represent the same vector. So which of these three arrows represents the same vector? The first one and the third one do. They both represent the vector with components 2, 1. But the middle vector has components -2, -1. So the middle vector is actually the negative of the other vectors. We've already talked about adding vectors together component by component, but let's see what a vector addition looks like when we draw arrows. First, I'll draw vector A in blue over 4 and up 1, and I'll draw vector B in red over 2 and up 3. Now, to get the vector A plus B, I have to go over horizontally 4 plus 2 units and up vertically 1 plus 3 units. So if I start at the origin where A starts, then my terminal point would be all the way over here at 6, 4. This is exactly the same place I'd get to if I translate over my vector B so that its tail is at A's tip, and then draw an arrow from the tail end of A all the way to the tip of B. And in general, to draw the sum of two vectors A plus B, we move the vector B over so its tail is at A's tip, and draw a line connecting the tail of A to the tip of B. It makes sense that this is the same thing as adding component-wise, because if the vector A has components A1 and A2, and the vector B has components B1 and B2, then the arrow that I've drawn in green is going to extend horizontally by A1 plus B1 and vertically by A2 plus B2. An alternative, an equivalent way of drawing vector addition with arrows is to put the two vectors with their tails together and form a parallelogram and now the vector sum is the diagonal of that parallelogram. Next, let's represent scalar multiplication with arrows. Let me draw my vector B for starters. Then the scalar multiple 2b is what I get by multiplying each of its components by a factor of 2. So that vector is going to go twice as far horizontally and twice as far vertically. In other words, 2b will point in the same direction but be twice as long. The vector -b will have components -2, -3. So it will have the same length as b, but point in the opposite direction. And in general, to draw a scalar multiple times a vector, say k times v, if k is positive, we draw an arrow k times as long as v in the direction of v, and if k is less than 0, we draw an arrow, the absolute value of k times as long as v in the opposite direction as v. Finally, let's represent vector subtraction with arrows. Let me draw my vector A and my vector B. Now A minus B is the same thing as A plus -b. So let me draw -b on here. That's just b going in the opposite direction. So here's -b. And now I want to do A plus -b. Well, that's the same thing as -b plus A. Now, to do negative b plus a, I just have to put them tail to tip. Well, hey, they're already tail to tip. And then I draw the line from the tail of negative b to the tip of a. This line right here is my a minus b. One way to check this is to look at what happens if we add b plus a minus b. Well, geometrically, that means we get this vector right here, which is a, and that makes sense. B plus a minus b should equal a. So in general, to draw the difference of two vectors, a minus b, one way is to just add a plus minus b, but as a shortcut, we could put the two vectors tail to tail and then draw a vector from the tip of b to the tip of a. Our last topic for this video is the length of vectors. What's the length of the vector with components 4 and 1? Well, since it goes over horizontally by 4 and up vertically by 1, and this figure forms a right triangle, I can use the Pythagorean theorem to find the length of the arrow, which is the hypotenuse of my right triangle. Pythagorean theorem says a squared plus b squared equals c squared. And so c, the length of the hypotenuse, is the square root of a squared plus b squared, or in this case, the square root of 4 squared plus 1 squared, which is the square root of 17. And in general, to find the length of a vector w with components w1 and w2, this length, written with absolute value signs or sometimes double absolute value signs, is given by the square root of w1 squared plus w2 squared. In this video, we represented vectors with columns of numbers and with arrows. We defined vector addition by adding together components and by sticking the arrows tail to tip. And we figured out the length of vectors using the Pythagorean theorem. Although we worked exclusively with two-dimensional vectors, vectors with two components that we could draw on the plane, everything we talked about generalizes to vectors of 3 dimensions or higher dimensions. In particular, if we wanted the length of a vector with, say, 3 components, we would use the generalized version of the Pythagorean theorem, add up all 3 of its components squared, and take the square root of that. This video is about solving equations of the form a times x equals b, where a is a matrix, b is a vector, and x is a vector that we're trying to solve for. We'll spend a bit of time focusing on equations of the form ax equals 0, where this is the 0 vector. Equations of this form, where we have all zeros on the right-hand side, these are called homogeneous equations. Let's start with this example. We're trying to solve the equation a times x equals b for x, where a is this 3 by 3 matrix and b is this length 3 column vector. To make the dimensions work out, I'm going to need my vector x to be a 3-dimensional column vector also. That way, when I multiply a times x to get b, I'll be multiplying a 3 by 3 matrix by a 3 by 1 column vector to get a 3 by 1 column vector as I want to. But this vector x is completely unknown. It's what I'm trying to solve for. Since it has 3 components, I'm going to use 3 variables, x1, x2, x3, to refer to those components, and I'm trying to solve for those components, x1, x2, x3. Now, if I work out the matrix multiplication, the left side of this equation becomes the matrix 1 times x1 plus 2 times x2 minus 2 times x3 in the first row, 3x1 plus 4x2 minus 5x3 in the second row, and 0x1 plus 1x2 plus 1x3 in the third row. So this left side is actually now just a column vector, right? There's just one entry in each row, and it has to equal this other column vector, 1, 7, negative 2. So that's just the same thing as this system of linear equations. x1 plus 2x2 minus 2x3 equals 1. 3x1 plus 4x2 minus 5x3 equals 7. And 0x1 plus 1x2 plus 1x3 equals negative 2. Well, we've seen how to solve systems of linear equations like this before. One way is to write it out as a matrix. 1, 2, negative 2, 1, we're writing out as an augmented matrix where the constants go in the last column of the matrix. Second row of the matrix will be 3, 4, negative 5, 7, and the third row will be 0, 1, 1, negative 2. What we'll do is we'll convert this to a reduced row echelon form, and then we'll be able to read out the solution. Notice that the matrix we're converting is simply the matrix A augmented with the column B. I'll skip the details of converting this to reduced row echelon form, but the final answer looks like this. So we can read off a solution that x1 is 5, x2 is negative 2, and x3 is 0. In other words, there's a unique vector x that satisfies this vector equation, and that vector x has components 5, negative 2, 0. I'd like to briefly look at a related problem, where instead of solving the equation a times x equals b, we solve the homogeneous equation a times x equals 0. Here, the 0 vector needs to be a 3 by 1 column vector. By the same reasoning as before, this amounts to taking the augmented matrix, this time augmented with a column of zeros, and converting it to reduced row echelon form. You can check that when we do this conversion, we get this matrix. Therefore, our related vector equation with a 0 instead of a b has a unique solution where x1 is 0, x2 is 0, and x3 is 0. In other words, the solution is the 0 vector. In fact, I could have predicted in advance that the 0 vector would be a solution to this equation with all zeros on the right side, because if I multiply any matrix by all zeros, I'm going to get zeros. What I didn't know in advance is that this 0 vector is the only solution. That's what working out the reduced row echelon form told me. Let's look at another vector equation. Once again, we're thinking of the vector x as our variable, and once again, it has to be a 3 by 1 vector with 3 components that I'll call x1, x2, x3. It has to have these dimensions to make the dimensions of the matrix multiplication work out. This vector equation is the same thing as this system of linear equations, and solving the system is the same problem as converting the augmented matrix to reduced row echelon form, where the augmented matrix I can get just by putting A together with the column vector B. Once again, I'll omit the details of converting the matrix to reduced row echelon form and just write out the final answer. In this case, our system of linear equations has infinitely many solutions. I can tell that because I have this column that's not my augmented constant column that doesn't have a leading 1 in it. So this variable x3 is a free variable, and I can write my other variables x1 and x2 in terms of x3 because x1 minus x3 is minus 18 and x2 plus x3 is 13. That comes from these first 2 rows, and therefore I have that x1 is x3 minus 18 and x2 is minus x3 plus 13. So my vector solutions are of the form x3 minus 18 minus x3 plus 13 x3, where x3 can be anything. I can also write this as a sum of 2 vectors. One vector that's multiplied by x3, so that'll be x3 times 1 minus 1, 1, plus a vector that just has constants in it, minus 18, 13, 0. Let me once again consider the related homogeneous equation, ax equals 0. Solving this vector equation can be accomplished by converting the associated augmented matrix, augmented with the 0 column vector, converting this augmented matrix to reduced row echelon form. When I do that, I get this matrix. The same matrix I had before, just with zeros in the far right column. So the solutions to my a times x equals 0 equation are given by x1 minus x3 equals 0, x2 plus x3 equals 0, and no conditions on x3. In other words, x1 equals x3, and x2 is negative x3. That's the same thing as saying that the vector x, which originally is x1, x2, x3, is of the form x1 is equal to x3, x2 is negative x3, and x3, a free variable, is just itself. So x can be thought of as x3, which can be anything, times the vector 1, negative 1, 1. Notice the similarities between my families of solutions for my two related equations. The family of solutions for my equation a times x equals b is this particular solution, negative 18, 13, 0, plus this expression here, which represents the solutions to my associated homogeneous equation ax equals 0. Another way to say this is that my solutions to the equation ax equals b are of the form x equals x3 times v plus w, where w is the vector minus 18, 13, 0, a particular solution to the equation ax equals b, and v is the vector 1, negative 1, 1, so that x3v is a general solution to the related equation ax equals 0. Solutions to ax equals b can be written as a particular solution plus the general solution to the related homogeneous equation ax equals 0. Let's recap where we've been. In our first example, our homogeneous equation just had one solution, the 0 vector. Our equation ax equals b also had one solution, the vector 5, negative 2, 0. In our second example, our homogeneous equation had infinitely many solutions of the form x3 times 1, negative 1, 1, and our original equation ax equals b also had infinitely many solutions of the form negative 18, 13, 0, plus x3 times 1, negative 1, 1. These two situations are typical. In fact, if the equation ax equals b has any solutions, in other words, if it's a consistent system of equations, then ax equals b has one unique solution if and only if the associated homogeneous equation ax equals 0 has one unique solution, namely the 0 vector, and ax equals b has infinitely many solutions if and only if ax equals 0 has infinitely many solutions also. Although I don't have time to demonstrate it in this video, I do want to emphasize that this correspondence only holds if the equation ax equals b is consistent, it actually has any solutions. If this equation ax equals b is inconsistent, no solutions, then anything goes. Well, almost anything. The equation ax equals 0 will always have at least one solution, the 0 vector. But it could have one solution or infinitely many solutions, and this equation ax equals b still have no solutions. In this video, we solved equations of the form ax equals b by writing down the augmented matrix with A and augmented by B, and then converting it to reduced row echelon form. We also noted that the solutions of ax equals b are related to the solutions of the homogeneous equation ax equals 0, at least as long as the equation ax equals b has solutions. Specifically, if ax equals b has solutions, then ax equals b has one solution if and only if ax equals 0 has one solution. And ax equals b has infinitely many solutions if and only if ax equals 0 has infinitely many solutions. In this video, we'll solve equations of the form a times x equals b, where a and b are known matrices and x is an unknown matrix. So we're trying to solve for the entries of x that will make this equation hold. In this video, we'll focus exclusively on the situation where A is a square matrix, the same number of rows and columns, although x and b might not be square matrices. But a lot of the ideas will pertain to situations where A is not a square matrix. Let's start with this example. A is a 2 by 2 matrix, and B is a 2 by 3 matrix. So if I want to multiply A times x and get B, what dimension will x have to be? In order for the matrix multiplication even to make sense, x is going to have 2 rows to match the 2 columns here of A. And in order to get the right number of columns in the output of B, x is going to have 3 columns. I'm going to call the columns of x, x1, x2, and x3, with that arrow to denote that they're column vectors. So we're looking for those column vectors so that A times x1, x2, x3 is equal to B. In a previous video on interpreting matrix multiplication, we saw that when we multiply a matrix by another matrix, we can accomplish that by multiplying the first matrix times each column of the second matrix separately and then just concatenating them together. So this expression, A times the matrix with columns x1, x2, x3, is the same thing as a result matrix with columns ax1, ax2, ax3. And that has to equal B, which has columns 1, -1, 4, 2, 1, 1. So we know that we need ax1 to be the column matrix 1, -1, ax2 to be the column matrix 4, 2, and ax3 to be the column matrix 1, 1. Hang on a sec. We've seen how to solve these problems. This is solving a vector equation, right? A matrix times a vector is another vector. So all we have to do to solve this first problem is to augment A with this column vector 1, -1 and put it in row reduced echelon form to read off our solution. Here's my augmented A, and to put that in reduced row echelon form, I can first leave the first row alone. It's already got a 1 in the upper left position, and I can get rid of this 2 by replacing the second row with -2 times the first row plus the second row. Then I can divide the second row by -4. Finally, get rid of this 3 by replacing the first row with the first row minus 3 times the second row. Now I can read off the solution vector. x1 is going to be the column vector -5/4, 3/4. Continuing, I need to solve A times x2 is a column vector 4, 2. So I'll write down the augmented matrix and start to do the row reduction. Wait, this is starting to seem familiar. I seem to be going through exactly the same steps as I did before. And that makes sense because when I'm doing the steps of row reduction, I'm really focusing on this part of the matrix, trying to get this part of the matrix to have leading ones with zeros above and below them. This last column just gets dragged along for the ride. So I do get a different answer for my x2 column vector. It's going to be -1/2, 3/2, but the process I used to get there is the same as what I used for the first column vector. And if I move my attention to solving this third vector equation, I'll go through the same row reduction steps once again. So I have my solution, the matrix x1, x2, x3, otherwise known as X, is going to be equal to my three answer vectors strung together. So that's -5/4, 3/4, -1/2, 3/2, and 1/4, 1/4. But I also have an idea for how to do this process more efficiently. Instead of doing this row reduction process 3 times for the 3 separate vectors, what if I just string those vectors together and do the row reduction process once? So I'm going to augment A with all 3 of the column vectors of B. And I'll start applying the row reduction operations in one fell swoop. The first thing we did was to get rid of that 2 in the bottom left corner by replacing the second row with -2 times the first row plus the second row. When I do this, I maintain all the information that I had in the blue, green, and purple computations. These first 2 columns that corresponded to the original columns of A and are the same in the 3 computations are the same here. And then these last 3 columns are the same as those columns that I did in those 3 computations before. I can also do the next step of the row reduction in one fell swoop. And the last step altogether. When I solve the matrix equation in this most efficient way, I can read off my answer matrix X from the rightmost chunk of my row-reduced matrix. Please pause the video and try your hand solving this matrix equation. I'm going to start by writing down the augmented matrix, A with B after it. I'll write down the steps of row reduction and leave it to you to verify the details. After doing that row reduction work, by hand or by computer, we can read off our solution matrix X. I encourage you to check the work by actually multiplying A times X and verifying that you do get matrix B. I want to point out that the reason we could read off our answer matrix so easily is that after we did the row reduction, the part of our matrix corresponding to A is in a particularly nice form. It looks like an identity matrix with a leading 1 in each column and no rows that are all zeros. If we had gotten, for example, a row of zeros down here and some columns that didn't have leading 1s in them, then we would have had to be more careful, and we might have ended up with no solution or infinitely many solutions. We'll talk more about those situations in class or in a later video. In this video, we saw that solving the matrix equation, A times X equals B, was equivalent to solving a bunch of vector equations, where the unknown vectors x1 through xn form the columns of the unknown matrix X, and the vectors b1 through bn form the columns of the known matrix B. But rather than solving each of these equations one by one, we saw that it was much more efficient to just augment the matrix A with the matrix B and convert that to reduced row echelon form. When we solve equations with numbers, like the equation 3 times x equals 4, we divide both sides by 3, or equivalently, we multiply both sides by 1/3. The number 1/3 is called the multiplicative inverse of 3. It's also written as 3 to the minus 1. When we multiply 3 inverse by 3, we get 1, which is why it's so useful for solving equations like this one. If we can find a multiplicative inverse for a matrix, that could give us a good way to solve matrix equations, like A times X equals B, where A, X, and B are matrices, A and B matrices that we know the entries of, and X a matrix we want to find. Recall the matrix I, called the identity matrix, that has 1s down the diagonal and 0s in all its other places. The identity matrix is a square matrix, and there's actually 1 for each dimension, n. So for example, I3 is a 3 by 3 matrix that has 3 1s down the diagonal and 0 as all its other entries. The matrix I plays the role of the number 1 for matrix multiplication. Just like 1 times any number just gives you the same number itself, if you multiply I by any matrix, you just get the matrix you started with. And it works if you multiply in the other direction too. So by analogy to numbers, the inverse for a matrix A would be a matrix A inverse that multiplies by A to give the identity. It turns out that such a matrix doesn't always exist for every matrix A, but when it does, it's super useful. Let's start with the definition of an inverse matrix. Suppose that A is an n by n square matrix and B is another n by n matrix, so that when you multiply A and B together, in either order, you get the identity matrix. Then A is called invertible, and B is called the inverse of A. And it can be denoted A to the negative 1. We're focusing our attention on matrix A in this definition, but in this situation, B is also called invertible, and A is going to be the inverse of B. We'll only talk about inverses for square matrices, and in fact, it turns out that it's not possible for pairs of matrices to satisfy both these two conditions if they're not square. You might be wondering, is it possible to have A times B be the identity matrix, but not B times A? We've certainly seen that in some cases the product A times B is not the same as the product B times A. Matrix multiplication is not, in general, commutative. But it turns out, although I won't prove it here, that if A and B are square matrices, such that A times B is the identity, then B times A will also necessarily have to be the identity. So the answer, is it possible to have the product one way be the identity but not the other way? The answer is no, this is not possible. You might also wonder, is it possible to have two different matrices B and C that are both inverses for A? In other words, could we have A times B equals I, and B times A equals I, and also have A times C equals I, and C times A equals I? Well, suppose I were in this situation, and I took the equation A times B equals I, and I multiplied on the left by C. Since C times A is the identity, this is the identity right here, so this equation can be rewritten as I times B equals C times I, but the identity times B is just B, and C times the identity is just C, so in fact, B would have to equal C. So the answer is no. It's not possible to have two different matrices B and C that are both inverses for A. They would end up having to be the same thing. Another question that comes to mind is, does every square matrix have an inverse? The answer to this question is also no. For example, let's consider the 2 by 2 square matrix 1, 2, 2, 4. Suppose we found a matrix, I'll write its entries as A, B, C, D, so that when we multiplied together, we got the identity matrix. If I work out the matrix multiplication, I get these entries on the left having to equal the identity matrix on the right. But that means I need A plus 2C to equal 1 and 2A plus 4C to equal 0 if I take twice the first equation and subtract the second equation. I get 0 equals 2, which is a contradiction. So there are no values of A, B, C, and D that would work. There's no inverse to this matrix. If we want to find an inverse matrix for a matrix like this one, that's the same as finding a matrix X such that A times X is the identity matrix. In this case, a 3 by 3 identity matrix. That's all we have to do, because we've seen that if the multiplication this way is the identity, then the multiplication in the other direction, X times A, has to also equal the identity. But we've seen how to solve matrix equations like this before. We can do that by writing down the matrix A and augmenting it with the matrix on the right side of the equation, in this case, the identity matrix. If we're able to convert this matrix to reduced row echelon form, and it works out that the chunk in this part of the augmented matrix turns into the identity matrix, then we'll be able to read off the solution for X in this chunk of the matrix. So let's do some row reducing. I'll swap the first two rows, use the first row to get rid of the 4 in the third row, get rid of the -3 in this position, and continue. Notice that our row reduced matrix has the identity matrix as a block where the original matrix A used to be. Therefore, we have a solution X that we can read off from the rightmost block of our row reduced matrix. That solution is the inverse of A. And we can check our work by multiplying this matrix by A in either direction and verifying that we get the identity matrix. I want to mention that if we had not gotten the identity matrix as our left-hand chunk after doing row reducing, if we had, for example, gotten a row of zeros here, then there would not exist an inverse to our matrix A. Now that we've found the inverse matrix for A, notice that this matrix A is the same matrix as was on this previous slide. Now that we've found its inverse, we have an easy way to solve the equation A times X equals B. All we have to do is multiply both sides of that equation on the left by A inverse. A inverse times A is the identity matrix, and the identity matrix times the matrix X just gives X. So the unknown matrix X will be given by A inverse times B. I'll copy A inverse from the previous page and multiply it by the matrix B. After some arithmetic, this works out to the following 3 by 2 matrix. In this video, we define the inverse of a square matrix as the matrix that you multiply it by to get the identity matrix. We also computed the inverse of a matrix by sticking the matrix and the identity matrix together and converting this to reduced row echelon form. Finally, once we had the inverse of a matrix A, we used it to solve an equation of the form AX equals B by multiplying both sides by A inverse. In this video, we'll compute the inverse of a 2 by 2 matrix two different ways. First, by using row reduction, and second, using a shortcut formula. As we saw in a previous video, one way to compute the inverse for a matrix is to augment that matrix with the identity matrix, and then convert it to reduced row echelon form. I'm going to do my row reduction by first multiplying the first row by 1/3, then getting rid of this 5, then multiplying the bottom row by -3/2, and finally getting rid of this 4/3. Since we were able to obtain the identity matrix as our left chunk after row reduction, the inverse matrix A inverse exists and lies in the right chunk. This is our inverse matrix. Next, I'm going to give you a shortcut formula for finding the inverse of a 2 by 2 matrix that'll get you the same answer with a little less work. In general, if your 2 by 2 matrix has entries, I'll call them little a, little b, little c, little d, then A inverse will be given by the matrix D negative B negative C A multiplied by the scalar 1 over AD minus BC. To help remember this formula, notice that the entries in this diagonal have been swapped. The entries in that diagonal have stayed the same but gotten negative signs in front of them. And the whole thing is multiplied by 1 over this crisscross product, AD minus BC. This crisscross product is also known as the determinant of the 2 by 2 matrix. Now, you might be wondering, what if AD minus BC is 0? Because then we'd be dividing by 0, and that seems like a bad idea. Well, that's a very good thing to point out. And in fact, I should be a little more precise and say that if AD minus BC is not equal to 0, then A inverse exists and equals this matrix here. But if, on the other hand, AD minus BC is equal to 0, then it turns out that A inverse does not exist. So let's see why this formula works. We could derive this formula by writing our abstract matrix A, augmenting it with the identity matrix, and doing row reduction. But it'll be a little simpler just to check that it works by multiplying our supposed inverse matrix by our abstract original matrix and making sure that we do in fact get the identity. Carry down my scalar here, and then I'm going to multiply this row by this column to get AD minus BC, this row by that column to get BD minus BD, that row by this column to get minus AC plus AC, and that row by that column to get minus BC plus AD. We can see that this corner is just 0, that corner entry is 0, and when we divide these two entries by AD minus BC, we get 1s, just like we want, the identity matrix. So this matrix must indeed be the inverse of A. So let's go back to our original problem, finding the inverse for this 2 by 2 matrix. We know the inverse should be what we get when we switch the numbers on this diagonal and negate the numbers on this diagonal and multiply the whole thing by 1 over 3 times 6 minus 4 times 5. So A inverse is 1 over negative 2 times the matrix. And if I bring in the 1 over the negative 1/2, that gives me negative 3, 2, 5/2, and negative 3/2. That's exactly what we got when we solved this problem before. This video gave us a handy shortcut formula for finding the inverse of a 2 by 2 matrix. This video gives a bunch of different ways of saying that a matrix is invertible. Let A be an n by n matrix. Recall that we say that A is invertible. By definition, that means that there exists an n by n matrix, call it X, such that A times X is the identity matrix and X times A is the identity matrix. That's the definition of A being invertible, but there are 5 other properties that are equivalent to this. In other words, if any one of these properties holds about matrix A, then all the rest of them hold also. And if any one of these properties fails to hold for A, then all the rest of them also fail to hold. I'll talk through these properties, but for a rigorous proof of why they're all equivalent, you'll need to look in another video. Statement 2 says that there exists a matrix B such that B times A is I. So certainly if A is invertible, that's true, right? Because if A is invertible, there's a matrix that we can multiply on the left or the right and get I. And here we just need to multiply on the left to get I. But it turns out that having B times A equals I for square matrices also implies that A times B has to equal I. And so if statement 2 is true, then statement 1 is also true. Similarly, it turns out that if A times C is I, then C times A is I. So if statement 3 is true, then statement 1 is also true. And of course, going the other direction, if 1 is true, if A is invertible, then there certainly exists a matrix C that's a right inverse. So statements 2 and 3 are both equivalent to statement 1. Now let's look at statement 4 and see what that has to do with statement 1. Suppose that A is invertible. Then there's a matrix X that solves the matrix equation A times X equals I. And solving this matrix equation is equivalent to taking the matrix A augmented by I and converting it to reduced row echelon form. When we do this, we're really just solving systems of linear equations, one system for each column of I. Well, since we know there's a solution, when we do the reduced row echelon form, we know we're going to have to get an I where A used to be, and then some other stuff where the I used to be. If we didn't get an identity matrix on the left-hand chunk, if we got something else with a row of zeros and some columns that didn't have leading ones in them, then we wouldn't have a unique solution here. We would either have no solution or infinitely many solutions, neither of which is possible if A is invertible. So therefore, A being invertible means that the reduced row echelon form of A has to be the identity matrix. And to go the other way, if the reduced row echelon form of A is the identity matrix, then that means that we can solve A times X equals I. We can just read off the solution from the right side after we do the reduced row echelon form. And so therefore, we're in a situation of 3, which we said was equivalent to situation of 1. Now, what about this fifth statement, that the vector equation AX equals B has exactly one solution for every n by 1 vector B? Well, if A is invertible, then to solve the equation AX equals B, we just multiply both sides on the left by A inverse, and we get that X is A inverse B. So there's definitely just one unique solution. On the other hand, going the other direction, if AX equals B always has a unique solution, then when we row reduce any matrix like this, then we end up having A in identity form. And we've seen from previous work that that's 4, that implies 1. So A being invertible is also equivalent to statement 5. Finally, let's consider statement 6. Statement 6 says the equation A times X equals 0 has exactly one solution. That solution is necessarily going to be the 0 vector, since any matrix times the 0 vector is a 0 vector. Well, the argument that this is equivalent to A being invertible is pretty much like the last one. If A is invertible, then the equation AX equals the 0 vector can be solved by multiplying by A inverse, which gives us a unique solution. And if AX equals 0 has a unique solution, then a similar argument says that A has to be row reduced to the form of an identity matrix, and therefore A is invertible. So all of these conditions are equivalent. We've seen that if A is invertible, then AX equals B has a unique solution for any vector B. But what about if A is not invertible? What can we say about the number of solutions to the equation ax equals b in that case? Well, we know for sure that this equation does not have one unique solution. Since if it did, the same sort of argument we used before would say that A would row reduce to the identity matrix and A would be invertible. So this equation cannot have one unique solution, so it must have either no solutions or infinitely many. That's because there are only these three possible options: one unique solution, no solutions, or infinitely many solutions whenever we have a system of linear equations, as this vector equation represents. In this video, we saw a bunch of different but equivalent ways of saying that a matrix is invertible. A key idea was that invertible matrices row reduce to look like the identity matrix. This video gives some properties of matrix inverses. Suppose that A and B are invertible matrices. I've written down 4 different properties here, and for each of these properties, see if you can figure out if it's necessarily true, no matter what invertible matrices A and B are. You may want to try some examples. Like you could pick a couple simple 2x2 invertible matrices and test these out. Let's start with statement 1. Is it true that the inverse of A inverse is A? Well, yeah, that's definitely true, because A inverse inverse is the matrix you multiply by A inverse to get the identity matrix, but A is also the matrix that you multiply by A inverse to get I, and since inverses are unique, A must equal A inverse inverse. What about this second statement? Is it true that if you multiply 2 matrices together and take the inverse of that, you get the same thing as if you take A inverse and multiply by B inverse? Let's try it out on an example. I'm going to set A equal to the matrix 1, 3, 2, 7, and B equal to the matrix 2, 3, -1, -1. Then you can check that AB is the matrix -1, 0, -3, -1, and AB inverse is the matrix -1, 0, 3, -1. Remember, there's a shortcut formula that makes it easy to calculate the inverse of a 2x2 matrix. We just swap the entries in these two positions, which doesn't do anything in this case because the entries are the same, and we negate the entries in these two positions, and then we multiply the whole thing by the scalar that's 1 over the determinant, which is just this crisscross product, this times this minus this times this. And in this case, that determinant is just 1. So now let's calculate A inverse. Again, the determinant of this example is 1, and so I can just swap the 7 and 1 and negate the 3 and the 2. That's my A inverse. And B inverse ends up being -1 here, a 2 here, -3 here, and a 1 here. Once again, the determinant is 1. So finally, A inverse B inverse multiplies out to -10, -27, 3, 8, which is not the same as the quantity AB inverse. So this statement is false. We've broken it with our first example. However, there is a related statement that's true. If we do, instead of A inverse B inverse, we calculate B inverse A inverse, that does give us -1, 0, 3, -1, just like when we did AB quantity inverse. So we have at least one example in which AB quantity inverse is the same thing as B inverse A inverse, and in fact, this statement is always true. AB inverse is the matrix that you have to multiply by AB to get the identity matrix. But if you multiply B inverse A inverse by AB, the A inverse A becomes the identity matrix. The IB becomes the matrix B, and the B inverse B collapses to the identity matrix. So since B inverse A inverse times AB is the identity matrix, B inverse A inverse must be the same thing as AB quantity inverse. We're using the fact there that inverses are unique. What about this next statement? Is it true that A plus B inverse is equal to A inverse plus B inverse? Again, we can try it out with an example. Let's use the same matrices, A and B. If we compute A plus B by adding together the entries, we get 3, 6, 1, 6. And if we compute the inverse of that, we end up with a matrix 1/2, -1/2, -1/12, 1/4, which I encourage you to check. If instead we add together A inverse plus B inverse, which we calculated up here, then we get an answer of 6 minus 6 minus 1, 3, which is not the same thing as A plus B inverse. In this case, it wouldn't help to switch the order. B inverse plus A inverse is the same thing as A inverse plus B inverse, since matrix addition is commutative. In fact, there's no relationship between A plus B inverse and the inverse of A and the inverse of B. In fact, it's possible for A and B to both be invertible, but A plus B to not be invertible. Finally, let's look at the last true-false. Is it true that the inverse of 3 times a matrix A is the same thing as 1/3 times the inverse of A? Well, in our example, 3A is the matrix 3, 9, 6, 21. And you can check that 3A inverted is the matrix 7/3, -1, -2/3, 1/3. But that's exactly 1/3 times the A inverse matrix that we calculated earlier. So this statement is true for that particular example of A, but in fact, it's true for any invertible matrix A and any scalar, not just the number 3. So in general, K times A inverse is equal to 1/K A inverse for any invertible matrix A and scalar K that's not 0. Makes sense that this is true, because if you take 1/K A inverse and multiply it by Ka, then pulling out the K, you get 1/K times K times A inverse times A. Well, that's definitely the identity. It's 1 times the identity matrix, or the identity matrix. And since we've multiplied two things together and gotten the identity matrix, the two things have to be the inverse matrices of each other. So 1/K A inverse must be the inverse matrix for K times A. To summarize, if A is invertible, then A inverse is also invertible, and its inverse is A. Also, if A and B are invertible, then A times B is invertible, and its inverse is B inverse times A inverse. And finally, if A is invertible, then K times A is invertible for any non-zero scalar K, and its inverse is 1/K times A inverse. There's one more property of inverse matrices that I want to talk about, and that's the inverse of a diagonal matrix. A diagonal matrix is a square matrix with numbers on the diagonal, which could be 0 or non-zero, and zeros in all the other positions. By the diagonal, I mean the diagonal that runs from the top left corner to the bottom right corner. So which of these two matrices are diagonal matrices? Well, the first one is diagonal, but the second one is not. The first one's diagonal because all the entries that aren't on the diagonal are zeros. It's fine that we have a 0 on the diagonal and some numbers that aren't 0 on the diagonal. The second matrix is not diagonal because even though it has zeros most of the places off the diagonal, it still has a 1 here. So if A is a diagonal matrix with diagonal entries given by the numbers d1, d2, d3 through dn, and none of these diagonal entries are zeros, I'll put big zeros here to indicate that all the other entries are zeros, then A inverse is also a diagonal matrix with diagonal entries 1 over d1, 1 over d2, and so on through 1 over dn. So for example, if we want to find the inverse of this matrix with 5 and 6 on the diagonal and zeros elsewhere, then we can write it down pretty quickly as 1/5, 0, 0, 1/6. It's not hard to convince yourself that this formula for the inverse of a diagonal matrix is true. Just take this matrix and multiply it by your original matrix and check that you get the identity. This video showed us how to find the inverses of matrices from the inverses of related matrices. For example, the inverse of a product is the product of the inverses but in the backwards direction. And the inverse of a scalar multiple of a matrix is the reciprocal of the scalar times the inverse of the matrix. This video is about the transpose of a matrix. The transpose of a matrix A, denoted by A with a little t superscript, is a matrix you get by switching the rows and the columns of A. In other words, the first row of A becomes the first column of A transpose. And the second row of A becomes the second column of A transpose. In this example, notice that we started with a 2 by 3 matrix, but when we took the transpose, we got a 3 by 2 matrix. And in general, if A has size m by n, then A transpose has size n by m. Let's work out some properties of matrix transpose. Let's let A and B be two matrices for which the following operations are defined. So for property 1, we need addition to be defined, so we're going to need A and B to be the same size. And for property B, we need A times B to be defined, so we need the number of columns of A to be the same as the number of rows of B. For property 4, we need A to be a square matrix so that we can take its inverse. Please pause the video and try your hand at figuring out which of these 5 properties holds. You might want to write down some example matrices for A and B and test the property out. I hope you found that the first property is true. If we take two matrices and add them up and then take the transpose, for example, these two matrices, we can think of that as adding them together row by row and then switching the rows to columns. But we'll get the same thing if we first switch the rows to columns and then add them up column by column. What about the next property? Is AB quantity transpose the same as A transpose times B transpose? Well, thinking about dimension, just because A times B makes sense dimension-wise, doesn't guarantee that A transpose times B transpose will even make sense. Here it doesn't, because we can't multiply a 2 by 3 matrix times a 4 by 2 matrix. And even if we stick with square matrices, so dimension's not a problem, it's still easy to come up with examples where AB transpose is not the same thing as A transpose times B transpose. For example, we can take A to be the matrix 2, 3, 1, 7, and B to be the matrix 2, 3, 4, -1. Then AB works out to be the matrix 16, 3, 30, -4, and when we transpose that, we get 16, 30, 3, negative 4. But if, on the other hand, we transpose A first, and also transpose B, and then multiply those transposes together, you can check that we get the matrix 7, 7, 27, 5, which has nothing in common with AB quantity transpose. So this statement, as written, is definitely false. But there actually is a relationship between transpose and multiplication. Like with inverses, if we take the product backwards, so here we do AB transpose, but on the other side we do B transpose first and then A transpose, this does turn out to be true. First of all, we can check that the dimensions will work out. If A is, for example, an M by K matrix, and B is a K by N matrix, so that A times B makes sense, then B transpose will be an N by K matrix, and A transpose will be a K by M matrix. So that multiplication will also make sense, and the resulting matrices on either side will be N by M matrices. On this side we get N by M because when we do the multiplication we get M by N, but then when we take the transpose, that switches that to N by M. But it's not just that the dimensions work out. These two matrices are actually equal for any matrices A and B. Let's see how this works in an example. Let's say that A is this 3 by 2 matrix, and B is this 2 by 4 matrix. Then if we want to multiply B transpose times A transpose, the entries of the resulting product matrix will come from rows of B transpose multiplied by columns of A transpose. For example, the entry in the 2, 3 position of the product, that is the second row, third column of the product, will come from multiplying the second row of B transpose with the third column of A transpose. But that's the exact same thing as multiplying the second column of B by the third row of A. So that'll be the 3, 2 entry of the product A times B. And in general, the IJ entry of A times B is equal to the JI entry of B transpose A transpose. But that means that the roles of rows and columns is exactly switched between these two matrices, and therefore B transpose A transpose is going to be the transpose of AB. So this statement here is a true statement for all matrices AB for which it makes sense. What about this next statement? The transpose of a scalar K times A is the same thing as a scalar K times A transpose. It's not too hard to convince yourself that this is true with an example. If we multiply 5 by the entries of a matrix and then switch the roles of the rows and columns, that's going to be the same thing as switching the roles of the rows and the columns and then multiplying that by 5. What about this next property? Is it true that A inverse transpose is the same thing as A transpose inverse? It may surprise you that this is true, at least for our square matrices, so that taking the inverse makes sense. One way to show that this is always true is to look at the product A inverse transpose by A transpose. If we can show that this product is the identity, then we'll know that A inverse transpose is the inverse of A transpose, which is what we're trying to show. But when we take a product of two transposes, we saw from this true property, the product of two transposes is just the transpose of the product in the other direction. So this is the transpose of the product in the other direction. Hey, A times A inverse is just the identity matrix. And when we take the identity matrix as transpose and switch the rows and columns, we just get the same thing as the identity matrix. And therefore, A inverse transpose is indeed the inverse of A transpose, like we wanted. Finally, is this last property true or false? Is A transpose transpose the same thing as A? I hope you're thinking that it's true. It's true because if we switch the rows and the columns, and then switch the rows and the columns again, we get back to the same thing. In this video, we defined the transpose of a matrix and looked at how transpose interacts with other matrix operations, like multiplication, addition, and inverses. This video is about symmetric and skew-symmetric matrices. A square matrix, let's call it A, is called symmetric if A transpose is the same thing as A. And a square matrix A is called skew-symmetric if A transpose is the negative of A. That is, its entries are the same as A's entries with negative signs in front of them all. So which of these three matrices are symmetric and which are skew-symmetric? If I take the transpose of the first one, I get this matrix. And we can see that that's the same as the original matrix. Therefore, this matrix is symmetric. Notice how a symmetric matrix has symmetry across its diagonal. The entries, if we reflect them over the diagonal, we get the same thing. That makes sense because taking the transpose is like flipping rows to columns. Let's see what happens when we take the transpose of the next matrix. The resulting matrix is exactly the negative of the original matrix, so this matrix is skew-symmetric. Once again, it's useful to think about the diagonal. Notice that all the entries above the diagonal, if we flip them across the diagonal, they line up with their negatives on the other side. Notice also that we have zeros all along the diagonal. If a matrix is skew-symmetric, it has to have zeros on its diagonal because when we take the transpose, the entries on the diagonal stay where they are, and so the only way that an entry can be its own negative is if it's zero. What about this third matrix? What happens when we take its transpose? We definitely don't get the same matrix. For example, this entry here is 1, but the corresponding entry in the original is -1. So we don't have the same matrix here, so the matrix wasn't symmetric. And we don't quite have the negative of the original. I mean, most of the entries are the negatives of their corresponding entries, but not the ones along the diagonal. And so it can't be skew-symmetric either. This matrix is neither. We know that symmetric and skew-symmetric is related to the idea of transpose. So let's see what happens if we take a matrix and add its transpose, or subtract its transpose, or multiply by its transpose. Please pause the video and try to answer these three questions. You may want to write out a matrix A and try an example. For a square matrix A, is A plus A transpose always symmetric, skew-symmetric, or neither of these? If I look at an example, here's an A, here's its transpose, and here's the sum, we get a symmetric matrix for this example. And in fact, A plus A transpose will always be symmetric. That's because if we take A plus A transpose and transpose it, we saw in the properties of transpose video, this is the same thing as A transpose plus A transpose transpose, which is the same thing as A transpose plus A, which is the original matrix. Since the transpose of A plus A transpose is the same as the original, the matrix is symmetric by definition. What about A minus A transpose? Again, if we look at an example, and I'll just use the same matrix A, we get a matrix that's skew-symmetric. Notice how each entry is the negative of its mirror image entry across the diagonal, and all the entries on the diagonals are 0. In fact, A minus A transpose is always skew-symmetric. We can write out the argument like we did before. A minus A transpose transpose is the same thing as A transpose minus A transpose transpose, because subtracting two matrices and then switching the rows and columns is the same thing as switching the rows and columns first and then subtracting. But A transpose transpose is the same thing as A, So this is just A transpose minus A, which is the negative of A minus A transpose. So when we take the transpose of A minus A transpose, we get the negative of the original. And that means that matrix A minus A transpose is skew-symmetric by definition. Finally, what about A times A transpose? Here we're taking the transpose of A and we're multiplying on the left by A. Notice that A times A transpose is always a square matrix, whether or not A is a square matrix. That's because if A has dimensions m times n, A transpose will have dimensions n times m, and the product will have dimensions m times m. So it makes sense to ask the question if A times A transpose is symmetric or skew-symmetric, whether or not A is square, because this will still be square. We could write out an example and check it with an example, but I'm going to go straight to writing A transpose and taking the transpose of that and seeing what I get. Recall that the transpose of a product is the same thing as taking the product of the transposes where you do the multiplication in the opposite order. So instead of A times A transpose, I'm going to put the second one, A transpose, in the first spot, and the first one, A, in the second spot. Well, A transpose transpose is just A, so this is A times A transpose, which is the original matrix that we started with. And therefore, we have that A times A transpose is symmetric. So we checked that A times A transpose is always symmetric. What about A transpose times A? I'll leave it to you to write out the details and check that this product is also always symmetric. Finally, I have a question for you. Is it possible to write this square matrix as the sum of a symmetric matrix and a skew-symmetric matrix? Try your hand at it and see if you can do that. It's possible to solve this problem by trial and error, but I'm going to show you a sneaky shortcut. Recall that A plus A transpose is symmetric, and A minus A transpose is skew-symmetric. But notice that if I take A plus A transpose and add it to A minus A transpose, that's the same thing as A plus A transpose minus A transpose. But A transpose minus A transpose, when you take a matrix and subtract all its entries, that just gives you the zero matrix. And so we just have A plus A, which is the same thing as 2A. So if I take 1/2 of A plus A transpose plus 1/2 of A minus A transpose, these will still be symmetric and skew-symmetric, but now they'll add up to 1/2 A plus 1/2 A, which is just A. So a nice trick to solve this problem is to take first a matrix, the matrix 1/2 A plus A transpose. That's 1/2 this matrix plus its transpose, which works out to 1/2 of this matrix, which simplifies to this. Then we'll take 1/2 of A minus A transpose, which simplifies to this. Notice that the first matrix is indeed symmetric, and the second is skew-symmetric. You can check that when we add up these two matrices, we do indeed get our original matrix A. This video was about symmetric matrices, which are their own transpose, and skew-symmetric matrices, which are the negatives of their transpose. This video is about the trace of a matrix. If you have an n by n square matrix A, the trace of the matrix, written TR of A, is the sum of the entries on the diagonal. By diagonal, I mean the diagonal that starts at the upper left and goes down to the bottom right. In abstract notation, if our matrix A has entries given by A11, A12, and so on through A1n in the first row, A21, A22, through A2n in the second row, and so on, down to AN1, N2, through ANN in the last row, then the trace of A is what you get by adding up these diagonal entries, the entries of the form A11 plus A22 plus A33, all the way through ANN. But it's easier to talk about the trace in a specific example. For this 4 by 4 matrix B, the trace is what we get by adding up the 4 numbers on the diagonal, 4 plus 1 plus 3 plus 5, and these add up to 13. Let's see how trace interacts with other operations on matrices. Suppose that A and B are 2 square matrices of the same size, n by n matrices, and let's let K be a number, a scalar. Then what can we say about the trace of A plus B? Well, if we take 2 matrices and add them together, we do that by adding corresponding entries. So if we want to take the trace of A plus B, we're adding up all those numbers on the diagonal, but that's just exactly the same thing as taking the sum of these 3 numbers and adding those 3 numbers. Therefore, the trace of A plus B is the same thing as the trace of A plus the trace of B. Similarly, when we subtract 2 matrices, we subtract corresponding entries. So the trace of A minus B, which is the sum of these numbers on the diagonal, is the same thing as taking the sum of these numbers and subtracting all of these numbers. Therefore, the trace of A minus B is the same thing as the trace of A minus the trace of B. Let's look at a scalar multiple K times a matrix. I'll use the same matrix A. Scalar multiple means I just multiply all these entries by K. So if I want to take the trace of K times A, I'm adding up these numbers, which is the same thing as adding up these numbers and multiplying by K, since multiplication is distributive. Therefore, the trace of K times A is the same as K times the trace of A. Well, following the pattern here, you might expect that the trace of A times B is the trace of A times the trace of B, but in fact, this is not true. For example, here I have 2 2 by 2 matrices, both of whose trace is 0, but when I take the product, I get a matrix whose trace is definitely not 0. But there is at least one thing we can say about the trace of A times B, and that's that it's equal to the trace of B times A. It's certainly true for this example, but it's actually true in general for any pair of n by n matrices. Suppose I have some general matrix A with entries A11, A12, through A1n on the first row, A21, A22, through A2n on the second row, and so on, and a general matrix B with its entries labeled B11, B12, B1n on the first row, and so on. To find the trace of A times B, we're going to have to add up the elements on the diagonal of A times B. Well, the entry in the first position of the diagonal of A times B is going to be the first row times the first column. So that would be A11, B11 plus A12, B21 plus A13, B31, all the way through A1n, Bn1. That's how I would multiply this first row by this first column. So that would be the first entry I add up in the trace of AB. The next entry that I add up in the trace of AB would be the entry that ends up in the second row and second column of the product. So that's the entry I get by multiplying row 2 of A by column 2 of B. So that would have entries A21, B12, plus A22, B22, plus A23, B32, all the way through A2N, BN2. The next entry of the trace would be the entry in the third row and third column of the product. I add up more and more entries till I get to the nth row and nth column entry of the product. I'd have to add up all these numbers to get my trace of AB. But what if instead I add up this way, sort of one column of this big mess at a time? This first column of terms actually corresponds, if I added all these up, that would be what I would get by multiplying the first row of B times the first column of A, right? I'd get B11 times A11, B12 times A21, that's this, B13 times A31, that's this, and at the end, B1n times AN1, that's this right here. So this column of numbers that I circled in purple added up would be the first row of B times the first column of A. The second column added up would be the second row of B times the second column of A. Next purple column would be the third row of B times the third row of A, and so on. So each of these purple columns added up is an entry on the diagonal of the matrix B times A. And when I add all these numbers up, I'm really just adding up the trace of B times A. Trace of A times B is therefore equal to the trace of B times A. There's just a couple more properties I want to look at. If we have a matrix A, and I take its transpose, well, the transpose doesn't change the entries on the diagonal, and therefore it doesn't change the trace. The trace of A transpose is the same as the trace of A. Last of all, what can we say about the trace of A inverse in terms of the trace of A? Well, it turns out pretty much nothing. As an example, suppose I have these two matrices, I'll call them A and B, that both have the same trace, right? These both have a trace of 3. But if I calculate their inverses, the trace of A inverse is 3, while the trace of B inverse is -3/4. So there's no simple relationship between the trace of an inverse matrix and the trace of the original matrix. If you're especially observant, you might notice that for 2 by 2 matrices, there is a relationship between the trace of the inverse and the trace of the original and the determinant of the original. Namely, the trace of the inverse is the trace of the original divided by its determinant. But things get even more complicated for higher dimensional matrices, and there's no simple relationship between trace and inverse. This video was about the trace of a matrix and how it interacts with other operations on matrices. I want to remind you that a trace is only defined for a square matrix. This video shows how to calculate the determinant of a matrix. Determinants are only defined for square matrices, matrices with the same number of rows and columns. People don't usually talk about the determinant of a 1 by 1 matrix. People don't usually talk about 1 by 1 matrices at all. But if for some reason you needed to compute the determinant of a 1 by 1 matrix, a matrix with only one entry, then that determinant would just be the entry itself. So now let's get to the simplest real situation where you'd want a determinant, the determinant of a 2 by 2 matrix. That determinant is given by this crisscross product, A times D minus B times C. There are a few notations for determinant. Sometimes you might just see the letters DET of your matrix. So that means the determinant of the matrix. Or you might see DET of A, if A is the name of your matrix. Another notation you might see is just straight lines, kind of like big absolute value lines surrounding the entries of your matrix. So all three of these are notations for the determinant of a matrix A with entries A, B, C, D. So now let's work an example. We're going to find the determinant of the matrix with entries 3, -2, 4, 5. So that means 3 times 5 minus 4 times -2, which is 15 minus -8, or 23. Once we go up in size from a 2 by 2 matrix to a 3 by 3 matrix, things get a little more complicated. We can compute the determinant of a 3 by 3 matrix by expanding along the first row and computing an alternating sum of entries times determinants of 2 by 2 matrices. By an alternating sum, I mean we alternate adding, subtracting, and so on. Let me explain more precisely what I mean. Expanding along the first row means we start with the first entry of the first row, so A, and then we take the determinant of the matrix we get by crossing off the row and column that A is in. So that's the determinant E, F, J, K. Next, we take the next entry in that row, B, and we multiply B by the determinant of the 2 by 2 matrix we get by crossing off the row and column that B is in. But we're doing an alternating sum, so we're going to subtract this one, B times the determinant of D, F, I, K. Continuing along the first row, we take the next entry, C, and we're going to add C times the determinant of the matrix we get by crossing off the row and column that C is in. So that's plus C times the determinant of D, E, I, J. If you like, we can write all that out as a formula, A times EK minus JF minus B times DK minus IF plus C times DJ minus IE. But I think it's easier just to remember the process rather than some complicated formula. So let's use this process on this example determinant. We're going to expand along this top row. So we'll start with the number 2 and multiply it by the matrix we get by crossing off the first row and first column. 2 times determinant of -4, 2, 1, -1. Then we'll subtract 5 times the determinant of 1, 2, 2, -1. And now we'll add 3 times the determinant of 1, -4, 2, 1. That works out to 2 times this product minus this product. So 2 times 4 minus 2, minus 5 times -1 minus 4, plus 3 times 1 minus -8. And that all works out to an answer of 56. Now, I have a question for you. What's so special about expanding along the first row? I invite you to try expanding around the first column instead. Do the same sort of process. Take one number at a time, cross out the row and column it's in, and do an alternating sum that way. When I do that, I get 2 times the determinant of -4, 2, 1, -1, minus 1 times the determinant of 5, 3, 1, -1, plus 2 times the determinant of 5, 3, -4, 2. And that works out to 56. Try using a few more rows or columns. If you use the second row, you have to be careful to use a negative sign in front of the first entry, a plus sign instead of the second, and a negative in front of the third. So it's still an alternating sum, but it's going negative here, positive here, and negative here. Same thing if you expand down the second column. You have to have a negative in front of the 5, a positive in front of the 4, and a negative in front of this entry 1. But if you use the third row or the third column, you're starting with a plus again and still doing an alternating sum. So it's kind of like the matrix itself has a checkerboard of pluses and minuses, and when you add up these entries times these 2 by 2 determinants, you just got to make sure you add them with the alternating sum that starts with the right negative or positive sign. I won't prove it here, but it's kind of cool that you get the same answer no matter what row or column you expand along, as long as you start with the right positive or negative sign. And this can also be handy for computation. If there happens to be a row or a column that has a lot of zeros in it, you might want to expand along that one to save yourself some arithmetic. Let me revisit what we just did with a little bit of definitions and notation. So for a 3 by 3 matrix A, the determinant of the 2 by 2 matrix that you get by crossing out the ith row and the jth column is called the ij minor, and it's denoted aij. So for example, if we wanted to find the ai11 minor, that would be the determinant of the matrix we get by crossing off the first row and the first column. So that would be 4 minus 2, which is 2. And A12 is the determinant of the 2 by 2 matrix we get by crossing off the first row and the second column. So that would be the determinant of 1, 2, 2, negative 1, which works out to negative 5. Similarly, A13 works out to 9. And when we calculated the determinant of matrix A, we took the alternating sum of entries times minors. So we took A11, the entry in the 1, 1 position, times A11, that minor, minus a little a12, the entry in the first row second column, times the minor A12, and then we added little a13 times the determinant of that 2 by 2 matrix A13. We also saw we could calculate the determinant by expanding along different rows or columns. For example, along the third column would be A13, capital A13, minus A23, capital A23, plus A33, capital A33. Now that we have this terminology and notation, let's extend this to find the determinants of matrices of higher dimension. So in general, if A is an n by n matrix, the ij minor of A is the determinant of the n minus 1 by n minus 1 matrix we get by crossing out row I and column J of A. The notation for the ij minor of matrix A is just Aij, as before. And the determinant of A is given by what we get by expanding along the first row of A and taking an alternating sum of entries times minors. So in symbols, that would be little a11 times minor big A11 minus little a12 times minor big A12 plus little a13 big A13 minus, and so on, until we finally get to A1n big A1n, and that will be either a plus or minus depending on whether n is even or odd. As with the 3 by 3 matrices, it turns out that you can actually expand not just along the first row, but along any row or column, as long as you start with the plus or minus sign that corresponds to this checkerboard pattern of plus or minuses with a plus in the upper left corner. So please stop the video and use this algorithm to calculate the determinant of this 4 by 4 matrix. Beware, it's going to involve a lot of arithmetic. So I'm going to expand along the first row. That means I'm going to start with the 1 times the determinant of this 3 by 3 matrix, and I'm going to subtract the 2 times the determinant of this 3 by 3 matrix plus 0 times this 3 by 3 matrix. Zeros make me happy here. We're not going to have to worry about this because it's just 0. And finally, I can subtract 3 times the determinant of this 3 by 3 matrix. Now I'm going to compute my 3 by 3 determinants each separately, and I'll just expand each one along its first row. So I get -8 for the first one, -14 for the next one, and -4 for the last one. So this all adds up to 1 times -8, -2 times -14, -3 times -4, and the final answer for the determinant of this 4 by 4 matrix is 32. And if you chose to calculate this determinant by expanding instead along a different row or column at any stage of the way, you should still get the same answer. This video showed how to calculate the determinant of a matrix by expanding along a row or column and then using determinants of lower dimension matrices. It turns out that when two matrices are related by elementary row operations, like switching two rows or multiplying a row by a constant, then their determinants are also related. This video lays out those relationships. Before we get to elementary row operations, I want to do one warm-up example. Please pause the video and see if you can figure out the determinant of this matrix A. I'm going to calculate the determinant by expanding along the first row. So I'm going to get 2 times the determinant of 1, 5, 3, 4, minus 1 times the determinant of 2, 5, 0, 4, plus 5 times the determinant of 2, 1, 0, 3. So that works out to 2 times 4 minus 15 minus 1 times 8 minus 0 plus 5 times 6 minus 0. If I add that all up, I get minus 22 minus 8 plus 30, which adds up to 0. Is it a coincidence that I got 0? No, actually I could have predicted that before I did any computations. Notice that in this matrix, the first two rows are identical. We know from a previous video that we get the same determinant no matter which row or column we expand over. Let's look what happens if we expand over the third row instead. Then we get the determinant of A is going to be 0 times the determinant of the matrix 1, 5, 1, 5, minus 3 times the determinant of the matrix 2, 5, 2, 5, plus 4 times the determinant of the matrix 2, 1, 2, 1. Notice that each of these 2 by 2 submatrices has 2 of its rows exactly equal. And so when I calculate any of these 2 by 2 submatrices determinants, I'm going to get 0. Therefore, the whole determinant has to be 0. A similar calculation shows that for any 3 by 3 matrix that has 2 rows the same, its determinant will have to be 0. And in fact, if we had a 4 by 4 matrix with 2 rows the same, here the first and the fourth row are the same. If we expand on some row that's not the first or the fourth, those little 3 by 3 submatrices that we take determinants of, they would have 2 rows the same, and so they would have all determinants 0, so the ultimate determinant would have to be 0. Using an inductive argument like that, going up one dimension at a time, we can see that it seems plausible that for any square matrix A, if 2 rows of A are identical, then the determinant of A must be 0. And the same thing holds if 2 columns of A are identical. Now let's move on to the main topic of this video, the elementary row operations. Recall that there are 3 elementary row operations that we use to convert matrices to reduced row echelon form. First, we might switch 2 rows. Second, we might multiply a row by a number. And third of all, we might add a multiple of one row to another row. Let's see what those elementary row operations do to the determinant of a matrix. Let's start by just calculating the determinant of this matrix A. So I'll expand along the first row of the matrix. If I work out the determinants of those 2 by 2 matrices, I get minus 6 minus 0, minus 8 minus 0, and 20 minus 3. So that works out to a total of negative 7 for the determinant of A. Now let's see what happens if we swap the first two rows. I'll call this new matrix A prime. Well, I could calculate the determinant of A prime by expanding along its new top row, but actually I'm going to save myself some arithmetic by expanding along this middle row because I've already worked with those numbers before. So if I do that, I have to remember to start with a negative sign. So negative 1 times the determinant of 3, 0, 5, negative 2. Then I do plus 2 times the determinant of 4, 0, 1, negative 2. And then minus negative 1 times the determinant of 4, 3, 1, 5. Do you notice that this computation is exactly the negative of this computation, right? All of these 2 by 2 matrices are the same, and I have all the same coefficients. I've just started with a negative instead of a positive, so everything is the negative of what it was up here. Therefore, without having to do any additional arithmetic, I can jump right to the conclusion that I'm going to get negative of the determinant of what I got before. In other words, 7. In fact, that happens anytime you switch the first two rows of any matrix, and better than that, it happens anytime you switch any two rows. So the fact that we won't prove here is that for any square matrix A, if we switch any two rows to get a new matrix A prime, then the determinant of A prime is the negative of the determinant of A. Next, let's see what happens if we multiply the first row of A by 5. I'll call this matrix A tilde. So let me calculate the determinant of A tilde, and I'm just going to expand again along the first row. Well, again, if I'm lazy, I don't actually have to do any additional arithmetic because I've already computed enough when I first computed the determinant of A. All of these 2 by 2 matrices are the same, and these coefficients, which come from the entries in my first row, are exactly 5 times the corresponding coefficients for the original A. And therefore, when I do this computation, it's got to end up being 5 times what we got before, 5 times negative 7 or negative 35. And this same principle works for any matrix A and any scalar multiple and any row that we want to multiply. So the fact is, for any square matrix A and any scalar K, if we multiply any row of A by K to get a matrix A tilde, then the determinant of A tilde is going to be K times the determinant of A. Let me point out that we're only allowed to multiply one row by K. If we end up multiplying 2 rows by K, then the new determinant would be K squared times the old determinant. And in the case of a 3 by 3 matrix, if we end up multiplying the whole entire matrix by K, in other words, multiplying each row by K, that would end up multiplying the determinant by K cubed. Finally, let's look at what happens to the determinant if we start with the original matrix and add twice the second row to the first row. In other words, we're going to replace the first row with the first row plus 2 times the second row. I'll call this new matrix A hat. I'll expand along the first row again. This one's a little harder to analyze, but if I just work out the arithmetic, I see that I get the same answer of negative 7 as I did for my original A matrix before. This is no coincidence. In fact, it always happens when we do this kind of elementary row operation. So the fact is, for any square matrix A and any scalar K, if we add k times one row of A to another row of A to get a new matrix A hat, then the determinant of A hat is exactly the same as the determinant of A. I'm going to try to give you an idea for why this property holds. When I expanded along the first row of A hat to get its determinant, the coefficients in the expansion came from the first row of A hat, but the first row of A hat came from the first row of A plus twice the second row of A. Let me rewrite my expansion to make that clear. Here I've color-coded the part of this coefficient 9 that came from the first row of A in green, and the part that came from twice the second row I put in purple. Similarly for this coefficient of 8 and this coefficient of -1. Now I'm going to distribute to split out the part of the determinant that goes with the green and the part of the determinant that goes with the purple. Now you can check that this green part is exactly the determinant of A. Makes sense because these green coefficients came from the first row of the original A. But you can also check that this purple expression is twice the determinant of a matrix with the first two rows identical. Specifically, it's twice the determinant we get by replacing the first row of A with the second row of A and keeping the second row of A as it is. Well, we saw previously that the determinant of any matrix with two identical rows is just 0. So therefore, the determinant of A hat is just the determinant of the green part, that's the determinant of A, plus 0. In other words, determinant of A hat is equal to the determinant of A. In this video, we looked at 3 elementary row operations: switching 2 rows, multiplying a row by a number, and replacing a row with that row plus a multiple of another row. We found that the third elementary row operation doesn't change the determinant at all. The second one multiplies the determinant by that number. And the first row operation, switching 2 rows, multiplies the determinant by -1. We also saw that the determinant of a matrix with 2 identical rows is 0. This video gives some properties of determinants. I'm going to start with this warm-up example. See if you can figure out the determinant of this 4x4 matrix. One hint is you might want to expand along a row or column that has a lot of zeros to make your life easier. So I think I'll expand along the first column. Then the determinant of B is going to be 3 times the determinant of this 3x3 submatrix minus 0 times the determinant of this 3x3 submatrix plus 0 times this 3x3 determinant minus 0 times this last 3x3 determinant. Well, I was kind of wasting my time even writing down all these 3x3 determinants because 0 times anything is going to be 0. So these last 3 terms are all just 0. And the determinant of B is just 3 times this 3x3 determinant. So continuing, I'm going to figure out this 3x3 determinant by expanding along its first column, since it has a lot of zeros in it. So let me carry the 3 and now start expanding. So that's 5 times a 2x2 determinant minus 0 times something plus 0 times something. So those drop out, and I just have the 3 times the 5 times that 2x2 determinant. Finally, I can calculate the 2x2 determinant as just -2 times 10 minus 0. So I'm ultimately getting 3 times 5 times negative 2 times 10. That's negative 300, but more interestingly, my determinant is just the product of these entries on the diagonal. And that's no coincidence. That came directly out of expanding along this column with almost all zeros to just get that 3 times the determinant of here, and expanding this gives us the 5 times the determinant of this, and expanding this gives us the negative 2 times 10. So this is an example of an upper triangular matrix. An upper triangular matrix is a matrix with all entries 0 below the diagonal. Similarly, a lower triangular matrix is a matrix with all entries 0 above the diagonal. I guess the upper triangular refers to the fact that it's the only non-zero entries are in the upper triangle, including the diagonal, and the lower triangular is something like this, whose only non-zero entries are in this lower triangle. So a triangular matrix is a matrix that is either upper triangular or lower triangular. And as we saw above, the determinant of a triangular matrix is just the product of its entries on the diagonal. That makes a triangular matrix one whose determinant is super easy to compute. Now let's go on to our main topic for this video, which is how the determinant interacts with other matrix operations. So let's let A and B be n by n square matrices, and let's let K be a scalar. Please pause the video and see if you can come up with any rules for the determinant of K times A, the determinant of A transpose, the determinant of A times B, and the determinant of A inverse for an invertible matrix. The idea is to write down the determinant of these quantities in terms of the determinant of A, or in this case, in terms of the determinant of A and B. You might want to write down some example matrices and work out some examples. We saw in a previous video that if we multiply one row of A by K, then that multiplies the determinant by K. Well, if we're multiplying the whole matrix A by K, that's like multiplying the first row by K, and then multiplying the second row by K, and all the way through the n row by K. So that should multiply the determinant by K n times. So I'll write 3 dots for therefore. The determinant of Ka is going to be K to the n times the determinant of A, where n is the number of rows of A, also the number of columns since A is square. What about the determinant of A transpose compared to the determinant of A? If you think it should be the same as the determinant of A, you're correct. Certainly it's true for our 2 by 2 matrices. The crisscross product is the same for the matrix and for its transpose. But if we look at a 3 by 3 matrix and its transpose, then evaluating the determinant of A by expanding along the first row and evaluating the determinant of A transpose by expanding along the first column gives us two expressions with the same coefficients here, 3, -4, and 7, and 2 by 2 matrices that are the transposes of each other and therefore have the same determinants. And so therefore the determinant of A and the determinant of A transpose must be the same. It's the same computation. An inductive argument like that, going up one dimension at a time, will show us that determinant of A and A transpose is also the same for a 4 by 4 matrix or a 5 by 5 matrix or any n by n matrix. What about the determinant of A times B? If you worked on an example, you might have noticed that it equals the determinant of A times the determinant of B. This fact is a little tricky to prove in general, but it's not hard to prove, say, for upper triangular matrices. If you work out what happens when you multiply two upper triangular matrices, you'll see that you get another upper triangular matrix. And in addition, the entries on the diagonal are just the product of the diagonal entries. For example, this entry here, where I multiply this row and this column, because of these two zeros that hit the 8 and the 9, I'm just going to get 5 times 2. Similarly, in this entry that comes from the second row of A times the second column of B, I'm just going to get 2 times 1, since the 0 times the 7 and the 7 times the 0 are both 0. Similarly, this entry here is 3 times 4. And I might get other horribly messy stuff in these positions, but I'm not worried about that because it doesn't affect the determinant. Now we can see that since the determinant of A is the product of its diagonal entries, and the determinant of B is the product of its diagonal entries, the determinant of A times B is the product of its diagonal entries. That ends up just being the diagonal entries of A times the diagonal entries of B, or the determinant of A times the determinant of B. So the fact that the determinant of A times B is the determinant of A times the determinant of B seems to work at least for upper triangular matrices, and in fact it turns out to work for all matrices. Finally, if A is invertible, how does the determinant of A inverse compare to the determinant of A? Well, we know that A being invertible means that A times A inverse is the identity matrix, and A inverse times A is the identity matrix. Using this multiplication property above, the determinant of A inverse times A is the same as the determinant of A inverse times the determinant of A. But that has to equal the determinant of I, and since I is just a triangular matrix with zeros, it's actually both upper triangular and lower triangular, but in any case, its determinant is just the product of its diagonal entries, which is 1. Therefore, we can solve for determinant of A inverse by taking 1 over the determinant of A. If you're worried that you might end up dividing by 0 here, you don't have to. If A is invertible, the determinant of A can't be 0. It can't be 0 because its product with something else has to be 1. You might notice that I haven't put anything on this list about the determinant of A plus B. That's because there's no relationship between the determinant of a sum and the determinant of the two pieces. Let's talk some more about invertible matrices and their determinants. We just saw that if a matrix A is invertible, then its determinant is not equal to 0. In fact, this is an if and only if statement. So if it's invertible, then the determinant is not 0, and if the determinant is not 0, then the matrix is invertible. These two conditions, A being invertible and the determinant of A being not 0, are equivalent. Let's use this equivalence of conditions to check if this 3 by 3 matrix is invertible. If we look at the determinant, we can calculate it pretty quickly since this is an upper triangular matrix. The determinant of this matrix is the product of its diagonal entries, 3 times 2 times 6, or 36, which is not 0. Therefore, the matrix is invertible. In this video, we found that the determinant of a triangular matrix is the product of its diagonal entries. We found ways to relate the determinant of a matrix A to the determinant of a scalar multiple of A, the determinant of A's transpose, and the determinant of A inverse if A is invertible. This video also stated the fact that a matrix A is invertible if and only if its determinant is not 0. Remarkably, it's possible to tell if a matrix is invertible or not just by calculating its determinant. If a square matrix A has a determinant that's not 0, then A is invertible. If, on the other hand, the determinant of A equals 0, then A is not invertible. Another way to say this is that a square matrix A is invertible if and only if the determinant of A is not 0. These two conditions, A being invertible and the determinant of A being non-zero, are equivalent. The purpose of this video is to give a proof of this fact. Let's prove the statement that an n by n matrix A is invertible if and only if its determinant is not equal to 0. To do this, we need to prove first that if A is invertible, then determinant of A is not 0, and second, if determinant of A is not 0, then A is invertible. Let's focus on this first statement first. If A is invertible, then we know there's an inverse matrix, A inverse, and A times A inverse is the identity matrix. But that means that the determinant of A times A inverse is equal to the determinant of the identity matrix. But the determinant of I is just equal to 1. That's because the identity matrix I has a bunch of 1s down the diagonal and 0s in all the other places. So the identity matrix is an upper triangular matrix. It's also a lower triangular matrix. And we know that the determinant of a triangular matrix is just the product of its diagonal entries. In this case, a product of a bunch of 1s, which is 1. So we have that the determinant of A times A inverse is 1. But the determinant of a product is the product of its determinants. So the determinant of A inverse is the same thing as the determinant of A times the determinant of A inverse. And that has to equal 1. And therefore, neither of these two factors can be 0, since you can't multiply 0 by something else and get 1. In particular, we have that the determinant of A is not equal to 0. That proves this first statement. And now we need to prove the second statement. So let's suppose that the determinant of our n by n matrix A is not equal to 0. Let's do some elementary row operations to reduce A to reduce row echelon form, and I'll call this new matrix A tilde. That is, A tilde is the reduced row echelon form for A. Now, we saw in a previous video that elementary row operations change the determinant of a matrix in very predictable ways. Switching to rows of a matrix multiplies the determinant by -1. Multiplying a row by a scalar k multiplies the determinant by k. And finally, adding a multiple of one row to another row leaves the determinant unchanged. Well, when we convert A to its reduced row echelon form, A tilde, we perform a series of these elementary row operations. So at each step, we either multiply the determinant by -1, multiply it by k, or leave it unchanged. But look at this, we're starting with a determinant of 0. Multiply 0 by -1, we still have 0. Multiply it by k, we still have 0. Leave it unchanged, we still have 0. Any of these row operations just leaves the determinant at 0, and therefore the determinant of A tilde, our reduced row echelon form version of A, must be 0. In particular, this shows that A tilde is not the identity matrix, since the identity matrix would have a determinant of 1. And we've seen before that this means that A is not invertible. If it were invertible, when we reduced it to a reduced row echelon form, we would definitely get the identity matrix. So we've proved that if the determinant of A is non-zero, A is invertible, and that completes the proof of the equivalence of A being invertible and the determinant of A being non-zero. In this video, we proved that A is invertible if and only if the determinant of A is not 0. Being invertible and having a non-zero determinant are equivalent conditions. Eigenvalues and eigenvectors of matrices have many applications, including to data analysis, where they can be used to simplify and make sense of a multidimensional data set. This video will define eigenvalues and eigenvectors and explain how to compute them. Consider the 2 by 2 matrix given here and the 2 by 1 vectors u, v, and w. Please pause the video for a moment and compute a times u, a times v, and a times w, and see if you notice anything interesting. To compute a times u, we need to multiply our matrix by the vector 1, 1. The result is 1, 1. Now that's a little weird. We multiplied by this vector u and we got back the same vector u. In other words, a times u is equal to u. Let's see what happens when we do a times v. This time we get an answer of 4, 2. So when we multiplied by v, we didn't get v back again, but we did get 2 times v, because 4 is twice 2 and 2 is twice 1. So we have that a times v is twice v. Does that happen for all vectors? Let's try a times w. This time our answer, -5, -1, is not a multiple of the vector w that we started with. So u and v are special vectors for A in that they're stable under multiplication by A. We'll give them a special name. They're called eigenvectors for A. I'll explain what this means more precisely in the following definition. For an n by n square matrix A, suppose that there's a scalar lambda and a non-zero vector x such that A times x equals lambda times x. Then lambda is called an eigenvalue for A, and x is called an eigenvector. In the above example, we had that A times u was equal to u. I'll write that as A times u equals 1 times u. And we also had that A times v is equal to 2 times v. So 1 and 2 are eigenvalues for A, and u and v are the corresponding eigenvectors. I want to emphasize that in this definition of eigenvalues and eigenvectors, we need the vector x, the eigenvector, to be non-zero. Lambda, the eigenvalue, can be 0 or a non-zero number, but x cannot be the 0 vector. If x were allowed to be the 0 vector, that would kind of be like cheating, because the 0 vector is always going to work. If you multiply any matrix A by the 0 vector, you get the 0 vector. If you multiply any lambda by the 0 vector, you get the 0 vector. So that wouldn't be anything interesting. So does every matrix have eigenvalues and eigenvectors? Is there always some scalar lambda and some non-zero vector x, such that ax equals lambda x? Well, if we allow for complex numbers as lambdas, numbers with i's in them as lambdas, then it turns out the answer is yes. But if we're only interested in real eigenvalues, as we will be in this class, then the answer is no. For example, consider this matrix B with entries 0, 1, -1, 0. If B did have an eigenvalue and an eigenvector, in other words, if there's some x vector such that b times x is lambda times x, then that would mean 0, 1, -1, 0 times, I'll write the components of x as x1, x2, would equal lambda times this vector with components x1, x2. Carrying out the multiplication on both sides of the equation, on the left side we get, let's see, this row times this column is just x2, and this row times the column is negative x1. So on the left side we get this vector, And on the right side, we get lambda x1, lambda x2. So we would need to have x1, x2, and lambda satisfy the two equations x2 equals lambda x1 and negative x1 equals lambda x2. If we substitute in lambda x1 from the first equation into x2 for the second equation, that gives us minus x1 equals lambda times lambda x1. In other words, minus x1 equals lambda squared times x1. So that means either x1 is 0, or if not, we can divide both sides by x1 and get lambda squared equals negative 1. Well, if we're just looking at real eigenvalues, real numbers for lambda, then x squared cannot equal negative 1. There's no real number that when you square it, you get a negative number. So x1 must equal 0, but then going back to this first equation, that means x2 is 0 also. So the only way to satisfy this equation is to use a 0 vector for x, but as we said before, the 0 vector doesn't count as an eigenvector. So in fact, there are no eigenvalues and eigenvectors that work for matrix B. But many matrices do have eigenvalues and eigenvectors. So how do we find them? Before we launch into finding them, I want to remind you of two facts about matrices. First of all, a matrix B is invertible if and only if the equation B times the vector x equals the 0 vector has no other solutions than x equals the 0 vector, which is always going to be a solution to an equation matrix times something equals 0. Since these two statements are equivalent, their negations are also equivalent. So B is not invertible if and only if Bx equals 0 does have other solutions than x equals 0. In other words, it has non-zero solutions. This is going to be relevant because when we're looking for eigenvectors, we're also looking for non-zero solutions to an equation. The second fact that I want you to recall is that a matrix B is invertible if and only if the determinant of B is not 0. Again, we could rewrite this equivalence by taking the negations. B is not invertible if and only if the determinant of B is equal to 0. Now let's see if we can figure out how we find eigenvalues and eigenvectors for a matrix A. Eigenvalues and eigenvectors correspond to scalars lambda and vectors x that satisfy this equation, ax equals lambda x. Let's rearrange this equation by bringing everything over to the left side. Now it's tempting to factor out the x and write something like this. But that wouldn't make sense because you can't take a matrix and subtract a scalar from it. So instead, I'm going to rewrite this equation as a times x minus lambda times I times x equals 0, where I is the identity matrix. This equation is the same as the one above it because I times x is the same thing as x. Now it makes sense to factor out the x and to find eigenvalues and eigenvectors for A. We want to find a lambda and a non-zero x that satisfy this equation. But fact 1 says having a non-zero solution to an equation of the form Bx equals 0 is equivalent to the matrix B being not invertible. So letting A minus lambda I play the role of B, finding a non-zero solution to this equation happens if and only if A minus lambda I is not invertible. Now let's look at fact 2. Fact 2 says a matrix B is not invertible if and only its determinant is 0. So having this matrix A minus lambda I being not invertible is equivalent to the determinant of A minus lambda I equaling 0. So we'll be able to find eigenvectors, solutions to this equation, exactly for those values of lambda that make the determinant of a minus lambda I equal to 0. Now we have a way to find the eigenvalues for a. What we have to do is set the determinant of a minus lambda I equal to 0 and solve for lambda. Once we've found the eigenvalues lambda, we can find the eigenvectors by solving this equation for x. Let me show you how this works with an example. So let's find the eigenvalues for this matrix A. What we need to do is we need to figure out what lambdas will make a minus lambda I have a determinant of 0. I'm going to write down a minus lambda I, so that's going to be 8, 3, 2, 7 minus lambda times 1, 0, 0, 1. That needs to have a determinant of 0. I'll rewrite this as 8, 3, 2, 7 minus lambda 0, 0, lambda. And I can also rewrite it as 8 minus lambda, 3, 2, 7 minus lambda by subtracting these two matrices one entry at a time. So I need the determinant of this matrix to be 0. So that means 8 minus lambda times 7 minus lambda minus 2 times 3 needs to be 0. Distributing out, I get 56 minus 8 lambda minus 7 lambda plus lambda squared minus 6 equals 0. So lambda squared minus 15 lambda plus 50 equals 0. And that factors into lambda minus 10, lambda minus 5 equals 0. So my eigenvalues are lambda equals 10 and lambda equals 5. Now let's find the eigenvectors. So first I'll consider lambda equals 10. Then I need to solve the equation a minus lambda I times x equals 0 with lambda equals 10. So in other words, a minus 10I times x equals 0. So let me write that out. So here's a, and here's 10I. I'll subtract my matrices, so 8 minus 10 is minus 2, 3 minus 0 is 3, 2 minus 0 is 2, 7 minus 10 is minus 3, and I'll write my x in components. Now you might recall that solving an equation like this can be done by writing down the augmented matrix, augmented by the vector on the right side, and converting it to reduced row echelon form. I'm going to do that by adding the first row to the second row, and then multiplying the first row by negative 1/2. Notice that I did not get the identity matrix when I reduced the matrix to reduced row echelon form, and that's good. That's what I expect, because I expect to get non-zero solutions to this system of equations, and actually lots of them. So to find the solutions, I can set x2 to be a free variable, since there's no leading 1 in the x2 position, the x2 column, and then I have that x1 minus 3/2 x2 equals 0, and so x1 is 3/2 x2. So my solutions are of the form 3/2 x2, x2, or this can be written as x2 times 3/2 1. These are my eigenvectors for the eigenvalue lambda equals 10. And if I just wanted one eigenvector instead of a whole family of them, I could just pick an easy value of x2, like x2 equals 1. So for example, the vector 3/2, 1 is an eigenvector for the eigenvalue lambda equals 10. So we're halfway done. Now we need to do the same computation with lambda equals 5. In other words, we need to solve the equation a minus 5I times x equals 0. I encourage you to pause the video and try this on your own before seeing the solution. To solve this, I'll write down A minus 5I and simplify a little. 8 minus 5 is 3, 3 minus 0 is 3, 2 minus 0 is 2, 7 minus 5 is 2, and I can augment that with the 0 vector and convert that to reduced row echelon form. I'm going to add the second row to the first row, put that in the first row's position. So that gives me 1, 1, 0, 2, 2, 0. And then I'm going to add negative 2 times the first row to the second row. That gives me the matrix 1, 1, 0, 0, 0, 0. So once again, I've gotten in reduced row echelon form, and I don't have the identity matrix. I have x2 as a free variable, and I have x1 plus x2 equals 0, so x1 equals minus x2, so my solution eigenvectors are of the form minus x2, x2, or I can write that as x2 times minus 1, 1, and if I want an example, I can use minus 1, 1. In this video, we found the eigenvalues of a matrix A by setting determinant A minus lambda I equal to 0, and we found the corresponding eigenvectors by solving the equation A minus lambda I times the vector x equals the 0 vector. This expression, the determinant of A minus lambda I, is called the characteristic polynomial of A. This video gives some properties of eigenvalues of matrices. Eigenvalues for triangular matrices are especially easy to compute. Let's see what we get when we find the eigenvalues for this triangular matrix, B. We can find the eigenvalues for B by computing the determinant of B minus lambda I, setting it equal to 0, and solving for lambda. Since the matrix lambda I has lambdas on the diagonal and zeros everywhere else, when we take B and subtract lambda I, we're just subtracting a lambda along each of the diagonal entries. Now we need to take the determinant of this and set it equal to 0. We saw in a previous video that the determinant of a triangular matrix is just the product of the diagonal entries. And since the original B was a triangular matrix, the matrix B minus lambda I is also a triangular matrix. So its determinant is 5 minus lambda times 2 minus lambda times 9 minus lambda. When we set that equal to 0 and solve, we get that lambda equals 5, lambda equals 2, or lambda equals 9. These are exactly the diagonal entries of B, and in general, the eigenvalues for a triangular matrix are the diagonal entries of the matrix. Next, let's relate the eigenvalues for a matrix to its trace and determinant. For this matrix C, the trace of C is 2 plus negative 1, which is 1, and its determinant is 2 times negative 1 minus 5 times 2, which works out to negative 12. To calculate C's eigenvalues, let's take the determinant of C minus lambda I, so that's equal to the determinant of 2 minus lambda to 5 minus 1 minus lambda, which works out to 2 minus lambda times negative 1 minus lambda minus 10, and we'll set that equal to 0 and simplify to get negative 2 minus 2 lambda plus lambda squared minus 10 equals 0. So that means that lambda squared minus lambda minus 12 equals 0. We can factor that to get lambda minus 4 times lambda plus 3 equals 0. So lambda equals 4 or lambda equals negative 3 are the two eigenvalues. Notice that the sum of these two eigenvalues, 4 plus negative 3, gives us 1, which is the trace of C, while the product, 4 times negative 3, gives us negative 12, which is the determinant. Let's see what happens for this 3 by 3 triangular matrix D. We know that the trace of D is the sum of the diagonal entries, and because D is triangular, the determinant of D is the product of its diagonal entries. But as we saw in the previous slide, since D is triangular, its eigenvalues are exactly its diagonal entries, -3, 7, and 5. So the sum of the eigenvalues will be equal to the trace, and the product of the eigenvalues will be equal to the determinant. Although I won't prove it here, these facts are true for all matrices, not just 2 by 2 matrices and triangular matrix. For any n by n square matrix, the sum of its eigenvalues is equal to its trace, and the product of its eigenvalues is equal to the determinant. Next, let's see how the eigenvalues of A are related to the eigenvalues of A transpose and A inverse. If I want to find the eigenvalues for A transpose, I need to take the determinant of A transpose minus lambda I and set it equal to 0. The eigenvalues for A transpose are the lambdas that satisfy this equation. But since the identity matrix I is the same as its transpose, and in fact lambda times I is the same thing as its transpose, I can rewrite this equation as A transpose minus lambda I transpose. Recall that the transpose of a sum of matrices is the sum of the transposes. So I can rewrite this again as the determinant of A minus lambda I transpose. But recall also that the determinant of a matrix's transpose is the same as the determinant of the original matrix. So I can rewrite my equation as the determinant of A minus lambda I equals 0. But the eigenvalues of A are the lambdas that satisfy this equation. Therefore, the eigenvalues of A transpose are the same as the eigenvalues of A. Next, let's think about the eigenvalues of A inverse and how they relate to the eigenvalues of A. We know that lambda is an eigenvalue for A with eigenvector x if and only if Ax equals lambda x, where x is a non-zero vector. Multiplying both sides by A inverse, this is equivalent to saying that A inverse Ax is equal to A inverse lambda x. Since A inverse times A is just the same as the identity, and the identity times x is just x, I can rewrite this left side as just x, and the right side I'll pull the scalar lambda out. Pulling the lambda out is legit because if we multiply A inverse by lambda times x, we get entries that are lambda times as big as if we multiplied A inverse by x. Notice that our lambda cannot be 0, because if it were, this whole right side would be 0, and therefore our x vector would be 0, and it wouldn't be a legitimate eigenvector. Since lambda is not 0, it's possible to multiply both sides of this equation by 1 over lambda. But wait, that's just the equation that x needs to satisfy to be an eigenvector for A inverse with eigenvalue 1 over lambda. Maybe it'll be a little bit more clear if I just switch the order. A inverse x equals 1 over lambda x. So this is true if and only if 1 over lambda is an eigenvalue for A inverse with eigenvector x. So the eigenvalues of A inverse are the reciprocals of the eigenvalues of A. And furthermore, the eigenvectors of A inverse are the same as the eigenvectors of A. So is it possible to have an eigenvalue of 0? In fact, it is. For example, if we look at the matrix 1, 0, 1, 0, then the determinant of A minus lambda I is the determinant of this matrix, which is 1 minus lambda times minus lambda minus 0. That equation is 0 if lambda is 1 or lambda is 0. So we do indeed have an eigenvalue of 0 as well as an eigenvalue of 1 for this matrix. But in fact, this can only happen for non-invertible matrices. A matrix A has an eigenvalue of 0 if and only if A is not invertible. Let me explain why. We saw in a video about invertible matrices that a matrix A is invertible if and only if the equation AX equals 0 has only the solution x equals 0. So the negations of these statements are also equivalent. A is not invertible if and only if AX equals 0 does not have only the one solution x equals 0. X equals 0 is still a solution, so this means that there must be some other x that's not 0 that's also a solution. But the equation A times x is the 0 vector is equivalent to saying A times x is 0 times x, since 0 times x is the 0 vector. That's just the same thing as saying that 0 is an eigenvalue for A. So we've shown that A is not invertible if and only if 0 is an eigenvalue for A. And that's exactly what we wanted to prove. Let me note that an equivalent way of saying this is that a matrix A does not have an eigenvalue of 0 if and only if A is invertible. In this video, we covered a lot of properties of eigenvalues. We saw that the eigenvalues of a triangular matrix are just the diagonal entries. We saw that the sum of the eigenvalues is equal to the trace of the matrix, and the product of the eigenvalues is the determinant of the matrix. We saw that A and A transpose have the same eigenvalues, and that A and A inverse have reciprocal eigenvalues. Finally, we saw that a matrix A has an eigenvalue of 0 if and only if it is not invertible. Or equivalently, A is invertible if and only if it does not have an eigenvalue of 0. Recall that a diagonal matrix is a matrix like this one, in which all the non-zero entries lie on the diagonal. In other words, all the entries that are off the diagonal are 0. Diagonal matrices are much easier to work with than just arbitrary matrices. And for that reason, it can be helpful to diagonalize a matrix or relate it to a diagonal matrix when possible. In this video, I'll explain what diagonalizing a matrix means and how to do it in some situations. As we just reviewed, a diagonal matrix is a square matrix whose non-zero entries all lie on the diagonal. A square matrix A is said to be diagonalizable if A can be written in the form P times D times P inverse for some diagonal matrix D and some invertible matrix P. So if A is an n by n matrix, then D and P need to also be n by n matrices to make the dimensions work out. Let's see what this means in an example. We're asked to show that this 2 by 2 matrix is diagonalizable, and we're given a very big hint to use this diagonal matrix and this matrix P, which hopefully is invertible. Recall there's a nice shortcut trick to finding the inverse of a 2 by 2 matrix. We swap the entries in the diagonal and negate the entries that are off the diagonal, and then multiply the whole thing by 1 over the determinant of the matrix. That's 1 times 3 minus 2 times 2, or negative 1. I'll rewrite this by multiplying through by negative 1, and we've got our P inverse. So now we need to check that A is equal to P D P inverse. In other words, we're going to multiply P by D by P inverse and see if that works out to A. I encourage you to pause the video for a moment and work it out for yourself before going on. Now, there's something interesting that happens when you multiply any matrix, in this case P, by a diagonal matrix, in this case D, with the diagonal matrix on the right. You end up just multiplying the columns of the first matrix by the corresponding diagonal entries. In other words, this is just the same as taking the column 1, 2 and multiplying them by 2 to get 2, 4, and then taking this column 2, 3 and multiplying it by 1 to get 2, 3 again. That's the output of that multiplication. Let's just see how that works. We're multiplying to get this entry 2, we're multiplying this row by this column, but since there's a 0 here, we're just really multiplying this first entry by 2. And to get this entry here, we're multiplying this row by this column, which again just multiplies the entry by 2. So this column just got multiplied by 2 to get this column. To get this entry here, we're taking this row times this column. Well, that ends up multiplying this entry by 1 to get this entry, this row by this column, which multiplies this entry by 1. So this column gets multiplied by 1. I went through that in such detail because we're going to use this fact in a moment. In fact, I'll write it out as a little note. So the note is when we multiply any matrix M by a diagonal matrix, I'll call it E, so M times E, this multiplies the columns of M by the diagonal entries of E. All right, so now that we've got that note tucked away there, let's continue with the problem. So we still need to multiply this matrix by the P inverse matrix. And if we work that out, we get, let's see, negative 2, 2, negative 6, 5, which is exactly the A matrix that we started with. So indeed, the matrix A is diagonalizable, and these are the matrices D and P that do the trick. But what if we want to diagonalize a matrix like this matrix A, and we're not given the matrices D and P to do it? We have to find them. In other words, we need to find D, which is diagonal, and P, which is invertible, such that A is equal to P, D, P inverse. I'm going to rewrite that equation by multiplying everything on the right by P. So I get A times P is P times D times P inverse times P. Well, P inverse times P is just the identity, and anything multiplied by the identity is just the same thing. So this equation becomes A times P equals P times D. I want to focus in on the columns of P, so I'll draw attention to them by writing P as its columns concatenated together. And I also want to draw attention to the diagonal entries of D, so I'll write the diagonal entries of D out like this. So let me bring that notation into my equation, AP equals PD. So that's A times the columns P1, P2 equals the columns P1, P2 times this diagonal matrix here that we don't know what B and D are yet. But we do know, because we talked about it on the previous slide, that when we multiply this matrix by this diagonal matrix, we just end up multiplying these two columns by the corresponding diagonal entry. So this is D1 times the column P1, and then we have the column D2 times the column P2. And hopefully you also remember from the video about interpreting matrix multiplication that when you multiply a matrix by another matrix, that's just the same thing as multiplying the matrix by each column of the second matrix and stringing them together. You can just try that out for a couple of matrices and verify it. So this means that we're looking for vectors P1 and P2 and numbers D1 and D2 so that A times P1 equals D1 times P1, and A times P2 equals D2 times P2, so that these two sides of the equation will really be equal. Does that remind you of anything? Because it reminds me a lot of eigenvalues and eigenvectors. This is exactly the statement that D1 is an eigenvalue of A with corresponding eigenvector P1, and ditto for D2 and P2. So we found the key idea for diagonalizing a matrix. We look for eigenvalues and eigenvectors. That's how we build our matrices D and P. So let's get to work. To find the eigenvalues of A, we need to write down the characteristic polynomial, which we do by taking the determinant of A minus lambda I. So that's the determinant of 3 minus lambda, 1, negative 2, 0 minus lambda, which is 3 minus lambda times negative lambda minus negative 2, which simplifies to lambda squared minus 3 lambda plus 2, and that factors to lambda minus 2 times lambda minus 1. When we set that equal to 0, we have the eigenvalues lambda equals 2 and lambda equals 1. Now to find an eigenvector corresponding to the eigenvalue lambda equals 2, we need to solve the equation A minus lambda I times x equals 0 for lambda equals 2. That is, I need to solve the matrix and vector equation. Let's see, when lambda is 2, that gives me 3 minus 2, 1, negative 2, 0 minus 2 times x1, x2 equals 0, 0. And I can do that by writing down the augmented matrix. Let's see, 3 minus 2 is 1, 1, negative 2, negative 2, augmented by 0, 0. And I need to row reduce this to reduced row echelon form. This matrix is pretty easy to row reduce if I just take the first row and multiply it by 2 and add it to the second row and replace the second row with that. I've already got it in reduced row echelon form. This tells me that x2 can be free and x1 plus x2 has to be 0, so x1 is minus x2. So an eigenvector that I can use is just like any x2 and then minus x2 here, or in other words, x2 times the vector minus 1, 1. So I could just use the eigenvector negative 1, 1 to keep things simple. Now I'll repeat this process for lambda equals 1. So now I need A minus 1 times I times x equals 0. So that is this matrix times the x1, x2 vector is equal to the 0 vector. And I can row reduce the augmented matrix to 1, negative 2, negative 1, augmented by 0, 0. This row reduces to this matrix. So I have x2 being a free variable, and 2x1 plus x2 equals 0 means x1 is negative 1/2 x2. So my eigenvectors are of the form x2 times negative 1/2, 1, and so I can just use the eigenvector negative 1/2, 1 as my eigenvector. So now I'm almost done finding P and D. My D matrix is the diagonal matrix made up of my two eigenvalues, 2 and 1, and my P matrix is made up of the corresponding eigenvectors, negative 1, 1, and negative 1/2, 1. Notice that the eigenvectors need to be in the same order as the eigenvalues they correspond to. I will leave it to you to check that when we multiply P by D by P inverse, we get indeed our original matrix A. Here's a little interesting tidbit I want to point out before we move on. The matrices that you use to diagonalize another matrix are not unique, because we could have instead put the eigenvalues in the other order, 1 and 2, and then switched around the corresponding eigenvectors, and that would have worked just as well. So the process we just used for this 2 by 2 matrix can be used for any n by n matrix with n distinct real eigenvalues. The process goes like this. First, you find the eigenvalues, lambda 1 through lambda n, and you put them in your diagonal matrix D. Then you find an eigenvector for each eigenvalue. Let's call these eigenvectors v1 through vn, and we make our matrix P by stringing together those eigenvectors. Now I should point out that it's not always necessary for the matrix A to have, the n by n matrix A to have n distinct real eigenvalues. Sometimes A can be diagonalizable even if it doesn't have as many distinct eigenvalues as its dimension. But this situation will cover all of the problems that will work in this class. So in this video we defined what it means to diagonalize a matrix, and we showed how it can be done using eigenvalues and eigenvectors. This video introduces the dot product of vectors. Suppose I have these two vectors, A and B, each with 3 components. I find the dot product, which is written A dot B. I usually write it with a little circle to make the dot more obvious. To compute that, we multiply corresponding entries and add them up. So here we do 2 times 5 plus -1 times 1 plus 3 times 2, and that adds up to 15. In general, to take the dot product of 2 vectors, each one with n entries, we again multiply corresponding entries and add them up. So here v dot w would be v1 w1 plus v2 times w2 plus all the way through vn times wn. Here are some properties of dot product. Let's suppose that u, v, and w are vectors, all of the same dimension. By the same dimension, I just mean the same number of elements. And let's suppose that c is a scalar. If we take the dot product u dot v, that's the same thing as doing v dot u. In other words, dot product is commutative. Dot product is also distributive over addition. If I take u dot v plus w, that's the same thing as doing u dot v and adding u dot w. And it's distributed in the other direction too. If I take v plus w and dot it with u, that's the same thing as v dot u plus w dot u. If I do scalar multiplication together with dot product, I can move that scalar around any way I want. I can rewrite this as u dot c times v, or I can do u dot v first and then multiply that by c. All of those give me the same thing. All of these first 3 properties can be proved by just writing out dot product in terms of the entries and using the commutative, distributive, and associative properties of regular arithmetic. For example, if we want to prove that u dot v is the same thing as v dot u, if we just write out the entries of a general vector u with n entries and the entries of a general vector v with n entries, we write out u dot v, then that string of arithmetic is the same thing as if we switch the orders of the v's entries and the u's entries, which is the same thing as v dot u. And these other properties can be proved similarly. Finally, last property, if I take u and dot it with itself, then I could get a lot of different numbers, but I'm always going to get a number that's positive or 0. U dot u is always greater than or equal to 0. That's because u dot u can be written in terms of its entries as u1 times u1 plus u2 times u2. Keep adding up the entry times itself, un times un. In other words, it's the sum of a bunch of squares. And squares are always positive numbers or 0. So therefore, this quantity has to be greater than or equal to 0. In fact, u dot u is only going to be equal to 0. It's going to be equal to 0 if and only if the u1, u2, and un are all 0. If even one of them is positive or negative, not 0, when you square it, it'll be a positive number. You'll get something strictly positive. So u dot u is 0 if and only if all of these entries are 0, i.e. u is the 0 vector. The property that u dot u is always greater than or equal to 0 and that it's equal to 0 if and only if u is the 0 vector is called the positive definite property. And that concludes this brief introduction to dot product. In this video, we'll review how the length of a vector is computed, and then we'll talk about unit vectors, which are vectors of length 1. Our first example is a vector A with 2 entries, so dimension 2. To find its length, which I'll write with double bars, although some people write length of a vector just with single bars like absolute value. We take the square root of 2 squared plus 5 squared, which works out to the square root of 29. That makes sense because if you draw the vector with its tail end at the origin and its terminal point at the point 2, 5, then Pythagorean theorem says 2 squared plus 5 squared gives us our length squared. If we want to find the length of this three-dimensional vector, this vector with 3 entries, then we use the three-dimensional version of Pythagorean theorem. The length of b is going to be the square root of 2 squared plus negative 3 squared plus 4 squared. This works out coincidentally to also be the square root of 29. You can also think of this expression for length in terms of the distance formula. If I draw this vector with its tail end at the origin and its tip at the point 2, negative 3, 4, then the length of the vector should be the distance between this point, and by the distance formula, that's the square root of 2 minus 0 squared plus negative 3 minus 0 squared plus 4 minus 0 squared. Exactly the same formula as we used here. In general, the length of a vector v with n entries, v1 through vn, is given by taking the square root of the sum of all those entries squared. Now it turns out that the length of a vector is closely related to its dot product with itself. Recall that when we compute v dotted with v, we just have each component squared all added up. Well, if we take the square root of both sides of this equation, we get the square root of v dot v is the square root of all these components added up. Well, that's just the same thing as the formula for the length of v. So we have that the length of v is the square root of v dotted with itself, or if you prefer, we could write that as the length of v squared is v dot v. This relationship will come in handy in the future. A unit vector is a vector of length 1. So let's check, for example, if this vector A is a unit vector. If we take its length, square root of 1 squared plus 2 squared plus 2 squared, we get square root of 9, which is 3, which is definitely not 1, so the answer here is no. Sometimes it's convenient to take a vector that's not a unit vector and rescale it to be a unit vector. In other words, multiply it by a scalar, by a number, so that that product is a unit vector. So what number would I have to multiply A by to get a vector of length 1, given that its current length is 3? If you're saying multiply it by 1/3, you're exactly right. Multiplying by 1/3 will shrink it by a factor of 3 and get that length of 3 down to a length of 1. Let's just check it with some arithmetic. 1/3 times A is 1/3 times each of these entries. And so the length of 1/3 A will be the square root of 1/3 squared plus 2/3 squared plus 2/3 squared, which is the same thing as the square root of 1 squared plus 2 squared plus 2 squared over 3 squared, which works out to 1. And more generally, For any vector v that is not the 0 vector, we can rescale it to be a unit vector by simply multiplying by 1 over its length. Suppose, for example, we want to rescale this vector b to be a unit vector. Well, the length of b is the square root of 7 squared plus 3 squared. That works out to the square root of 58. So our rescaled vector is going to be 1 over the square root of 58 times b, or in other words, 7 over the square root of 58, 3 over the square root of 58. And that's all for this video on unit vectors. This video introduces orthogonal vectors. Two vectors v and w are said to be orthogonal if their dot product is equal to 0. Please pause the video for a moment and see which of these two pairs of vectors are orthogonal. For the first pair, if we take a dot b, that's 3 times negative 4 plus 4 times 3, that works out to negative 12 plus 12, which is 0, so yes, they are orthogonal. For the second pair, take c dot d, that's 1 times 2 plus 2 times 1, which works out to 4, which is not 0, so no, these are not orthogonal. The word orthogonal means perpendicular. And in fact, it's true that v dot w equals 0 if and only if v is perpendicular or at right angles to w. And if we draw these two pairs of vectors, we can see, in fact, that the first pair is at right angles from each other and the second pair is not. Let's run through a couple more definitions. An orthogonal set of vectors is a collection of vectors such that for any pair of vectors, v and w, in the collection, v is orthogonal to w, i.e., the dot product of v and w is 0. An orthonormal set of vectors is a collection of orthogonal vectors that are also each unit vectors. In other words, for any vector in the set, any vector v, the length of v is 1, and for any pair of vectors, v and w, v dot w is equal to 0. So let's show that this set of vectors, it's just a set of 3 vectors, a, b, and c, let's show that it's an orthogonal set. So for any pair, there are 3 possible pairs. There's a and b, there's b and c, and there's a and c. So let's compute each of these dot products. For the first pair, a and b, their dot product is definitely 0. For the next pair, b and c, I'm getting 33 plus 2 is 35 minus 35. Yep, that's 0. And finally, for the third pair, a and c, yep, here I'm also getting 0. So for any pair of vectors in this set, that pair is orthogonal to each other, and therefore we have an orthogonal set. Is it, however, an orthonormal set? Well, no, because, for example, the length of A is equal to the square root of 18, the length of B is the square root of 171, and the length of C is the square root of 38. So this set doesn't have any unit vectors, and it needs all of its vectors to be unit vectors as well as orthogonal to each other to be an orthonormal set. But I can make it an orthonormal set by taking A and dividing it by its length, or multiplying it by 1 over its length. And same thing with B, and same thing with C. Those vectors, which I'll write out here, those vectors will each be a unit vector, and they'll still be orthogonal to each other. Because since they were perpendicular to each other before we rescaled them, they'll still be perpendicular, they'll still be at right angles to each other after we rescale them by altering their lengths. Another way of seeing the same idea is that since a dot b was 0, when we take a over its length, dotted with b over its length, that's the same thing as 1 over the length of a times 1 over the length of b times a dot b. And since a dot b was 0, multiplying it by a couple of scalars still gets us at the 0. So these two vectors, once rescaled, are still orthogonal. In this video, we defined orthogonal vectors, vectors who are perpendicular to each other, whose dot product is 0. We also defined orthogonal sets and orthonormal sets of vectors. This video defines orthogonal matrices and gives some properties of them. An orthogonal matrix is a square matrix with orthonormal column vectors. Recall that a set of vectors is orthonormal if every pair of vectors is orthogonal and each vector by itself has length 1. Recall that orthogonal means the same thing as perpendicular. It means the dot product of the two vectors is 0. So we could write this first condition in terms of dot product as saying that vi dotted with vj has to be 0, where vi and vj are any two distinct column vectors of the matrix. This second condition, that each column vector has length 1, can also be written in terms of dot product, since the length of a vector squared is the same thing as the dot product of the vector with itself. So saying that the length has to be 1 is the same thing as saying that the length squared has to be 1, or saying that the dot product of the vector with itself has to be 1. So let's verify that this matrix B is an orthogonal matrix. So first, we need to check that each pair of column vectors is orthogonal. So I'm going to give these column vectors names. I'm going to call them this one C1 vector, this one I'll call it C2, and this one I'll call it C3. So we need to check that C1 dotted with C2 is 0, that C1 dotted with C3 is 0, and that C2 dotted with C3 is 0. So, for example, if I want to do the first one, C1 dotted with C2 is this vector dotted with this vector. So that's going to be 1 over root 3 times 1 over root 6 minus 1 over root 3 times 2 over root 6 plus 1 over root 3 times 1 over root 6, which adds up to 1 minus 2 plus 1 over root 3 root 6, which adds up to 0, as we want it to. I'll let you verify for yourself that these other two dot products are also 0. So the column vectors are all orthogonal. Now let's check that they all have length 1. Or equivalently, we could check that the dot product of each column vector with itself equals 1. For example, if we take C1 dot with C1, that's going to be 1 over root 3 times 1 over root 3 plus minus 1 over root 3 times minus 1 over root 3 plus 1 over root 3 times 1 over root 3, which adds up to 1/3 plus 1/3 plus 1/3, which is indeed 1. And I'll let you verify that the other two columns also have length 1. So B is indeed an orthogonal matrix. Let's see what happens when we compute B transpose times B. So here's B transpose, where I've turned every row into a column, and I'm going to multiply that by the original matrix B. So my answer should be a 3 by 3 matrix, and to get the element here in the upper left corner, I need to multiply the first row by the first column. So that looks like what we just did, right? When we calculated column 1 times column 1, it's the same computation. Of course it's the same computation because this row came from, since this is a row as part of B transpose, it came from the first column of B. So we're just doing the first column of B in row form times the first column of B. So that's just the computation we did. That has to equal 1. Now to get the next entry in the first row and second column of the answer, we're going to do the first row of B transpose times the second column of B. But that's just the same thing as the first column of B, right? Times the second column of B. So first column of B times the second column of B was 0. The next entry over here is going to come from the first row of B transpose times the third column of B. But that's the same as doing the first column of B times the third column of B. And since this is an orthogonal matrix, that needs to be 0. If we continue like that, we see that every single entry of this matrix is actually coming from a row of B transpose and a column of B, which is the same thing as coming from a column of B times a column of B. So those are always going to be 0 if we're getting it from distinct columns, and we'll always get 1 if we're taking the dot product of the column with itself. Therefore, our answer is the identity matrix. And in fact, the same reasoning shows that for any orthogonal matrix, when we take the transpose and multiply by the matrix itself, we're destined to get the identity matrix. So that's our first nice property of orthogonal matrices. If we have an orthogonal matrix Q, then Q transpose by times Q is going to be the identity matrix. Another way of saying the same thing is that the inverse of an orthogonal matrix is just the same thing as its transpose, right? Inverses are unique, so if any matrix times Q gives us the identity, that matrix has to be the inverse of Q. Finally, if I take Q times Q transpose, the opposite order of what I did up here, that's the same thing as doing Q times Q inverse, and so I'll also get the identity matrix this direction. That last property actually reminds me of one more nice property of orthogonal matrices. Not only are the columns an orthonormal set, but the rows are also an orthonormal set. That's because when we take Q times Q transpose, we're multiplying rows of Q by the columns of Q transpose, but the columns of Q transpose are just coming from the rows of Q. Therefore, we're just multiplying the rows of Q by the rows of Q. And since we're getting to the identity matrix, that means that each row dot product itself gives us 1, each row dotted with a different row gives us 0. So those rows are orthonormal. In this video, we saw that orthogonal matrices are matrices whose columns are orthonormal. Also, their rows are orthonormal. Also, if you take an orthogonal matrix times its transpose in either direction, you get the identity matrix. In other words, an orthogonal matrice's inverse is just its transpose. This video gives some facts about the eigenvalues and eigenvectors of symmetric matrices. Recall that a symmetric matrix is a matrix like this one, whose transpose is equal to itself. Let's start by finding the eigenvalues and eigenvectors of this symmetric matrix. To find the eigenvalues, we'll write down the characteristic polynomial, the determinant of A minus lambda I. The eigenvalues will be the values of lambda, for which that's equal to 0. Lambda times I is the diagonal matrix with lambdas on the diagonal, so when we subtract that from A, that amounts to subtracting lambda from each diagonal entry. We need to take the determinant of that. So I'll expand along the first row, and that works out to this expression, which, after some algebra, gives us this polynomial. I'll set this equal to 0, and I need to solve for lambda. It turns out this factors into the following expression. I figured this out using Wolfram Alpha, and you're welcome to too. You can also figure it out by hand, knowing that the possible candidates for these roots, these solutions for lambda, are going to be plus or minus the factors of 18, and then using long division. In any case, we now know what our eigenvalues are. They're going to be lambda equals 6, -3, and -1. Next, let's figure out our eigenvectors. For the eigenvalue lambda equals 6, we're going to be solving the equation A minus 6i times some vector x equals the 0 vector. We can do that by writing down the augmented matrix with a minus 6i here, and then the 0 vector here. So that's this matrix. I can solve by converting this to reduced row echelon form. I'm going to omit the details. In fact, I actually solved this using Python. But this is the answer, and from here we can find the eigenvectors. Let's set x3 as a free variable. We have x1 minus x3 equals 0 and x2 minus x3 equals 0. So the eigenvectors are the form x3, x3, x3. In other words, they're of the form x3 times the eigenvector 1, 1, 1. And I can just use 1, 1, 1 as an eigenvector. A similar computation for lambda equals -3 goes like this, and a computation for lambda equals -1 goes like this. Let me copy my eigenvalues and eigenvectors here and make some observations. First of all, the eigenvalues for this matrix are all real numbers. This may not seem so surprising to you because we've been working with examples intentionally with real eigenvalues, but it actually is significant. It turns out that for any symmetric matrix, it'll never have complex numbers as the solutions to its characteristic polynomial. It'll always be just all real numbers. So that's the first kind of nice thing about symmetric matrices. The second thing that I want to point out is that all these eigenvectors are orthogonal. Let me give them names, v1, v2, and v3. And now if I take v1 dot v2, I get 0. v1 dot v3 is 0, and v2 dot v3 is 0. This is no coincidence. In fact, this is true for any two eigenvectors of distinct eigenvalues for a symmetric matrix. In this video, we looked at an example that illustrated two important facts that are true about all symmetric matrices. The eigenvalues of symmetric matrices are always all real numbers. No non-real complex numbers at all. And secondly, the eigenvectors of symmetric matrices for distinct eigenvalues are always orthogonal. In other words, if v1 is the eigenvector for eigenvalue lambda 1, and v2 is the eigenvector for eigenvalue lambda 2, and lambda 1 is not equal to lambda 2, then v1 dotted with v2 is 0. I'll show you the proofs of these facts in a different video. In a previous video, we stated two facts about the eigenvalues and eigenvectors of symmetric matrices. First, we said that the eigenvalues of a symmetric matrix are all real numbers. No complex numbers that aren't real occur as the roots of the characteristic polynomial. The second fact that we stated is that the eigenvectors of a symmetric matrix corresponding to distinct eigenvalues are orthogonal. This video gives proofs of these two facts. So the first fact we want to prove is that if A is a symmetric matrix, then all of its eigenvalues are real numbers. To prove this, let's suppose that lambda is an eigenvalue and V is an eigenvector for that eigenvalue. If we compute the length of A times V squared, remember that's the same thing as A times V dotted with A times V, which is the same thing as taking the A times V vector, which is a column vector, transposing it to make a row vector, and then multiplying by AV, which is a column vector. That matrix multiplication also multiplies corresponding entries and adds them up, just like dot product does. Now remember, when we take the transpose of a product, that's the same thing as doing the product of the transposes in the other order. So I can rewrite this as follows. And since A is symmetric, A transpose is just the same thing as A. Now, since V is supposed to be an eigenvector for the eigenvalue lambda for A times V is just lambda times V. Let me pull the lambda out. And once again, A times V is lambda times V. Once again, pull the lambda out. And V transpose times V is just the same thing as V dot V, or the same thing as the length of V squared. Therefore, if I put the far left side and the far right side of this string of equations together, I get the length of AV squared is lambda squared times the length of V squared. In other words, if I divide by the length of V squared, I'm getting that lambda squared is the length of AV squared over the length of V squared. Notice that it's legit to divide by the length of V squared because V is supposed to be an eigenvector, so it can't be the zero vector, so it can't have length 0. So I'm not dividing by 0 here. In fact, I have something on the numerator that's got to be positive or 0. A times V could actually be the 0 vector if lambda is a 0 eigenvalue. And then on the bottom, I have something that's just got to be strictly positive. When I divide something greater than or equal to 0 by something greater than 0, I get something that's greater than or equal to 0. So lambda squared is greater than or equal to 0, which means I can take the square root of it, and lambda is a real number. Next, let's prove that if A is a symmetric matrix, then the eigenvectors associated with distinct eigenvalues are orthogonal. So let's take lambda 1 and lambda 2 to be distinct eigenvalues. And that is, they're different numbers. So, and let's let v1 and v2 be eigenvectors for lambda 1 and lambda 2 respectively. Okay, so what we want to show is that v1 dotted with v2 is 0. But I'm going to start instead by looking at lambda v1 dotted with v2. So that's the same thing as the matrix A times v1 dotted with v2, which is the same thing as taking A times v1, that column vector, transposing it to a row vector, and multiplying, doing matrix multiplication with v2. Now I'll rewrite that transpose as v1 transpose A transpose v2, but A transpose is the same thing as A, since A is symmetric. And since v2 is an eigenvector of A with eigenvalue lambda 2, that's the same thing as v1 transpose lambda 2 v2. So if I pull out the lambda 2, v1 transpose v2, that's the same thing as lambda 2 v1 dotted with v2. Therefore, I have lambda 1 times v1 dot v2 is equal to lambda 2 v1 dot v2. If I pull everything over to the left side and factor out the v1 dot v2, I know that lambda 1 minus lambda 2 is not 0 since lambda 1 and lambda 2 are distinct, and therefore v1 dot v2 must also be 0. So we've now proved these two facts about the eigenvalues and eigenvectors of symmetric matrices. The key components of the proof were the definition of eigenvalues and eigenvectors, the definition of symmetric matrices, and this key idea of rewriting dot product in terms of the transpose of the first vector to turn it into a row vector, matrix multiplied by the second vector, column vector. This video is about diagonalizing symmetric matrices. In the video about diagonalizing matrices in general, we saw that if we have a matrix A, that's an n by n matrix, with n distinct real numbers as eigenvalues, then A can be written as a product of matrices P times D times P inverse, where D is an n by n diagonal matrix, and P is an n by n invertible matrix. Writing A in this form is called diagonalizing A. We constructed the diagonal matrix D by stringing together all the eigenvalues of A. And we constructed the invertible matrix P by stringing together eigenvectors for each of these eigenvalues as the column vectors for P. Now suppose we add the condition that A is a symmetric matrix. That means that A transpose is the same as A. We still assume that it has n distinct real eigenvalues. Then A can be written as a product of P times D times P inverse, where D, again, is an n by n diagonal matrix, and P this time is an n by n orthogonal matrix. Recall that an orthogonal matrix is a matrix whose column vectors form an orthonormal set. Recall that an orthogonal matrix is automatically invertible because its inverse is given by its transpose. So by starting with a symmetric matrix, a matrix with a little bit extra structure, then in our diagonalization we get P to be an orthogonal matrix, a matrix with also a little more structure. So how do we know that this is possible? Well, we're going to use pretty much the same construction as we did before. We'll let D be the diagonal matrix whose entries on the diagonal are the eigenvalues of A. Let's call those eigenvalues lambda 1, lambda 2 through lambda n. Now we'll pick an eigenvector for each eigenvalue, and I'll call those v1, v2 through vn. So v1 is an eigenvector for lambda 1, and so on. From the previous video on symmetric matrices and their eigenvalues and eigenvectors, we know that the eigenvectors v1 through vn are all orthogonal to each other. Well, now they might not be orthonormal though. They might not have length 1, but let's just take w1 to be v1 divided by its length, and w2 to be v2 divided by its length, and so on. Then the w1s through wn's will still be orthogonal, but they'll also have length 1. So they will be an orthonormal set. If you're worried about why they're still orthogonal to each other, just consider, say, w1 dotted with w2. That's v1 just rescaled dotted with v2 rescaled. And if you pull out the scalars, then you just have a real number times v1 dot v2, and since these were already orthogonal, their dot product is 0, and therefore the dot product of w1 and w2 is still 0. So now we're going to take this orthonormal set of vectors, w1 through wn, and we're going to let P be the matrix we get by putting those column vectors together into an n by n matrix. Since we have that A times any of the wi's is equal to lambda I times wi, we know that A times the matrix of the wi's all stuck together is going to be this matrix. But the matrix on the right side is just exactly what we get by taking the matrix with columns w1 through wn and multiplying it by this diagonal matrix. If you think about what happens when you compute each entry of this product, you'll see that this is what you get. So now we have that A times P, because this is our matrix we called P, is equal to P times D, our diagonal matrix, and therefore A is equal to P times D times P inverse, by multiplying both sides of this equation by P inverse on the right. So we've diagonalized A, and because we started with a symmetric matrix and just made sure our eigenvectors were rescaled to be length 1, we ended up with an orthogonal matrix for P. So this is what we just proved. If A is an n by n symmetric matrix with n distinct real eigenvalues, then A can be written in this form: D is a diagonal matrix, P is an orthogonal matrix. But in fact, as you might have noticed, we don't actually need to state that these eigenvalues for A are real, because if A is a symmetric matrix, its eigenvalues are automatically real. So that was kind of a redundant statement there. In addition, it turns out, although I won't prove it here, that we don't even need to know that A has distinct eigenvalues. It could have the same eigenvalue repeated twice or more. Like that eigenvalue could be a multiple root of the characteristic polynomial. And we would still be able to write A, diagonalize A in this way. Let's finish with an example. Let's orthogonally diagonalize the matrix given here. Orthogonally diagonalize means we write A as P, D, P inverse, where this is a diagonal matrix, and this is an orthogonal matrix. So to do this, we need to start by finding the eigenvalues, since that's what's going to go into our diagonal matrix D. So I'll write down the characteristic polynomial. That determinant works out to this expression, which factors into lambda minus 9 times lambda minus 4. When I set that equal to 0, I see that my eigenvalues are going to be 9 and 4. Next, I'll compute the eigenvectors for each of these eigenvalues. So for lambda 1 equals 9, I'm solving A minus 9I times some vector equals a 0 vector. The matrix A minus 9I is this matrix, which I'll rewrite as an augmented matrix and row reduce as follows. I'll let x2 be a free variable, and I know that 2x1 minus x2 is 0, so x1 is 1/2 x2. So I have eigenvectors of the form 1/2 x2 x2, or that is x2 times 1/2 1, and so I can use 1/2 1 as an eigenvector, except I want all my eigenvectors to have length 1, so they'll be an orthonormal set. And the length of this eigenvector, I'll call it v1, length of v1 is the square root of 1/2 squared plus 1 squared, the square root of 5/4, or the square root of 5 over 2. So I need to use v1 over its length, which works out to, let's see, 1/2 divided by square root of 5 over 2, and 1 divided by square root of 5 over 2. That simplifies to 1 over square root of 5 and 2 over square root of 5. Notice that this rescaled eigenvector is still itself an eigenvector. It's like using this eigenvector where x2 was 1 over square root of 5 over 2. I can find the eigenvectors for the eigenvalue lambda 2 equals 4 similarly. Once again, the length of the eigenvector that I found is not equal to 1. In this case, its length is equal to the square root of 5. So, as before, I just rescale my eigenvector by dividing by its length. Now that I've found my eigenvalues, found corresponding eigenvectors, and made them length 1, I'm ready to construct my matrices D and P. The diagonal matrix D will have its diagonal entries from the eigenvalues, and the invertible matrix P will have its columns from these length 1 eigenvectors that we just found. I invite you to check that this matrix P really is an orthogonal matrix, and that if you find its inverse, which is just its transpose, and then take P, D, P inverse, you get back to the original matrix A. In this video, we worked out how to diagonalize a symmetric matrix A by putting the eigenvalues of A into the diagonal matrix D and putting eigenvectors of A as the columns of the matrix P, after first making sure to rescale those eigenvectors to have length 1. When we do that, we end up with a matrix for P that's not only invertible, but actually orthogonal. This video is about linearly dependent and linearly independent vectors. Consider these three vectors, A, B, and C. A linear combination of these vectors is any sum of scalar multiples of the vectors, such as 3 times A minus 4 times B, which works out to the vector with entries -1, 2, 5, 8. Another linear combination would be A plus 1/2 B minus 2C, which works out to the vector with entries -1/2, 5/2, 7/2, 9/2. And in general, a linear combination of vectors v1 through vn is any sum of scalar multiples of the vectors. We can put in any real numbers for c1 through cn, including zeros and including negative numbers, which is why we could think of this subtraction as really a sum where one of the coefficients is -4. So let's try to figure out if this vector d is a linear combination of a, b, and c. In other words, can we write d as some number x1 times a plus x2 times b plus x3 times c? We could write this out as follows, or we could even write it out as a system of linear equations. Recall that solving a system of linear equations like this can be done by row reducing the augmented matrix, where we augment by the constant terms that here were on the left side of our equations. I'll omit the details of row reducing and just write down the final form, which tells us that we can indeed solve this system of linear equations with x1 equals -1, x2 equals 11, and x3 equals 0. As a check, if we write down -1 times the vector A plus 11 times the vector B plus 0 times the vector C, we do indeed get the vector 10, 9, 8, 7. So D is indeed a linear combination of A, B, and C. In fact, we didn't even need C. The coefficient of C ended up being 0. The set of vectors v1 through vn are called linearly dependent if at least one of the vectors can be written as a linear combination of the others. So in the previous example, A, B, C, and D were linearly dependent because vector D could be written as a linear combination of the others. Equivalently, we can say that v1 through vn are linearly dependent if there are scalars x1 through xn, not all of them 0, such that x1 times v1 plus x2 times v2 plus all the way through xn times vn is equal to the 0 vector. Specifying that the xi are not all 0 is important because we could always make this sum equal to 0 just by making the x's all equal to 0. Let's see why these two definitions are equivalent. Suppose we have the statement of definition 1, that one of the vectors can be written in as a linear combination of the others. Let's say for example, v3 can be written as a linear combination of the other vectors. Then we can get an expression like the one in definition 2 just by subtracting over v3 to the other side. So we have exactly the expression from definition 2 with the c's functioning as the x's, and notice that these x's are not all 0 because the coefficient of v3 is -1, which is not 0. And conversely, suppose we have the condition in definition 2, so we have an expression like this where all the x's aren't 0, but the sum is 0, then we can just find an x that's not 0. Let's say, x4 is not 0, and use that to solve for v4 in terms of the other v's. So we can write x4 times v4 in terms of all the other v's, and then just divide both sides by x4, which is a number that's not 0, to isolate v4 and get v4 as a linear combination of the other vectors, which is exactly the condition we need for definition 1. So enough about linearly dependent vectors. Let's talk about linearly independent vectors. Well, they're vectors that are not linearly dependent. In other words, in terms of definition 1, the vectors v1 through vn are called linearly independent if it is not possible to write any one of the vectors as a linear combination of the others. Or, thinking in terms of definition 2, the vectors v1 through vn are linearly independent if it's not possible to write an expression like this one, where multiples of the vectors add up to 0, except for if those coefficients, x1 through xn, are all zeros. So the vectors are linearly independent if the only possible scalars, x1 through xn, that make this expression 0 are x1 equals 0, x2 equals 0, and all the x's are 0. So let's see if these three vectors are linearly dependent or linearly independent. One way to do that is to write down the equation x1 times u plus x2 times v plus x3 times w equals the 0 vector, and see if we can find solutions for x1, x2, and x3 that are not just all zeros. I can rewrite this equation as follows, or I can write it as this system of linear equations. Solving this system of linear equations can be done by writing down the augmented matrix and converting it to reduced row echelon form. Once again, I'll omit the details of row reducing it and just write down the final answer. From this matrix, we can see that the only solution is that x1 is 0, x2 is 0, and x3 is 0. So there are no other solutions besides the x's all being zeros, so that means that these three vectors are in fact linearly independent. In this video, we defined linearly dependent and linearly independent vectors. Linearly dependent vectors are redundant in some way. You can find a vector in the group that can be written as a linear combination of the other vectors. Whereas you can think of linearly independent vectors as all being necessary for the collection. You can't write any one of them as a linear combination of the others. This video gives an algorithm, known by the name of Gram-Schmidt, to convert a set of linearly independent vectors into a related set of orthogonal vectors. So suppose we have n vectors, v1, v2, v3, all the way through vn, that are linearly independent. Recall that this means that none of these vectors is a linear combination of the others. How can we use them to construct n vectors w1 through wn that are orthogonal? Recall that two vectors are orthogonal if their dot product is 0. So I'm going to show you an algorithm to do this. And this algorithm basically replaces one vector at a time, building up a bigger and bigger collection of orthogonal vectors. So we'll start with v1. We don't actually need to fix v1. We'll just let w1 be exactly the same thing as v1. I want to note, because we're going to need to use this in a moment, I want to note that w1 is not the 0 vector. Or in other words, v1 is not the 0 vector. And that's because we assumed that we started with a bunch of linearly independent vectors. If this first one were the 0 vector, then this set of vectors wouldn't be linearly independent, because you can always write 0 as a linear combination of a bunch of other things just by letting the coefficients all be zeros. Okay, so now I've hopefully convinced you that w1 is not the 0 vector, and we're going to go on to the next step, which is to fix v2. v2 might need some fixing because it's not automatically going to be orthogonal to v1 unless we modify it. So here's how we're going to modify it. We're going to let w2 be the same thing as v2 minus some multiple of w1. and that multiple is going to be given by v2 dotted with w1 divided by w1 dotted with w1. Notice that this expression here is a scalar because dot products give us scalars, and we didn't divide by 0 because w1 is not the 0 vector, so its dot product with itself can't be 0. So w2 is a legitimate vector, and now let's see what happens when we take w2 and dot it with w1. That's the same thing as taking this expression for w2 and dotting it with w1. Let me distribute the dot product. And now the w1 dot w1 is going to cancel out, and I'm left with this expression v2 dot w1 minus v2 dot w1. So that's going to go to 0. Therefore, w2 is orthogonal to w1. And we've made a good start. We now have two vectors, w1 and w2, that are orthogonal to each other. Note also that w2 is not going to be the 0 vector. That's because w2 is a linear combination of v2 and w1, w1 being the same thing as v1. So w2 is a linear combination of v2 and v1, and since these v vectors are linearly independent, we can't get a linear combination of them equaling 0 unless the coefficients are all 0, and the coefficient of v2 is 1, not 0. Let's continue by fixing up v3 using the same ideas. So we're going to let w3 be v3 minus a multiple of w1 minus a multiple of w2. The multiple of w1 is going to be given by v3 dot w1 over w1 dot w1, and the multiple of w2 is going to be given by v3 dot w2 divided by w2 dot w2. w3 is a legitimate vector because it's just a linear combination of other vectors, and notice that w1 dot w1 can't be 0 since w1 is not the 0 vector, and also w2 dot w2 can't be 0, so we're not dividing by 0 here. Now I claim that w3 is going to be orthogonal to both w1 and w2. If I take w3 dot w1 and distribute the dot product, I get a w2 dot w1, which I already know is 0 because w2 was orthogonal to w1, and after canceling some w1 dot w1s, I get an expression that's equal to 0. Similarly, if I dot w3 with w2, I get now this middle term goes to 0 since w1 dot w2 is 0, and now this third term cancels with the first term to give us 0. So w3 indeed is orthogonal to both w1 and w2. The same argument as before tells us that w3 cannot be the 0 vector. It's a linear combination of v3, w1, and w2, but w1 and w2 are themselves linear combinations of v1 and v2. So w3 is really a linear combination of v3 and some v1s and v2s whose coefficient of v3 is 1, and so linear independence says that can't give us the 0 vector. So we continue in this way, fixing up v4, then v5, and so on. Finally, the last vector vn will replace with wn, which will be vn minus a multiple of w1 minus a multiple of w2, and so on, until finally we subtract a multiple of wn minus 1. Anytime I dot product this with a previous w vector, I'm going to get 0. For example, if I dot product it with w3, then all of these terms would go to 0 because all the previous w's are orthogonal. And the w3 dot w3 would cancel, and I'd be left with vn dot w3 minus vn dot w3, which would give us 0. A similar argument shows that wn dotted with, say, w4 or any other of the w's would give us 0. So in the end, we have w1 through wn all orthogonal vectors. And arguments like we made previously can be used to show that they're all non-zero vectors too. Question: are these new vectors w1 through wn still linearly independent? In fact, they are. In fact, any set of orthogonal vectors, none of which is the zero vector, will be linearly independent. That's because if we take a linear combination, x1, w1 plus x2, w2, so on through xn, wn, and if that's equal to the zero vector, then look at what happens if we dot product both sides with, say, w1. Well, on the right side, we'll get 0 since the zero vector dotted with anything is 0. And on the left side, after we distribute the dot product, we'll get a bunch of zeros everywhere since we've got a bunch of orthogonal vectors, and we'll be left with just x1 times w1 dot w1 equals 0. And since w1 is not the zero vector, so its dot product can't be 0, this means that x1 must be 0. So dotting with w1 shows that x1 is 0. If we dot with w2 instead, the same argument will show us that x2 is 0. And so on, we can keep going to show that all the xi's are 0. Therefore, these orthogonal vectors, w1 through wn, must be linearly independent. So one last theory question before we get to an example. If we have these w1 through wn now, a set of non-zero orthogonal vectors, how can we build a set of n orthonormal vectors? Remember, orthonormal means they're not only orthogonal to each other, but they each have length 1. Well, fortunately, that's pretty straightforward. All we do is, I'll call the new set of vectors by u's. I'll let u1 be w1 over its length, u2 be w2 over its length, and so on, up through un, which is going to be wn divided by its length. Each of these u's is just a w rescaled to be length 1. So they'll definitely all be length 1, and they'll also still be all orthogonal. For example, if I take u2 and dot it with u3, that's going to be the same thing as w2 over its length dotted with w3 over its length. And if I factor out the 1 over the length of w2 and the 1 over the length of w3, I'm just going to get that scalar times w2 dot w3. Well, this is going to be 0 since the original w's were orthogonal, and therefore the dot product of the u's is 0. The u's are orthogonal. So we have a straightforward method of converting non-zero orthogonal vectors into orthonormal vectors. So let's conclude with an example. Let's apply this algorithm to convert this set of 3 vectors into an orthogonal set of vectors. I'll let you check on your own that this is in fact a set of linearly independent vectors, or you can take that on faith. So our first vector, w1, is just going to be the same thing as v1. Our next vector, w2, is going to be v2 minus v2 dot w1 over w1 dot w1 times w1. Let's do some scratch work on the side. v2 dot w1, that's the dot product of these two vectors, which works out to 3, while w1 dot w1 is the dot product of those two vectors, which also works out to 3. So w2 is going to be v2 minus 3 over 3 times w1. That works out to the vector with entries -1, 2, -1, 2. Now we need to build the vector w3. That's going to be v3 minus v3 dot w1 over w1 dot w1 times w1 minus v3 dot w2 over W2 dot W2 times W2. Again, I'll do some computations on the side. And so we end up with this expression, which works out to minus 3, 1, 2. So these are our new vectors, W1, W2, and W3, and you can check that they're in fact all orthogonal to each other. If I wanted to go one step further and get a set of orthonormal vectors, I could just divide each of W1, W2, and W3 by its length. This video gives an algorithm for turning a set of linearly independent vectors into a set of orthogonal vectors, and if we want, we can go one step further and turn them into a set of orthonormal vectors. This video introduces the idea of singular value decomposition, a powerful way of rewriting matrices that has important applications to real-world problems like image compression and data simplification. Recall that an n by n square matrix A is said to be diagonalizable if there's a diagonal matrix D and an invertible matrix P such that A can be written as P times D times P inverse. Recall also that if we start with an n by n symmetric matrix, let's call it S, then we can diagonalize S in such a way that P is an orthogonal matrix. The singular value decomposition generalizes these ideas to a general matrix A that need not even be a square matrix. In order to generalize this idea of diagonalization to matrices that aren't even square matrices, we first need to generalize the idea of a diagonal matrix. So up to now, we've only talked about n by n square matrices being diagonal matrices. And we said that a square matrix is a diagonal matrix if all of its non-zero entries lie on the diagonal. So we might have some non-zero entries here, and then we have zeros everywhere else. So we'll say that an m by n matrix, where m and n might be different, is called a diagonal matrix if all of its non-zero entries lie on its diagonal, where the diagonal entries are the entries whose row number and column number are the same. So for example, here's a 4 by 2 diagonal matrix, and here's a 3 by 5 diagonal matrix. For an m by n matrix A, the singular value decomposition, abbreviated SVD, of A is a way of writing A as a product of a matrix U, a matrix sigma, and a matrix V transpose, where sigma is an m by n diagonal matrix, V is an n by n orthogonal matrix, and U is an m by m orthogonal matrix. Let me draw these matrices with squares and rectangles to illustrate the dimensions. So here's A, an m by n matrix. Here's U, an m by m square matrix. Sigma is an m by n matrix, just like A. And V transpose is an n by n matrix. And actually V is also n by n. The singular value decomposition has some features similar to the diagonalization of a matrix, namely that the middle matrix, sigma, is diagonal, and that it's a product of three matrices. In fact, since V is orthogonal, V transpose is the same thing as V inverse. So we could make this look even a little more like a diagonalization by writing this as U times sigma times V inverse. Also, like the diagonalization of a symmetric matrix, the singular value decomposition uses matrices on the outsides that are orthogonal. But the singular value decomposition is different from a diagonalization in that U and V may be different matrices. In fact, if M and N are different numbers, if we have a purely rectangular matrix, not a square matrix, then U and V have to be different matrices because they've got different dimensions. A singular value decomposition has a lot of the same power as a diagonalization does, namely the power to write a matrix A in terms of a much simpler diagonal matrix, which is why it has important applications, as we'll see in future videos or in class. For now, let's look at an example of a matrix and its singular value decomposition. Here's an example of a singular value decomposition. We have a 3 by 2 matrix A, and it turns out that we can write A as U times sigma times V transpose using these given matrices here. Notice that this last matrix needs to be V transpose, not the original V. It's clear from looking at it that sigma is a diagonal matrix. I'll leave you to check, if you want to, that the matrices U and V are both orthogonal matrices. In other words, each pair of columns of U has a dot product of 0, and if I dot product any column by itself, I get 1. And same thing for V. I'll also let you check, if you're interested, that this product really does work out to the original A. Now, you may be wondering, how did I come up with these matrices, U, sigma, and V, that work? Well, to be honest, I use software. But there is a method, an algorithm, that will allow us to do a singular value decomposition for a matrix A like this, and I'll show that to you in another video. In this video, we introduced the idea of a singular value decomposition and compared it to diagonalizing a matrix. In future videos, we'll look at how to do a singular value decomposition, in other words, how to find U, sigma, and V, and what some of the applications are. Recall that a singular value decomposition for a matrix A is a way of writing A as the product of 3 matrices. A square matrix U, that's actually an orthogonal matrix, a rectangular matrix sigma, the same dimensions as A, that's actually a diagonal matrix, and a square matrix V transpose, where V and V transpose are both square matrices and orthogonal matrices. In this video, I'll walk you through an algorithm to start with the matrix A and find these 3 matrices U, sigma, and V. I'll also do one example. But I'm going to postpone to another video explaining why this algorithm actually works, why at the end of it we actually get matrices whose product is A, and why the matrices U and V that we get are actually orthogonal. So for an M by N matrix A, how do we find orthogonal matrices U and V and a diagonal matrix sigma such that A is equal to U sigma V transpose? First, let's consider the case when A is a tall matrix. In other words, when M is greater than or equal to N. First, we're going to find the matrix A transpose times A. Notice that that will be an N by N matrix, and it'll actually be an N by N symmetric matrix, since the transpose of A transpose A is A transpose transpose, which is A transpose A. Same thing as we started with. We're going to find the eigenvalues of A transpose A. Since A transpose A is symmetric, these eigenvalues are all real numbers. But even better, as a previous video shows, any matrix of the form A transpose A has eigenvalues that are actually non-negative real numbers. So we have that these are all real numbers greater than or equal to 0. Now in this class, we'll only work with situations when all the eigenvalues of A transpose A are distinct. So I can call them lambda 1 through lambda n, and I'm going to order them in such a way that lambda 1 is bigger than lambda 2, is bigger than lambda 3, and so on. More generally, in some examples, the eigenvalues won't all be distinct numbers. Sometimes they'll be a root of the characteristic polynomial that's repeated. And so if that's the case, we'll still write them all down. And if the root of the characteristic polynomial has, say, multiplicity 3, we'll just write it down 3 times. And so in more generality, we'll just be able to say that lambda 1 is greater than or equal to, because there might be some repeated eigenvalues. Now, when we were diagonalizing a matrix earlier, we just used those eigenvalues for the matrix as our diagonal entries. But this time we're going to do something a little bit different. We're going to use the square root of our eigenvalues as our diagonal entries. So I'm going to call the square root of lambda I, I'm going to call this sigma I. Notice that it's no problem taking the square root of lambda I, since lambda I is going to be greater than or equal to 0. Notice also that we still have the sigmas in descending order. These numbers, sigma 1 through sigma n, are called the singular values of A. And now I'm going to build the rectangular diagonal matrix sigma by taking sigma 1 through sigma n along the diagonal and filling the rest in with zeros. If m is bigger than n, then the last few rows of sigma will all be zeros. To me, it kind of makes sense we want to use the square root of lambda I instead of lambda I, because lambda I is the eigenvalue for this product, which is kind of almost like doing a squared. So it makes sense the square root of lambda I would be more related to just A itself. Okay, so now we've got sigma, the middle matrix of the 3. Next, let's work on V. So for step 2, we're going to take an eigenvector, V1 for lambda 1, V2 for lambda 2, etc., each of which has length 1. If the first eigenvectors we pick don't have length 1, then we can just rescale them by dividing by their length to get an eigenvector of length 1. Now we're going to build the matrix V using V1 through Vn as its column vectors. Again, for our class, we'll only ever consider the situation where the lambda eigenvalues are all distinct and we just take one eigenvector for each of them. If you were to consider a more general situation when maybe, say, the first eigenvalue was repeated, so lambda 1 and lambda 2 were the same, then you would end up having to choose 2 eigenvectors for that eigenvalue in such a way that those 2 vectors were not only length 1 but also orthogonal to each other. And it turns out that this is possible since these eigenvalues came from a symmetric matrix, but that's beyond the scope of our class. Okay, so now we have built our matrix V, from which we can easily get V transpose. Notice that these eigenvectors are eigenvectors for the matrix A transpose A, which is an n by n matrix. So these vectors have dimension n, and so the matrix V will be an n by n matrix. And the last thing we need to do is to find our matrix U. So to find U, we're going to compute A times Vi over sigma I for each non-zero number sigma I. Since the matrix A is an m by n matrix, when we multiply A by the n-dimensional column vector, we're going to get an m-dimensional column vector. And dividing it by the scalar, it'll still be an m-dimensional column vector. We'll have no more than n of these column vectors. It would be exactly n, except for some of the sigma i's might be 0. So I'm going to call these column vectors u1 through ur, say, where r is less than or equal to n. And I'm going to start building U, the matrix U, by stringing these column vectors together. Ultimately, I want U to be an m by m matrix, and I might not have enough columns to do that. So I need to fill out my matrix U with some more columns, m minus r of them to be exact. There are a few ways to do this, but in practice, the simplest thing to do is usually just to pick m minus r columns at random, and then using the Gram-Schmidt orthogonalization algorithm to make them orthogonal to each other and to the original U1 through UR columns, and dividing them by their lengths if necessary to make them length 1. So I'll call these extra columns after we orthonormalize them. I'll call them UR plus 1 through UM. There are a few details here that I'm sweeping under the rug. In particular, in order to do the Gram-Schmidt orthonormalization process, we need all of our columns together to be linearly independent. Turns out if you pick columns at random, usually you will get things that are linearly independent. If you have bad luck, you might have to do some repicking. There are some other ways to fill out the matrix U, but in the interest of keeping things short and simple, I won't go into those details here. In addition, as you'll see in the applications video, it doesn't actually matter a whole lot what the end of this matrix looks like. Okay, so to summarize, we build the diagonal matrix sigma using the eigenvalues of A transpose A and taking their square roots. Then we find V by using the eigenvectors for A transpose A. And then we find U by computing A times those eigenvectors divided by those singular values and filling out the matrix one way or another. I want to remind you that we haven't yet verified that this process actually gives us a singular value decomposition. That is, we haven't verified that U and V are actually orthogonal matrices and that the product U sigma V transpose actually gives us A. That'll happen in the next video. I wanted to do this for a tall matrix first, where m is greater than or equal to n, because that way we could be sure that the number of eigenvalues we get for A transpose A, n eigenvalues, would be small enough to fit into our rectangular matrix sigma. Next, we'll look at the case of a wide matrix. Although it turns out that a similar process could be used when A is a wide matrix, that is, when m is less than or equal to n, instead, I'm just going to repeat what we did on the previous slide for the tall matrix B, which is given by A transpose. That'll give us B as a product of some U times some sigma times some V transpose, where the dimension of B is n by m, since it's the transpose of A, and the dimensions of U, sigma, and V are as follows. Now I can write A, which is B transpose, as U sigma V transpose transpose, which is the same thing as V transpose transpose, sigma transpose, U transpose, or V sigma transpose, U transpose. And since V and U were orthogonal matrices and sigma a diagonal matrix, I'll still have orthogonal matrices here and a diagonal matrix here, all of the correct dimensions. Let's do an example and find the singular value decomposition for this 3 by 2 matrix. Step 1 is to compute A transpose A and find its eigenvalues. A transpose A is this product, which works out to this 2 by 2 symmetric matrix. To find the eigenvalues, let's write down the characteristic polynomial, which is given by the determinant of the matrix with entries 5 minus lambda, 2, 2, and 8 minus lambda. Here's the determinant, which simplifies to lambda squared minus 13 lambda plus 36. When I factor this and set it equal to 0, I get that the eigenvalues of A transpose A are lambda 1 equals 9 and lambda 2 equals 4. So now I can write down my diagonal matrix sigma, which should also be a 3 by 2 matrix. Here it is. Recall that the diagonal entries, the sigma i's, are given by the square roots of the lambda i's. Now let's move on to step 2. finding the eigenvectors for A transpose A, and building V with them. I encourage you to pause the video and work this out for yourself before going on. Here's what I get. So for eigenvectors, I have the vector 1/2, 1 and the vector -2, 1, but since those aren't length 1, I'm going to want to rescale them by dividing by their lengths. The length of this first eigenvector is the square root of 1/2 squared plus 1 squared. That's the square root of 5/4, or the square root of 5/2. So I'm going to take the eigenvector and divide by that length, which gives me the length 1 eigenvector, 1 over square root of 5, 2 over square root of 5. For the other eigenvector, its length is going to be the square root of 5, and so I can divide by the square root of 5. Now I can build my matrix V by using these two length 1 eigenvectors as my columns. And I'm ready to go on to the third step, which is using the column vectors A, Vi over sigma I to build the matrix U. Here the Vi are the column vectors of V. So let me write down A V1 over sigma 1 and A V2 over sigma 2. Those work out to these vectors. These will be my first two columns of U, and you might notice that they're already length 1 and orthogonal to each other, but I need to fill U out with a third column that's also length 1 and orthogonal to these first two columns. For this third column, I'm going to start with the column vector 1, 0, 0, although any column vector that's linearly independent from these two would do. And then I'll apply the Gram-Schmidt orthonormalization process to make it orthogonal to U1 and U2. I'll omit the details, but this is the vector I get, which is in fact orthogonal to both U1 and U2. It's not length 1, so I'll just calculate its length and divide by it to get my last orthonormal vector, U3. We put these three columns together, and we have our matrix U, and we finished our singular value decomposition using these three matrices. This video gave the methods for finding a singular value decomposition. It was a complicated process, but it will prove to have powerful applications. In a previous video, we walked through an algorithm for finding the matrices U, sigma, and V used for a singular value decomposition. In this video, we'll go through some of the theory behind it to explain how we know that the U and V that we found are orthogonal matrices, and how we know that when we multiply these three matrices together, we actually get back to A. Here are the steps we used to find the singular value decomposition for a tall matrix A. By tall, I just mean that the number of rows is greater than or equal to the number of columns. First, we found the eigenvalues for the product A transpose times A, and we took their square roots to get our singular values, sigma sub I. We put those sigma sub i's down the diagonal of an m by n matrix to get our matrix sigma. Next, we found length 1 eigenvectors for A transpose times A and used them as our columns for the matrix V. The simplest situation is when A transpose A has all distinct eigenvalues, so we can just take one eigenvector for each eigenvalue. It's a little more complicated if A transpose A has repeated eigenvalues, and I didn't go into those details. Finally, we computed the first few columns of the matrix U by taking A times V sub I over sigma sub I for the non-zero singular values, sigma sub I, and we got the rest of the columns for U by choosing linearly independent vectors, using Gram-Schmidt to orthogonalize them, and dividing by their lengths to make them length 1. It's clear from the construction that we get a diagonal matrix for sigma. But here are the other details we need to check to make sure we have a legitimate singular value decomposition for A. First, we need to check that when we do this process and then multiply U times sigma times V transpose, we actually do get the matrix A back. And then we also have to check that V and U are honest-to-goodness orthogonal matrices. In addition, it's interesting to note that the non-zero eigenvalues for A transpose times A end up also being the non-zero eigenvalues for A transpose. And it's interesting that the vectors we use for the first few columns of U, these vectors of the form A times V sub I over sigma sub I, are actually eigenvectors for A transpose. So we'll also look at why these two facts are true. These facts show that even though we build our matrices U, sigma, and V in sort of an asymmetric way, focusing on A transpose A instead of A transpose and using eigenvectors to get V, but doing something entirely different for U, even though we use an asymmetric method, there is, in fact, a symmetry to how U is formed, V is formed, and the choice of doing A transpose A instead of A transpose. I'm going to start by showing these two matrices are orthogonal. Then I'll show that A is the product we think it should be, and then I'll show these additional facts. I'm not going to say very much about why V is an orthogonal matrix. Recall that the columns of V are eigenvectors for A transpose A, rescaled as needed to be length 1. But it's a fact from a video about symmetric matrices that the eigenvectors for distinct eigenvalues of a symmetric matrix are orthogonal. Since A transpose A is a symmetric matrix, at least in the case when it has distinct eigenvalues, we're going to get orthogonal eigenvectors, and so rescaling them will mean they're orthonormal, and our matrix will be an orthogonal matrix. It turns out that when A transpose A doesn't have distinct eigenvalues, it's still possible to choose eigenvectors in such a way that they're orthogonal to each other. And so rescaling them will still give us an orthonormal collection of vectors to make an orthogonal matrix V. Next, let's convince ourselves that U is an orthogonal matrix. The first few columns of U are of the form A times VI over sigma I, where VI is one of the column vectors of V. So if we take two of these column vectors, two different ones, say AVI over sigma I and AVJ over sigma j, and we want to check if these are orthogonal, we're going to take the dot product. Well, that's the same thing as taking the first vector, transposing it, and doing matrix multiplication with the second vector. I can pull these scalars out, and now I have AVI transpose matrix multiplied by AVJ. Using transpose rules, this is the same as this expression. Since when we take the transpose of a product, it's the product of the transposes in the opposite order. Now Vj, remember, is an eigenvector for A transpose A. So when I multiply A transpose A times Vj, I'm just going to get lambda j times Vj. Let me pull out the lambda j. But Vi transpose times Vj is the same thing as doing the dot product of Vi and Vj. And if I and j are different, then this is just 0, because my matrix V, we already showed, was orthogonal. So the dot product of distinct columns of U in those first few columns of this form are all going to be orthogonal. And furthermore, if I take something of the form AVI over sigma I and dot it with itself, then this exact same computation is going to get me down to lambda I over sigma I Vi dot Vi. Since sigma I is the square root of lambda I, this quotient of scalars is just equal to 1, and since the matrix V is an orthogonal matrix, this dot product is equal to 1, so this whole expression evaluates to 1. Therefore, the initial columns of the matrix U, the ones of this form an orthonormal set. But when we added on some more columns to U to complete it to an M by M matrix, we did so in a way to ensure those last columns would be orthogonal to each other and to the first columns because we used the Gram-Schmidt orthogonalization process. And we also made sure they were length 1 by dividing by their lengths if needed. Therefore, all of the columns of U are an orthonormal set, and U is an orthogonal matrix. So now let's show that A really is equal to U times sigma times V transpose. Since V is an orthogonal matrix, V transpose is the same thing as V inverse. So we need to show that A is equal to U sigma V inverse, or equivalently, that A times V is equal to U times sigma. Well, when we multiply two matrices together, that's the same thing as multiplying the first matrix by each column of the second matrix and then just concatenating those columns together. I'll write this down. And when we multiply a matrix by a diagonal matrix on the right, that's the same thing as multiplying each column of the first matrix by the corresponding diagonal entry. I'll write this down. Notice that if U is an M by M matrix and sigma is an M by N matrix with M bigger than N, then the last few columns of U, they don't even appear in this expression. They're completely irrelevant because all the entries in those last few columns just get multiplied by the zeros down at the bottom of sigma. So this is what we're trying to show. In other words, we need to show that A times VI is equal to sigma I times UI for I between 1 and N. For sigma I not equal to 0, we know that UI is defined as A times VI over sigma I, so sigma I UI is going to be sigma I A VI over sigma I. Canceling out the sigma i's, we get the equality that we're looking for. And if sigma I is equal to 0, then sigma I UI is just 0. But lambda I, which is sigma I squared, is also 0. So A VI is also going to be 0 times VI, which is the 0 vector also. So we have the equality of matrices that we need to prove that A is equal to U times sigma times V transpose. Next, let's show that the non-zero eigenvalues for A transpose A are also the non-zero eigenvalues for A transpose. Suppose that lambda sub I is a non-zero eigenvalue for A transpose A. In other words, there is a non-zero vector, say xi, such that A transpose A times xi is equal to lambda I times xi. Let's multiply both sides of this equation on the left by the matrix A. That gives us A transpose A xi equals A lambda I xi. If I pull out the lambda I on the right side, give the vector A xi a name, say yi, then I have the equation A transpose yi is equal to lambda I yi. Note that yi is not the 0 vector, because if it were, then A transpose times yi, in other words, A transpose A xi, would be a 0 vector, which would mean that lambda I would actually be a 0 eigenvalue. Therefore, we know that yi is an eigenvector for A transpose with eigenvalue lambda I. So lambda I is a non-zero eigenvalue for A transpose. Conversely, if mu I is a non-zero eigenvalue for A transpose, i.e. A transpose times some, say, zi is equal to mu I times zi, then the same kind of argument, multiplying both sides on the left by A transpose, will show that mu I is a non-zero eigenvalue for A transpose A. So the non-zero eigenvalues for these two matrices, A transpose A and A transpose, are exactly the same. And when we're doing the singular value decomposition, even though we build the matrix sigma in terms of the eigenvalues for A transpose A, we could just as well have built them in terms of the eigenvalues for A transpose. Finally, I want to show that the vectors we use for the first few columns of U, the vectors of the form A times VI over sigma I, where the VI are the eigenvectors for A transpose A, the columns of the V matrix, and the sigma I are the singular values, the non-zero singular values. I want to show that these first few columns of U are actually eigenvectors for A transpose. This shows that U and V have a lot more in common than we might first have realized. They're both built out of eigenvectors. So to prove this, let's take A transpose and multiply it by A V sub I over sigma I. I'll pull out the 1 over sigma I. And now, since V sub I is an eigenvector for A transpose A with eigenvalue lambda I can rewrite this as 1 over sigma I times A times lambda I V sub I. Now let me pull out the scalar lambda sub I and rewrite things a little bit. And we see that this vector, A V sub I over sigma I, when we multiply A transpose by it, we just get the same thing as lambda sub I times it. Also, this vector A VI over sigma I is not equal to the 0 vector, because if we multiply A transpose A V sub I over sigma I, then that gives us lambda I V sub I over sigma I, which is not 0 because we're assuming sigma I and therefore lambda I are not 0. Therefore, A V sub I over sigma I is an eigenvector for A transpose with eigenvalue lambda sub I. This video squared away a lot of the details about singular value decompositions. The matrices U and V that we built really are orthogonal. When we multiply U times sigma times V transpose, we really do get back A. In addition, U and V are not so different from each other. V is built with eigenvectors for A transpose A, and U is built with eigenvectors from A transpose. The non-zero eigenvalues for A transpose and A transpose A are the same, so either one can be used to build the diagonal matrix sigma after taking square roots.